Hi, my name is Erfan and I will be your guide in this comprehensive Rust course for beginners. So if you're interested in learning Rust, then congratulations, you have found the right course. So I've designed this course to ensure that you will learn Rust the proper way, using slides and visuals to illustrate concepts and providing exercises we will solve together. This means you will have an appropriate mix of theory and practice that will help you step by step mastering this new awesome programming language. And I strongly advise you to code along because you will learn so much more when actively participating rather than just watching the video. So let's dive in. So what are the goals of this course? First and foremost, getting familiar with core concepts and syntax of the language. We will take a look at data types and data structures, as well as ownership and borrowing. We will see how data is allocated in memory and how we access the data. And we'll take a look at standard library, generics, traits, lifetimes, and much more. Basically everything you need to become a great Rust developer. So why would you want to learn Rust? Now there would be, I guess, 1,000 reasons, but I have here put together some of the main ones. Now Rust is a really fast language in terms of execution time. It provides a rich type system. It doesn't have a garbage collector, which is part of the reason why it's so fast. It provides useful compiler outputs, and you will see that in the exercises we are solving. It guarantees memory safety, and it's the most beloved programming language since 2016 according to Stack Overflow, meaning now 7 years in a row. And we are experiencing fast adoption in various branches. Now over here you can see a table which shows various programming languages and their score in terms of energy efficiency and execution time. And as you can see, Rust is one of the languages on the top of the list. Now over here are some resources that you can learn with. Now I guess the main resource would be the Rust programming language. Really fantastic book, and I recommend you to read it. Then there is Rustlings. These are small exercises, basically programs which you have to debug. Then there is Rust by example. So if your style is more focusing code and less on text, then this would be suitable for you. And there is a website called Rust by Practice, and that is what we will cover together. And if you want to go more advanced, there is a book called Rust Forestations, and it's also very much recommended to read that. So before we dive into the first topic, I want to show you the website of Rust by Practice. And you can access it by going to the URL practice.rs. And this is the website. And over here, as you can see, these are all the topics we will cover together. Right? Now, this will be the first one, variables. And as you can see over here, we have small exercises that we will solve together. Now, before we start, I want to show you something else. And of course, we will keep up with the tradition and write a hello world program. So you can go to the rustlang.org website. This is the official website of the Rust Foundation. And you can click over here, Playground. And as you can see over here, you can write Rust code and then execute it. And it's really cool because you even have the Vim key bindings over here. And you can even choose themes like that. And let's write our first program. So every program in Rust starts in the main function. This is the starting point of execution of every Rust program. And we declare functions with the fn keyword. So to print out to standard output, we can use the print line macro. As you can see, we write print ln exclamation mark, and then we can provide here the string we want to output. Like that. And then you can hit run. And as you can see, we have executed our first program. So congratulations. I hope you coded along. And now we start with the actual course. So variables. Variables are assigned using the let keyword. So if you're coming from a JavaScript background, this might seem familiar. You can print to standard output by the print or print ln macros. So print and print ln are basically very much the same, but print ln adds a new line at the end of the output. And scope of a variable is defined by the block of code in which it is declared. Now a function is a named block of code that is reusable. And shadowing allows a variable to be redeclared in the same scope with the same name. So let's solve some exercises. Binding and mutability. A variable can be used only if it has been initialized. Fix the error below with least amount of modification to the code. So again, we are starting always in the main function. Now over here we have two variables. And again, we declare variables with the let keyword, then the name, and over here we have a type annotation. Now don't worry too much for now, we'll cover that in the next topic to come, but for now think of i32 as an integer type, right? And then we have here the assert eq macro, which stands for assert equality. So this macro takes two arguments and just basically asserts that these two are equal. In case they are not equal, the program will panic, meaning immediate exiting and returning an error message. If they are in fact equal, then the program will just continue executing. So as you can see, we want here that x is equal to a value of 5. So we can initialize x over here with a value of 5, like that. And to run this program, you can either click here or you can press Ctrl Enter. And let's read that over here, uninitialized but used error. So when you use a variable, it has to be initialized with a value, which makes sense, right? You can't use something which isn't initialized yet. Now y over here is uninitialized but also unused. This will only output a warning. Now over here you can't see the warning actually, but if I take this code and put it over here, as you can see, it gives us a warning unused variable y. Okay, to fix that, we can prepend it with an underscore, like that. All right. Use mute to mark a variable as mutable. So in Rust, a variable in its nature is immutable, and you have to explicitly state that you want a variable to be mutable. So fill the blanks in the code to make it compile. As you can see, we are here using a variable x. So we want over here to declare x and initialize it with a value of 1. Now over here we are mutating x. which means this variable x over here should be mutable, and we do that using the mute keyword, like that. Now this over here is shorthand syntax for this. Alright, so we take the value of 1, we add 2 to it, and then we assign it back to x, meaning x will then hold 3, right? Now, just a quick note, I will always try to annotate the type in this course. Most of the time it's not necessary, so when you see me annotating types, it's actually not because this is necessary, but just because I want to make stuff as clear as possible. So in this case, this would hold an integer type, and again we will cover that in the next topic. Let's see. As you can see, this is compiling, x is equal to 3. Scope. A scope is the range within the program for which the item is valid. Fix the error below with least amount of modification. So over here we are initializing the variable x with a value of 10, an integer type. Alright. Now here we have another scope. We also can call it the inner scope, and this would be the outer scope, right? So in this scope over here, we are declaring another variable, y. Now we over here try to print out x and y, and we can do that by placing inside the println macro these placeholders over here, and then providing as additional arguments over here the variables we want to put the values inside here. So for example, if we provide x over here, then this will get replaced by 10 because x is holding a value of 10. And as you can see, in the outer scope we are doing exactly the same. Now this program won't compile, and the reason is because a variable is only valid inside the scope in which it was declared. So for example, the variable y is declared inside the scope, meaning the variable y is only valid until this point. Alright, that means we can't use y here. So what would be the solution? The solution would be very simple. We just initialize the variable y in the main scope, in the outer scope over here, meaning x and y, both of them are valid until this point over here, right? Because this over here is the main scope. Let's see. As you can see, this is compiling. Fix the error with the use of define x. Now we can have other functions besides main. So over here we have the function define x, and as you can see, we are initializing a variable x which holds a string. Now this would be the type annotation for a string, right? Don't worry too much about the annotations now, because we will cover that, but just to let you know. Now the problem here is that in main we are trying to access x. Now in this scope over here there is no variable with the name of x, which means that this program won't compile, because the compiler will tell you I can't find over here a variable with the name of x. So what we can do over here is actually taking this line and putting it inside the function over here, because as you can see, in this scope of the function, a variable x has been declared and initialized. But if I run this program now, nothing will happen. And that's because, as I've said, the starting point of every Rust program is in the main function. Now, when we run the code, nothing will get executed. And that's because we have to actually call this function for it to do something. So in this case, we can call a function like that, just providing the name of the function and these parentheses. And as you can see, the output will be hello world, right? Because over here we are providing X to the print line macro, and we are appending to it comma world, like that. Shadowing. You can declare a new variable with the same name as a previous variable. Here we can say the first one is shadowed by the second one. Only modify assert EQ to make printline work, print 42 in terminal. As you can see over here, we are initializing the variable X, which holds an i32 type, an integer type. Now in this scope over here, we are initializing another variable with the same name, X. But over here, we are initializing it with a value of 12 instead of 5. And that means when we assert the value of X over here, it should actually be 12, right? Now, what would be the value of X in this outer scope? If you said 5, then you're right, because this variable over here has been declared in the main scope, in this scope over here. That means X is holding a value of 5. Now in this scope over here, X holds a value of 12. And these are basically two different worlds, right? So the variable X declared in the main scope doesn't actually care about the variable X declared in this scope over here. They are separate. Now over here we are shadowing X in the main scope, meaning we redeclare and reinitialize the variable X, again with an integer type. Now when we output X, it should actually print out 42. As you can see, this will be the output. Number 6, remove a line in the code to make it compile. Now over here we have a mutable variable X which holds 1, an integer type. Then we are assigning 7 to X. Now X holds 7, right? Then we are shadowing and rebinding, so we are redeclaring X and reinitializing it. And we initialize it with a value of X, meaning with 7, right? And then over here we are mutating X, and that means we are here incrementing X by 3. Again, using this shorthand notation, which would equate to that. And this would actually fail. And I want you to look at it and think about it. What over here might cause an error? So over here, as you can see, we are redeclaring X. And over here we are mutating X. Now, as I've said, every variable in Rust is in its nature immutable, meaning if we redeclare X like that, X will be immutable. Even if it was mutable over here, when we shadow it, then it will be immutable again. So what we can do over here is just using the mute keyword again, so X stays mutable. Now, you might ask, okay, why even shadowing? we can just assign a new value to x. Why is this even a thing? And you can see that here very good. So y over here holds an integer type, right? An integer 4. Now when shadowing, we can assign to the variable a value of another type. In this case, for example, a string, right? So y will then hold a string type. Right, let's run that. And as you can see, this compiles. Now this line over here is completely useless. I hope you noticed that, because we are taking x and assign it again to x, which basically is the exact same thing as we had over here. So completely useless. Of course, they are doing that to learn the concept, but in real life, you don't need this line. All right, you can just do it like that. And as you can see, this also compiles. Unused variables. Fix the warning below with only one solution, 2 distinct solutions. So as you can see, of course, we want 2 stars, so we will do with 2 solutions. Now the problem here is that this program won't actually output warnings, right? So I will again copy that, and I will put it inside the Rust playground, like that. So if we run this program now, as you can see, we get a warning, unused variable x. Now I have showed you that before. The easiest method would be to prepend the variable name with an underscore. As you can see, we don't get the warning over here. The second way would be to do it like that. This is telling the compiler that it should allow unused variables. So if you run it again, as you can see, no warning. So we have solved that. Destructuring. We can use pattern with let to destructure a tuple to separate variables. Now tuples, we will cover that in a later topic, but for now just think of tuples as a data structure that can hold various values, even of different types. So fix the error below with least amount of modification. So as you can see over here, we have a tuple, right, holding 2 integers, 1 and 2. And this over here is called destructuring. So we are using the let keyword, and we use this syntax over here to destructure these values into variables x and y. So x will then hold a value of 1 and y will hold a value of 2. Now over here we are mutating x. Now again, this variable here would be immutable, because in Rust every variable in its nature is immutable, and we have to explicitly state that we want to have it mutable. So what we can do over here, like we did before, we use the mute keyword, like that. And then this should actually compile. So x holds 1 here, and then we increment x by 2. So x should in the end hold 3 and y should stay the same as it was. And as you can see, this is compiling. Destructuring assignments introduced in Rust 1.59. You can now use tuple, slice and struct patterns as the left hand side of an assignment. So this is very useful actually. So we can declare 2 variables at once. So here we declare x and y, and this would be the same like writing let x and let y, right? So you're writing 1 line of code instead of 2 lines here. Now again, we declare here the variables, and we can then destructure these data structures over here. So we have here a tuple, and we are destructuring it. And notice over here we don't need to use the let keyword again, because we have already declared these variables over here, right? So we assign 3 to x, and this value over here we don't care about, so we can use these double dots over here. Now this over here is an array, and again we will cover that, don't worry. And this array holds 2 values. Now we don't care about the first one, but we want to destructure the second one into a variable called y. Now fill the blank to make the code work. In this case we have here an array, right? Remember, assert eq takes 2 arguments, and both of them have to be the same, equate to the same output, right? So what would be the value of x? It would be 3, because we have destructured here 3 into the variable x, and the same goes for here. We have destructured 2 into a variable y, which means y will then hold 2. Alright, and we are done with the first topic. Easy start, and see you next time. Now let's look at numbers in Rust, and we will start with integer types. Now an integer is basically a whole number, meaning it doesn't have a fractional part. And integers can come in 2 different forms. They can either be signed or unsigned. Now a signed integer can represent both positive and negative numbers. And I remember that because signed might stand for the minus sign that could be prepended to it. And unsigned integers are always positive integers, meaning they don't have a minus sign, hence unsigned. Now integers can come in different lengths. So there can be 8-bit integers, 16-bit, 32, up until 128 bits. And each length over here has 2 distinct types, one for signed and one for unsigned. So for example, if we have a variable which holds an unsigned 8-bit integer, we would type annotate that with the type U8. Or for example, we have a signed 64-bit integer, we would annotate it as I64. Now the last element in the table over here is arg, and arg stands for architecture. Now that means that the size of these 2 types, I size and U size, are dependent on the computer's architecture. Now I guess most of you guys today run computers with 64-bit architecture, meaning I size and U size have a size of 64 bits or 8 bytes. Alright, now the default types in Rust are for integers I32 and for floats F64. So if we don't annotate anything, the compiler will infer it to these types. Now my head is in the way. Now to make sense of all of this, you will have to understand the binary number system. Now if you're familiar with binary, just skip ahead because you don't learn anything new here. But I just want to ensure that we are all on the same page. So if we consider this decimal number over here, 42, and let's look at each distinct digit. So we would have 4 and we would have 2, right? Now 2 would be in the ones place and 4 would be in the tens place. And if we would have more digits here, here would be the hundreds place, thousands place, and so on. Now, As you can see, we are here using a base of 10. Why is that? Because in the decimal system we have 10 distinct digits to represent numbers, right? 0 to 9. And as you can see, we are here doing an exponentiation with an exponent of 0, because this is actually a mathematical rule which states that anything with an exponent of 0 will always evaluate to 1. So it doesn't matter which base you use, if you have an exponent of 0, the result will always be 1, right? 10 to the power of 0 would be 1, 4 to the power of 0 would be 1, and so on. And over here we have 10 to the power of 1, which would be 10, right? And then what we do is just we are multiplying the digits of our number with these exponentiations, right? So we would, for example, here 4 times 10 to the power of 1 plus 2 times 10 to the power of 0. Now again, 10 to the power of 1 would be 10, and 10 to the power of 0 would be 1. And then we would multiply these numbers together and then add this, and we would have 42, right? Something which is very natural to you and you don't even think about it, right? Because decimal numbers are everywhere. Now in computers, things actually look a little bit different. Let's, for example, again consider the decimal number 42. Now this would be the binary representation of this number, 00101010. And as you can see, we have here 8 digits. Now a digit is called bit, right? And a bit is the smallest possible unit of information a computer can hold. Okay, now we have 8 bits over here, and 8 bits make up 1 byte. And we over here have actually the same logic as we did over here, but with a base of 2, because again we can only represent 2 digits in a computer, and that's because a transistor can only be in one of 2 states. Either it's conducting electric current or it's non-conducting, 0 or 1, right? So the logic stays the same. Here we have 2 to the power of 0, which would be 1 because of the rule we have talked about. 2 to the power of 1 would be 2. 2 to the power of 2 would be 4. 2 to the power of 3 would be 8, and so on. And as you notice, the number here doubles. 1, 2, 4, 8, 16, and so on. Now, this over here is actually the fascinating part about computers to me personally, because it's just crazy if you think that everything represented, this video over here, and graphical models and 3D games and everything is stored and represented with only 2 digits. Mind-blowing, right? So we actually here do the same thing. We are just multiplying the bits over here with the exponentiations. Now we won't consider the 0 bits because anything multiplied by 0 will always be 0, right? So we are just caring about the 1 bits over here. So we are multiplying 1 times 2 to the power of 1, which would be 2, right? Because 1 times 2 would be 2. Then 1 times 2 to the power of 3, which would equate to 8. And 1 times 2 to the power of 5, which would be 32, as you can see over here. And then we are basically just adding these numbers together and we have 42. And this is the way your computer stores all of your data. All right. Now you might ask, okay, how far can we go with this? What would be the largest possible number we can represent? And let's for that see the range of 8-bit integers. So the smallest possible unsigned 8-bit integer would be 0, right? I hope this makes sense, because if we have a 0 in every position over here, the result will just be 0, right? Now the largest possible unsigned 8-bit integer would be 255. And that's the case when every single position over here holds a 1, right? And again, we are then just multiplying the 1 by the exponentiations over here and add it together. And you might now think, okay, 255 isn't a lot. What if I want to represent bigger numbers? And there is a simple solution to that. We are just adding more bits over here, right? Because the more bits we have, the larger number we can represent. So let's see, for example, a 16-bit integer. Again, the smallest possible 16-bit integer unsigned would be 0. And this is if every position over here holds 0. Now the largest possible 16-bit integer unsigned would be 65,535. Okay? And again, this would just be if we had in every single position a 1, right? Again, just adding the results of the exponentiations over here all together, and we would have this result. Now, as you can see, the more bits we have, the more we can represent. Now, what about signed integers? Again, signed integers can represent negative numbers. So signed integers use a concept called 2's complement, where the processor will take a number over here, for example 42, and this would be the binary representation of this number. Then it will invert this binary number, meaning a 0 becomes a 1 and 1 becomes 0. Right? Just inverting. And then after inverting the number, we add one single bit. Okay? So we add 1 here. This would then equate to 0, and we have a carry of 1. And then we add here 1, and we would have 1, and the rest stays the same. Now this would then be the binary representation of minus 42 or negative 42. Now the most significant bit over here is actually the sign bit. If it is 0, then it means the number is positive. If it is 1, then the number is negative. All right? And that's why there are distinct types for signed and unsigned. And the ranges for signed and unsigned integers vary, right? And over here we have an illustration just to see the ranges. For example, for I8, a signed integer of 8 bits, the range would be from minus 128 to 127. So the smallest possible number we can represent with a signed 8-bit integer would be minus 128, and the largest one would be 127. And as you can see, again, the more bits we have, the larger and smaller the integer can go, right? And again, unsigned integers never go below 0. Right, then we have U size and I size. So these are, as I've said, architecture dependent. So on a 32-bit architecture computer, the size of these U size and I size type would be 32 bits. On a 64-bit architecture, it would be 64 bits. And this is also called pointer-sized integer type, because it matches the size of a word in a given platform. So what is a word? You have to understand that the processor does not read 1 byte at a time from memory, it reads 1 word at a time. So in a 32-bit processor, it can access 4 bytes or 32 bits at a time, and in a 64-bit processor, it can access 8 bytes or 64 bits at a time. Now, if we look at this very simplified representation of computer memory, where we have over here addresses and over here the data, and each location over here holds data of 1 byte. All right. Now, in a 32-bit architecture, the size of a word is 4 bytes, right? 32 bits. Which means that the processor can access 4 bytes at a time. So the processor will read this section over here as 1 word, right? It's basically a unit of data. And what you have to take from this is this statement over here. usize gives you the guarantee to be always big enough to hold any pointer or any offset in a data structure. So the usize type can hold memory addresses which can point to any location in computer memory. That's very important. So let's see, floating point. There are 2 types, F32, which is of size 32 bits, and F64, which is of type 64 bits. Now the representation of these floats are according to the IEEE 754 specification. So let's look at some exercises. Tips: if we don't explicitly assign a type to a variable, then the compiler will infer one for us. Now, remove something to make it work. As you can see over here, we have a variable x which holds an I32 integer, right? Now over here we have a mutable variable y which holds an unsigned 32-bit integer, right? So over here we are trying to assign x to y. Now this would actually fail because we can't assign a variable of a type to a variable of another type. It's not possible. So what we can do over here to fix that is actually just omitting the type. And this will then implicitly hold an I32 type, right? Because this is the default integer type in Rust. Now over here we are initializing another variable z, and what would be the type of z? Right, it would be I32. All right. Fill the blank. So over here, as you can see, we have a value 38 which is of type U8. So we can also annotate a type directly on a value, meaning this value over here 38 is of type U8. Now the problem here is that the variable over here v expects a type of U16. So we can't initialize a variable which expects a certain type with another type. But what we can do over here is using the as keyword, which basically can convert an integer type to another integer type. So we can use here as and U16. This will then compile. Tips: if we don't explicitly assign a type to a variable, then the compiler will infer one for us. Now we know that already. Modify assert EQ to make it work. So over here we are initializing the variable x with a value of 5. What would be the type annotation? It that would be i32, right? It's the default integer type in Rust. Now in this assert EQ macro, we have here a string EU32. We don't vary yet about this method. I will explain that in a later episode. And on the other side of the assert EQ macro, we have a function call. So we call type of with an argument of x. Actually a reference to x, but again, don't worry, we'll cover that. So when we call this function over here, it basically just gives us back the name of the type. So if we pass x over here, we would get back i32, right? Because this variable over here holds a value of type i32. Now this would then actually fail, right? Because we want here that type of x returns EU32. So what we can do is just changing this type annotation over here. All right. Fill the blanks to make it work. Now over here we have a data type, for example i8, and the constant max. Now max just returns the largest possible number that can be represented with the mentioned data type. So for example i8 max would be 127, right? This would be an signed 8-bit integer, and we have seen the ranges. Now the max for an unsigned 8-bit integer would be 255. All right. Fix errors and panics to make it work. Now over here we have a value 251, which is of type U8, and we add 8 to it. Now in this case the compiler will infer the types. So this would be U8, and the variable itself will hold an U8. Now can you spot the problem over here? The problem is we have seen that U8 can only represent up to 255, right? So over here we would have 259. So this is not possible. So what we can do over here is just changing that to the next bigger data type, for example U16. Now then we have here a data type i8, a signed 8-bit integer, and we call the checked add method. Now this is actually the same as doing it like that, but in a safer way, because we have to handle the error. And unwrap over here, we will cover that. So this is actually a little bit safer, but it still will panic, because again i8 cannot represent 259. It would be an overflow. So again we can over here just say we want an i16, because an i16 can without problems represent 259. So v1 will then hold u16 and v2 will hold i16. Again, I'm just doing this for clarity. You don't have to annotate the types. Alright, modify assert to make it work. Now as you can see over here we have numbers in different representations, or basically in different number systems. So this is decimal, this is hexadecimal, this is octal, and this is binary. Okay. Now the decimal over here has an underscore, and this is just a delimiter. So this is just for readability. It doesn't affect the actual value. Now let me convert that over here. We would have 2024. This is already in decimal system. Then over here we would have 255, Then over here we would have 63, and then over here, I hope you remember, this would be 255. Now if we calculate these, as you can see, the result would be this value over here. Like that. And this basically proves that in Rust you can perform mathematical operations on different number systems, right? Now floating point, fill the blank to make it work. As you can see over here we have a floating point value. So what would be the type? I will annotate it directly. So it would be F64. This is the default floating point type, right? Now over here we have an F32, and over here we have an F64, right? Like that. Again, type annotations are not necessary. Now if we pass X to the type of function over here, what would be the return value? It would be F64, right? Make it work in two distinct ways. So if we execute this program over here, as you can see, this would panic. Now the problem here is floating point precision. The result won't be exactly 0.3. It would be something like that maybe, right? Or something like that. I don't know exactly. But the floating point value is too precise because the default floating point type is F64. So this is really precise, and that's why you have these tiny fractions over here. Now we can solve this using an F32, which is less precise, right? Like that. And this succeeds. Now, two distinct ways. We can also use the as keyword. Like that. So let me first move my head over here again. So range, two goals. First, modify assert to make it work. Second, make print line output 97 to 122. Now over here, as you can see, we have a mutable variable sum. What would be the type annotation? It would be I32. Okay. Now over here we have a for loop, meaning we are iterating over some range, and then we are executing an instruction inside this code block over here multiple times. Basically the times we are iterating over this range over here. Now in each iteration the variable I will hold a different value, right? So in the first iteration it would be -3. In the second iteration it would be -2. In the third -1, and so on until we reach 1. Why 1? Because 2 over here is excluded. And that's always the case when using this syntax. The endpoint of the range is always excluded. So we are iterating from -3 to 1. Okay? Now let's actually do these iterations manually. So we start with 0, right? Now in the first iteration I would be -3. So 0 plus -3 will be -3, right? So sum will then hold -3. Now in the second iteration I will be -2. So -3 plus -2 will be -5. Third iteration -1, -5 plus -1 will be -6. Then in the next iteration I will be 0, so it doesn't have any impact. And in the last iteration I will be 1, so -6 plus 1 will be -5. So the value of sum after this for loop will be -5. Now over here we again have a for loop, and this time we are iterating over a range of characters, namely from A to Z. Now this time Z over here is included because we are using the equal sign over here, which means we want a range from A to Z where the endpoint Z is included. And C over here will then hold in each iteration a character. So in the first one it would be A, then it would be B, then C, and so on. And we just print out the characters. Let's see how that looks like. As you can see, just printing out each character from A to Z. Now we want to have an output of 97 to 122. So let's look at the ASCII table. As you can see, in memory a character would be stored as a numerical value. Now of course in memory everything is stored as binary numbers, but it would be stored as the binary representation of these decimal numbers right here. So we want to go from 97A to 122Z, right? So it's actually pretty simple. Instead of outputting the C as character, we want to output it as an U8, for example, right? And then as you can see we have the ASCII code for the characters from A to Z, lowercase. Alright. Then over here, exercise 10, fill the blanks. So we are here importing from the standard library the ops module, range and range inclusive. Now we have seen the shorthand syntax, and this would actually be the more verbose way to write that, but I think no one actually does it this way. Over here we have a range which starts at 1 and ends at 5. Now again 5 would be excluded, right? Like that. Now range inclusive means we range from 1 to 5 where 5 is included, and we would write that shorthand syntax like this: 1 to 5 and 5 is included. Right, let's see the last exercise in this topic, computations. Fill the blanks and fix the errors. So as you can see over here we have integer addition. So 1 plus 2 will be 3. And the compiler over here will infer these types. So because we have over here an U32, an unsigned 32-bit integer, it will infer these values over here to be of the same type. All right. Now over here the same thing, we have 1 minus 2 would be minus 1, and the compiler infers these types. Then over here we have 1 minus 2, which is equal minus 1. The problem over here is that we are dealing with an unsigned 8-bit integer. Now remember, unsigned integers can never be negative. So what we can do to fix that is just converting it to an I8, a signed 8-bit integer. And signed integers can represent both positive and negative numbers. Now over here we would have 150. And if there are no type annotations here, the default integer type will be inferred, which will be I32. Now over here again we have the problem of floating point precision, so we can cast that to an F32. Like that. Over here we have the modulus operator, and the modulus operator basically gives back the remainder of a division. So if we divide 24 by 5, we would have a remainder of 4. Now, as you can see, here we have Boolean logic and bitwise operations, and I want to show you some slides so we get the concept. Let's start with Boolean logic. Boolean logic deals with values that are either true or false. And there are three basic operations: and, or, and not. And over here you can see the truth tables of these operations. So let's see the AND operator. Now the AND operator takes two inputs and produces one output. Now the only time it outputs true is when both of the inputs are true. Otherwise it will always return false. In an OR operation, if either one of the inputs is true or both of the inputs are true, then it will output true. If both of the inputs are false, then it will output false. And the NOT operator will just basically invert the Boolean value. So over here we have not false, and this would evaluate to true. And not true will evaluate to false. Now let's see bitwise operations. Bitwise operations are operations that manipulate individual bits that make up a binary number, treating each bit of a binary number as a separate unit and perform logical operations on them. So it's very important that you get that in bitwise operations we are treating each bit as a separate unit, and we are doing some manipulation on each individual bit and not the binary number as a whole. And we will cover here AND, OR, XOR operations and bitwise shifting. Now there are a lot more, but I will just cover the ones in the exercise. Let's start with the AND operator, this ampersand symbol over here. AND returns 1 only when both of its inputs are 1. So similar to Boolean logic, as you can see, the AND operator takes two inputs and produces one output. Now, as you can see in the truth table, if both of the inputs are 1, then the output will be 1. In any other case, the output will be 0. Let's see the OR operator, this symbol over here. OR returns 1 if at least one of its inputs is 1. If both inputs are 0, the output will also be 0. So same thing as in Boolean logic, if either one of the inputs or both of the inputs are 1, then it will output 1. So the only case it outputs 0 is when both of the inputs are 0. And let's see XOR. XOR or exclusive OR returns 1 if the inputs are different and 0 if the inputs are the same. So it's basically similar to the OR operator, with the difference that if both of the inputs are 1, then it will output 0. So the inputs must be different, so it will output 1. Alright, if they are the same, it will output 0. And this is basically a building block of your computer. So your computer is made up of logic gates, and these logic gates perform these operations all the time, millions of times in a second. Then let's see bitwise left shift. So we have over here the decimal number 1. This would be the binary representation. Now we want to left shift by 5 positions. So we take this bit over here and move it 5 positions to the left. So this bit over here will be at this position after the bitwise left shift operation. Alright, and that means we then have a value of 32 because this is the binary representation of decimal 32. And bitwise right shift is basically the same. Now over here we have a hexadecimal value and we want to right shift it 2 positions. Now this value over here would be 128 in decimal. And this would be the binary representation of 128. Now we want to right shift it 2 positions, meaning we take this bit over here and shift it 2 positions to the right, meaning the bit will then be in this place. And again we would have 32 because this over here is the binary representation of that number. Alright, let's see. So true and false would be false, right? Because in an AND operation, both of the inputs must be true in order for it to output true. Now true or false would be true, because in an OR operation, only one of the inputs have to be true. And not true would be equal to, that's right, false, right? Like that. Now let me run the program so we can see the result of these bitwise operations. So as you can see over here, 0011 and 0101 is 0001. Why is that? Because again, we are here considering each individual bit as a unit and performing manipulation on each distinct bit. Now over here, as you can see, we are taking the rightmost bit over here and we are performing the AND operation with the rightmost bit over here, meaning 1 and 1 would be 1, right? Because AND, if both of the inputs are 1, then it will output 1. In any other case, as you can see, 1 and 0 would be 0. 0 and 1 would be 0. 0 and 0, of course, would be 0. Now let's see this OR operation. We have 1 or 1. This will output 1. We have 1 or 0, which will output 1 again, right? Because in an OR operation, if either one of its input or both of them are 1, then it will output 1. 0 or 1 is 1, and 0 or 0, of course, is 0. And then we have XOR. 1 XOR 1 would be 0. Because remember, XOR, the inputs must be different in order for it to output 1. Like over here, for example, 1 XOR 0 would be 1, right? The inputs over here are different, 1 and 0. Same over here, 0 XOR 1 would be 1. And 0 XOR 0, of course, will be 0. And as you can see over here, these are the bitwise shifting, so I've covered that in the slides. Alright, see you in the next topic. So we will cover now char, bool and unit. Let's start with characters. So over here, make it work. Now size of val will just return the size in bytes of a specific value. So over here we are initializing the variable c1 with a character. So c1 holds a type of char. Then we pass to the size of val function the variable c1, and this will return the size of this character in memory in bytes, right? And same thing over here, we have c2 also holding a char, and we call the size of val function with this variable. So let me first print out the actual result of this function call. So if I come over here and I will do a print line statement, and just basically outputting the result of this function call. So let's see. As you can see, the output would be 4, meaning this character over here will take up 4 bytes in memory. So the size of C1 is 4 bytes. Now in Rust, the char type is big enough to hold every single Unicode symbol, meaning it is of size 4 bytes, so it's able to hold any Unicode scalar value. Alright? And the same thing over here, the output would be 4, meaning if we call this function, we will get back 4. Alright, make it work. Again, initializing a variable with a char. Then we are calling the print char function with an argument of this variable. As you can see, this function over here, this is the function signature. This function takes as argument c, which is of type char, and then we just print out c. Now the problem over here is that this isn't actually a char. This would be considered a string, because in Rust there is a difference between double quotes and single quotes. So double quotes are for strings and these single quotes are for characters. And as you can see, we just print out the character. Let's see booleans. Make print line work. As you can see, this variable _f holds a boolean value of false. And over here, t also holds a boolean value of true. Now, in an if block, this conditional over here will be checked. If the result evaluates to true, then this instruction inside the curly braces will be printed out. If it evaluates to false, then the program will just ignore this instruction over here. Now in this case we want to print that out, but over here the result would evaluate to false because we are saying not true, right? Because t holds a boolean value of true. So not true would be false. That means this will never get printed out. What we can do over here is just removing this not operator, and then it will work. Make it work. Again, we have some variables that hold boolean types. Now again, this variable over here, t, will also hold a boolean type because this over here is an AND operation. And remember, an AND operation takes 2 inputs and produces 1 output. So the output type will be of type bool. Now true and false would evaluate to false. And then we are comparing t and f. Now f holds true and t holds false, which is not what we want. So what we can do over here is just making this false over here. And then both of them hold a boolean value of false. Unit type, make it work, don't modify implicitly read unit. So the unit type is a type which doesn't hold any value. Its size is 0 bytes, and it's usually, if a function doesn't return any value, then a unit type will be returned, and this happens implicitly, so you don't have to annotate that. Let's see an example. Over here, the _v variable holds a unit type. As you can see, a unit type is basically represented as an empty tuple, and this would be the type annotation, right? So over here we are holding a tuple with two i32 values. Then, as you can see, we have here an assert eq macro. We are comparing v with the output of this function call. Let's see this function over here, implicitly read unit. So all this function does is it will print out something and then goes back to the caller. Now this function over here doesn't return anything. And if a function doesn't return anything, the compiler will implicitly return a unit type, right? But you don't have to annotate that. Alright, so the return value of this would be unit type. Now v over here holds a tuple, meaning this would fail. We have here to provide _v, which holds a unit type. So this holds a unit type, and this function call over here will return a unit type. Alright, what's the size of the unit type? Modify 4 in assert to make it work. As you can see, we are again having this size of val function, and we are providing it this variable which holds a unit type. Now the output would be 0 because unit types are of size 0. So to quickly recap, a char is a single character of size 4 bytes. A Boolean value of true or false is of size 1 byte. And a unit is an empty tuple of size 0 bytes used to return nothing in expressions or functions. So this time I will first show you the slide, and then we will solve exercises. So a statement is an instruction that performs some action but does not produce a value. Function definitions, for example, are statements as well as code that ends with a semicolon usually. And an expression will evaluate to a resultant value. So let's see. Alright, let's see this example. Over here we have x, which holds an u32. Alright, now over here we are initializing the variable y with the resultant value of this whole expression. So as you can see, we can, inside these curly brackets, we can declare variables over here, and then we do some operations and return the value. As you notice, I omit over here the semicolon. That means that this result of this operation will get returned, which means when this evaluates, it will then be assigned to y. So y will then hold the result of this operation. Now all of the code inside these curly braces are considered as an expression because it produces a resultant value, right? It would be this value over here. Now this variable assignment over here would be considered a statement because first of all it ends in a semicolon, and second, it doesn't produce a new value, right? It just assigns a value to a variable. Now y in the end would hold an u32, right? Because we are here performing an operation with values of U32 types. The semicolon suppresses this expression and unit type is assigned to Z. So Z over here would hold a unit type. Why is that? Because we over here have a semicolon. So this code over here doesn't return a value. If we omit the semicolon, then this would be the return value that then gets assigned to this variable, meaning it will then hold a U32. Alright, let's do exercise 1. Make it work with 2 ways. So, as you can see over here, we are initializing this variable over here with this expression inside the curly braces. Now we are here initializing the mutable variable x with a value of 1. So x will hold I32. Then we are mutating x, incrementing it by 2. So x should then hold 3, right? Now over here, this would actually hold a unit type, because over here we have an assignment. So we are adding 2 to the value of x and then reassign it to x. Now the problem is that variable assignments are actually statements, so this should end in a semicolon, because this would be the same as if I would write it like that, right? So we can't return over here a variable assignment, but what we can do is we just return x, because x over here will then hold 3 and then we return x, meaning the value of x is then assigned to the variable v. So variable v will then hold a type of I32. Let's see. This is compiling. As you can see, make it work in 2 ways. Now the second way to solve it is just in this assert EQ macro, we compare v to a unit type, because no value will get assigned to v, and that means the variable v will then hold a unit type like that. Over here, as you can see, we are initializing v with a variable assignment, so this would not be allowed. It's invalid syntax. But what we can do is we use curly braces like that, and then we initialize here a variable x and we return x. This would be allowed. So v then holds an I32. Let's see, over here we have a function call with 2 values 1 and 2. So let's see the function over here. It takes 2 arguments, x and y, of type I32, and it returns an I32 value. Now over here, as you can see, this function just adds x plus y. Now the actual return type over here would be unit type, because as you can see, we are ending this operation with a semicolon, meaning nothing will get returned. So if we omit this semicolon over here, then we would have a return type of I32. Meaning after the function call over here, s will then hold the result of this operation. 1 plus 2 would be 3, so s would hold 3, and that would be a type of I32. So let's now look at functions. A function is a block of reusable code that performs specific tasks. It can take arguments, processes those inputs, and then returns a result. And a diverging function is a function that never returns to the caller. And this would happen, for example, if the diverging function is panicking, looping forever, or quitting the program. So let's see. Don't modify the following two lines. As you can see, we have here a tuple and we are destructuring it. We have already seen how that works. Now over here we have a function call. Now this would be the caller and this function would be the callee. Okay? When we call the function, the flow control will go to this function and the program will continue executing the instructions provided in this function. Now, it's very important that you know that functions always have to annotate types for their arguments. So over here, we would define that x should be of type i32, right? Because y is i32 and we are performing here a mathematical operation, meaning they both have to be of the same type. And as you can see, like in the last exercise, this function wouldn't return a value because over here we have a semicolon. So if we omit that, then this result of this operation will get returned, which means the return type would be i32. Then when this returns, the flow control will go back over here and assign the returned value from this function to variable s, meaning the variable s will then hold a type of i32 and the value would be 3, right? Because we are calling the function with arguments 1 and 2, or x and y over here, which hold 1 and 2. And then this function will just sum it up together, and that means s will hold 3. Over here we are calling the print function. So we go to the function over here, and as you can see, the function just prints out something to standard output, but it doesn't return a value. Now, implicitly the compiler will return a unit type like that, but we don't have to write it. It's implicit. Solve it in two ways. Don't let println work. Alright, so we are here calling a function never return, and this function should never return because, as you can see, the return type over here is defined as exclamation mark, and that means this is a diverging function, a function that should never return back to the caller. Now, we can do this in various different ways, but I will just use the most simple one, which is panic. And the panic macro just causes the program to panic, meaning the program will immediately exit and return an error. As you can see, unreachable statement. So this line over here is never reached, as you can see. And that's what we want, because over here don't let println work. So we never actually reach this point. The program will exit before going back to the caller. Diverging functions. Diverging functions never return to the caller, so they may be used in places where a value of any type is expected. So in the main function we just print out something, and over here we have a function getOption. It takes as argument a value of type U8 and returns option I32. Now we will cover options in a later episode. Now over here we are matching TP, and matching, if you're coming from another programming language, is like a switch block. Okay, we are matching TP, and then if, for example, TP would be 1, then this code block over here would get executed. If it is anything else, then this code block will be executed. And we will cover match statements, but match is just a much more powerful way of pattern matching than, for example, if-else conditionals. So after this match, we are calling this never return fn, and this should never return. So there are some macros we can use here. I've showed you one, the panic macro. Like that. Or we can also use unimplemented, and you use the unimplemented macro if you have a function that is not implemented yet. And we can also use the to-do macro, like that. And to-do is basically very similar to unimplemented, and all of them will cause this function to not return to the caller. In this case, this would be the caller over here. Fill in the blank. So as you can see, we have here a variable b, which then gets matched over here. So if b holds a value of true, then 1 will be assigned to variable v. If b holds a value of false, then it will print out success, and the program will then panic. Now we can here assign false, because I guess we wanted to print out success, right? And yeah, let's see. As you can see, this would be the compiler message if a program panics. Thread main panicked at we have no value for false, but we can panic. That would be this output over here. So we will now cover ownership. And ownership is a concept which is unique to Rust, meaning even experienced programmers can find it difficult to understand this concept. But it's very logical and it all makes sense, and I will use visuals and illustrations to make it easier to understand the concept. So ownership is basically a set of rules that govern memory management. These rules are enforced at compile time. If any of the rules are violated, then the program won't compile. Now let's see the 3 rules of ownership in Rust. First, each value in Rust has an owner. Second, there can only be one owner at a time. Third, when the owner goes out of scope, the value will be dropped. Now, the owner of a value is the variable or data structure that holds it and is responsible for allocating and freeing the memory used to store that data. Let's look at scope. A scope is a range within a program for which an item is valid. We have 2 types of scope. One is global scope, and that means a variable that is declared in global scope is accessible throughout the entire program. And local scope, if a variable is declared locally, it means it is accessible only within that particular function or code block, which in turn means it's not accessible outside of that function or code block. Let's see an example of scope. As you can see, we are here initializing the variable s with a string. That means s over here is the owner of this data, of this string value. Okay? Now s is valid from this point forward. So after initializing s, it will be valid throughout this scope over here, which is defined by these curly braces. So inside of this scope, we can do stuff with s. When this scope is over, s is no longer valid. So s over here, the owner of this data, will deallocate the data that is stored in computer memory, and that means in turn we can't use s after this point. It gets dropped or removed from memory. So when s comes into scope, it is valid, it remains valid until it goes out of scope. And a general rule is the scope ends where the block of code ends. So to understand ownership, you have to understand computer memory. Now, memory is a component in a computer to store data and instructions for the processor to execute. There is a type of memory called random access memory, or RAM, and it is volatile, meaning when you're turning off your computer, all data stored inside RAM is lost. And there are two types of regions in RAM which is used by your Rust program. It is stack memory and heap memory. So now let's look at stack memory, and I want you to imagine a stack of plates. Now, if you want to eat something, you take from the top of the stack a plate, put food on it, eat, and then you will clean up the plate, right? When you're done cleaning, you put the plate back on the top of the stack. And that's exactly what is happening in stack memory. So this concept is called last in, first out, meaning the last thing that is pushed on top of the stack will be the first thing that will get popped from the stack, meaning the first thing that will get executed. Now, all data stored on the stack must have a known fixed size, like integers, floats, chars, bools, and so on. Basically, all the types we have seen so far are all of fixed known size at compile time. Now, pushing to the stack is faster than allocating on the heap, because the location for new data is always at the top of the stack, meaning the program can access data in stack memory at constant time, if you're familiar with time complexity. And types of unknown size will get allocated to the heap, and a pointer to the value is pushed to the stack, because a pointer is fixed size. Don't worry, I will show you illustrations which will make you understand this concept better. Let's see, for example, this simple Rust program. So as you can see, we are starting in main, because main is the starting point of execution in every Rust program. So over here we declare some variables x, y, and z, meaning these variables are local to the main scope, to this code block over here. And because they are local, they can't be accessed outside of this scope. Now over here we have a function call, and we pass it the value of x and of y, right? So as you can see, the addNumbers function takes two arguments of type i32. Then over here we declare a new variable and we assign the result of the operation a plus b, meaning the passed values x plus y, and we assign it to the variable c, and then we just return c, right? So then z over here will hold the returned value. Now when we start execution, main alongside with all the local variables will get pushed to the stack. Then, because we have over here a function call inside main, the add numbers function alongside with all the local variables to this function will get pushed to the stack. If we would have other function calls over here or inside here, then this will also get pushed on the stack, and so on. And then the program will just execute everything that is on the stack from top to bottom. Now let's look at heap memory. Data of no known fixed size belongs on the heap. Allocating data on the heap will return a pointer, an address to a location where the data has been allocated. Allocating on the heap is slower than pushing to the stack. And accessing data on the heap is also slower, as it has to be accessed using a pointer, which points to an address. So if we look at this abstract illustration of heap memory, as you can see, we are allocating to heap memory if the size of the type we are allocating is not known at compile time. And the types can then also be dynamically grown or shrinked, right? The size is not fixed. And we will see examples of these types where this could be useful. So when we allocate to heap memory, let's see, for example, this packet over here, we will get back a memory address. And we need this address so we know where this specific data over here has been allocated. So we then can access it in our program. And an example of a heap allocated type would be the string type. Now, as I've said, all types we have covered so far were fixed size, meaning their size was known at compile time, and they can't grow and shrink. So the difference is a string is mutable, meaning its size can change at runtime. And a string is stored on the stack with a pointer to the heap. So when we initialize a string type, then we will get back a pointer, which then points to the actual data in the heap. And the actual data of the string is stored on the heap. So let's see an example to understand this better. As you can see, we have here the variable s1, which we initialize with a string type over here. And we initialize a string like this, string, double colon, from, and then the actual string. Now, you need to understand that the variable s1 doesn't hold the actual string in this case. It holds a pointer which points to the data that was allocated on the heap. So if we look at s1, we can see that s1 doesn't hold the actual data, but it holds a pointer, and a pointer is basically a variable that holds a memory address. That's what we call pointer. And we have here len, and this is the length of the string we have initialized, and the capacity holds the information of how much space was reserved in heap memory for this specific type. In this case, we have initialized a string with a length of 5, so the capacity will be 5. So 5 locations have been allocated in heap memory. So this place is reserved for this string type. And we will go into much greater detail about capacity. But for now, when we initialize a string with a length of 5, the capacity will be 5. It will be the same. So the size of this S1 variable will be 24 bytes, because each field over here is of type usize. Right? So the pointer is of type usize, the len and the capacity. All of them are usize, and usize, assuming we are on a 64-bit computer, will be 8 bytes. So 3 times 8 bytes will be 24 bytes. Meaning the size of the variable S1 is known at compile time. Because again, the variable S1 will get pushed to the stack memory, and everything that lives on the stack memory has to be of known fixed size at compile time. In this case, all of these fields over here are known fixed size. But we are pointing over here to the actual data in heap memory, which can be dynamically sized, right? It can grow and shrink, and we will see examples of that. So that is actually the point. Important, the S1 variable doesn't hold the actual data, but it holds a pointer to the data in heap memory. Okay, basically a pointer to the location of the first element. And by the way, in heap memory, this data over here is allocated as a contiguous block. Meaning in heap memory, these are all in a contiguous sequence of memory addresses, right? And that's why we only need the memory address of the first location and a length, and then the compiler will know where to look at and how long this sequence of data is. So, copy versus move. Scalar values with fixed size, all types we have covered at the beginning, will automatically get copied in this stack. Copying here is cheap. Dynamically sized data won't get copied but moved. Copying would be too expensive. Let's see an example. Over here, as you can see, we have initialized a variable x with a value of 5. Then we assign x to y. Now the type of this value would be i32, right? Because it's the default integer type. Now, because i32 is fixed size, it means that it lives in the stack memory. And everything that lives in stack memory will automatically get copied. Meaning we are here assigning a copy of x to y, or basically a copy of the value 5. So we are not assigning the actual value, but a copy of that, meaning y and x would point to different memory locations. The value is the same, but the location at which the value is stored is different, because again, when we assign a fixed size integer that lives in stack memory, Rust will automatically copy the value, because copying on the stack memory is cheap. Now over here, as you can see, we initialize a string. And then we assign S1 holding the string to S2. Now, as we've seen, S1 doesn't actually hold the data over here, but it holds a pointer, which is returned when we are allocating this data over here, this string, on the heap memory. So the allocator that allocates this data on the heap memory will return a pointer. And that means if we assign S1 over here to S2, then S2 will only get a copy of the pointer and not the actual data. So that is how that might look like. As you can see, we have S1, which is initialized to hold a string. Now, S1 will then be assigned to S2. And as you can see, this is how this might then look like. We have here the variable S1 and S2. Now, the actual data over here didn't get copied. The one thing that got copied was the pointer alongside with the metadata, meaning these two variables now point to the same location in memory, right? Now this would violate the second rule, which states that there can only be one owner at a time. So we can't over here have two owners to the same data in heap memory. So what Rust will do is it will drop S1. It will delete S1, and that means S2 will then be the owner of the data. So the first variable S1 will be dropped and cannot be used after assigning it to S2 to avoid dangling pointers. So after assigning S1 to S2, we can't use S1 again. And that's different, like we saw over here with, for example, integers, which are fixed size. We can use, after assigning x to y, we can use both of these variables, x and y, without any problem. Because again, here the value got copied. So the compiler will drop the variable s1, meaning s2 will become the owner of this string. And that means we can't use s1 after this point. Now, what if you want to actually have a deep copy, meaning you actually want to copy the data that is allocated in heap memory? We can do that, but we have to explicitly state that we want to do that, because as I've said, this might be expensive. If you have large data that is allocated on the heap, and if Rust would implicitly copy all the data all the time you're assigning variables, then this would be really expensive. And that's why we have to explicitly call over here the clone method. So when we take s1, which holds a string, and we call upon it the clone method and assign this to s2, then that is what this might look like. As you can see, s1 again doesn't hold the actual data, but a pointer to the data that has been allocated in heap memory. And when we now look at s2, s2 also holds a pointer to data that has been allocated in heap memory. The difference is that the actual data in heap memory that s1 is pointing to has been copied in heap memory. So S1 and S2 point to different locations, even if the data is the same, right? And that's different from what we saw here. As you can see, S1 and S2 point to the same location in heap memory. I hope you get the concept. So let's now see how ownership works in functions. As you can see, we have here a variable s, which we initialized with a string type. So over here, s comes into scope. And in this case, s will be the owner of this data. Then over here, we are calling the takes ownership function, providing it an argument of s. So s value moves into the function and so is no longer valid here. meaning the function takes ownership is now the owner of S. So as you can see, this function over here takes an argument of string type, and it just prints out the provided string. So as you can see, some string comes into scope, and some string over here is the string we have provided as an argument. Then we print it out, and over here some string goes out of scope and drop is called. The backing memory is freed, meaning when we reach the end of the scope, some string will get deallocated in heap memory. So after this point over here, S can't be used in this main function over here, because again the ownership has been moved from variable S into the takes ownership function. Now over here we have another initialized variable X with a value of 5. Now 5 would be of type i32, the default integer type, meaning 5 is a type that lives on the stack. It's pushed to the stack and not allocated on the heap. And that means when we call this function makes copy and provide it X over here, then we provide this function a copy of the value and not the actual value itself. So we provide here a copy of the value 5, right? And then over here we just print out this number. Then here some integer goes out of scope, nothing special happens. So the argument we are providing here goes out of scope, but X over here is still valid, because again we have just provided a copy, because this is a type that is living on the stack memory. So let's see this example. Over here we are calling the gives ownership function. Now when we look at this function over here, we are inside the function code block initializing a variable with a string value over here, and then we are just returning this string, and that means that S1 will then hold the returned string, namely this yours string over here. So S1 will be the owner of the returned string type. Over here we are initializing S2 with a string over here. That means S2 is the owner of the string. Then we are calling here the function takes and gives back with an argument of S2, meaning takes and gives back will become the owner of this data. And that also means that after calling this function, we can't use the variable S2 because it has been dropped. Now when we look at the function takes and gives back, it takes an argument of type string, which we are providing here, and then it just again returns the string, right? So S3 will then hold the return string. Basically S3 then became the owner of this data, right? So we have transferred ownership from S2 to this function takes and gives back, and then from this function to S3. And then at the end of the main scope, S3 goes out of scope and is dropped. S2 was moved, we've seen that, we have moved it inside the function, so nothing happens. S1 goes out of scope and is dropped. So the variable S1 also gets dropped because it is the owner of this string type returned from this function. So you're now asking, why do I even care about all this stuff? In other languages, I don't have to worry about all of this, and this seems rather complicating a simple issue, right? Now, The main point of all of this is that ownership prevents memory safety issues. So by this concept of ownership, you are preventing dangling pointers that point to nowhere or some garbage values. Double free, which is trying to free memory that has already been freed. Or memory leaks, not freeing memory that should have been freed. And if you're coming from C or C++, you know exactly what I'm talking about here. So, before stepping into borrowing, we will do some exercises concerning ownership. So let's see, number 1, use as many approaches as you can to make it work. So, as you can see, the variable x over here has been initialized with a string. Then we are assigning x to y, so y also should hold a string. The problem over here is that we try to access x over here after it has been assigned to y. Now we have seen in the example that x will get dropped after we are assigning it to another variable. Right? So we can't access x. But what we can do is telling the compiler that we want a deep copy of the data that x is holding, and we are using for that the clone method. And then we can access both of these variables because the data has been cloned and x still lives on. Number 2, don't modify code in main. Again, s1 has been initialized with a string. And then we are calling here take ownership and providing it an argument s2. As you can see, the function take ownership expects an argument of type string and it just prints out the provided argument. Now we are then assigning the return value of this function to this variable. The problem here is that this function actually doesn't return anything. So this would hold a unit type, right? Now if we want to return the argument over here after printing and using it, we can just return it like that. And if you return something from a function, you have to annotate the return type, and that would be string, right? Because we are taking here in the string and then we are returning it back. That means s2 will then hold the returned string. And then we can print out s2. And notice s1 can't be used after we have called this function with an argument of s1 because the ownership has been transferred to this function. So meaning s1 is holding the data over here, which means it's the owner. Then we call this function and provide it s1, meaning this function over here becomes the owner, and then we are assigning the return value to s2. So that means s2 over here will be the owner of the data in the end. Number 3, we are here calling the function give ownership. And as you can see, inside the function we are initializing a variable s which holds a string. And we call here the into bytes method on s. Now let me show you that in the documentation. So this is the into bytes method. Now as you can see, converts a string into a byte vector. So if we have a string over here and we call the into bytes method, then we will get the string over here, but represented as a vector of bytes. Okay. And the important thing here is that this consumes this string, meaning s over here will get consumed, and that means s can't be used after this point. Now what we can do as an alternative, we can use as bytes, and as bytes just takes references, and references will be our next topic, so don't worry too much about it right now. But when we call the as bytes method over here, then the owner will remain the same, right? It doesn't consume the data. So what we can do over here is calling the as bytes method, and that means s remains the owner of this data, and we can return it then, and that means s over here will be then the owner of the returned value, and then we just print out s. Fix the error without removing code line. Again, we are initializing s with a string. Then we are calling the print_stir function with an argument s. And all we do is we then print out the string. But over here again, we try to access s. And that would be a compiler error, because we are over here providing s as an argument to this function over here, meaning this function will become the owner of the data s is holding, and that means s is not accessible anymore. What we can do over here is we can call the clone method. Meaning we are providing this function over here a copy of this data. So this data will get copied in heap memory, and that means s will still be valid. Don't use clone, use copy instead. So over here we have a tuple. Now this tuple holds two integers, a unit type and a string. Now let me annotate that. We annotate tuples like that, and we have to define each type of every value this tuple holds. So we have two i32 integers, one unit type and one string. Now over here we are calling the clone method and assign it to y. So y should actually hold the same values, alright? And because we have called the clone method, we can use both variables without a problem. Now it says don't use clone, so we can't use clone over here. Now my solution to this would be, if you take a look at the types this tuple is holding, then we see that most of the types over here are actually on the stack memory, meaning they are of known fixed size, right? So integers and i32 would be of size 32 bits, right? A unit type would be of 0 bits. The only problem arises here because we have a string. Now a string is a heap allocated type, meaning its size is not known at compile time. Now what we can do over here is we can use a string literal. Now we will cover the difference between strings and string literals, but for now a string literal is a string that is hard-coded into the binary itself, into the program. So it is immutable, which means that the size is known at compile time. So all the types the tuple holds are of known fixed size at compile time. So over here we can do the same. And what's the reason we have been doing this? Because we know that a type that lives in stack memory, meaning its fixed size, will get copied implicitly. Now this tuple only holds fixed sized types, meaning the tuple itself is fixed size. And that means X over here will get copied implicitly by the compiler. All right? Mutability can be changed when ownership is transferred. As you can see, we are here initializing S with a string. Then modify this line only. We are here assigning S to S1. Now over here, as you can see, we are modifying the string that S1 is holding. And remember, when we assign S to S1, S1 will become the owner of this data, meaning S will get dropped. So we are then trying to mutate S1, and we are pushing to it the string world. Now remember that a variable is immutable in its nature, so we have to use the mute keyword over here to denote that S1 should be mutable. And that means that if the ownership has been transferred to another variable, we can change its mutability, right? Even if S was immutable, we can make S1 mutable without problem, because S1 is now the owner of the data. Now over here, as you can see, we are initializing a variable X with a boxed integer type. Now box allows you to allocate directly on the heap. As you know, this is an i32, and i32s normally live in stack memory. When we use this over here, box new, and we box this i32, it means it gets allocated on the heap. And that means X will then hold a pointer to the data that was allocated in heap memory. So the type annotation here would be box, and this box holds an i32. And X then basically holds a pointer. Now over here, implement this line, don't change other lines. Now, as you can see, we have over here to declare Y. Now Y gets dereferenced, and that means we have over here to get back a pointer. So we can do basically the same thing like we did before. We can use box new, and let's do 1, for example. So the variable 1 will hold a box with a type of i32. And as I've said, we allocate this integer on heap memory, meaning we get back a pointer, and the pointer is a memory address to the location where this data has been allocated. Now, because Y holds a memory address, we can't assign a value, an integer value, directly to Y, because Y is just holding an address and not an i32 type. Because remember, we can just assign a value to a variable if both of them are of same type. Now, as you can see, Y holds a type of box i32, which is not the same type. That means we have to dereference, and we are dereferencing using this star operator. And this star operator means we go to the location of Y, because Y is holding a memory address, and we want to access the value right? So we want to access this integer that has been allocated on the heap. And that means we can assign a new value to y, but we have to use the star operator. And again, over here you can see it even better. This would be equal, right? Because x is pointing to a location in memory which holds an integer value of 5. Now, if we would omit this star operator, this would not match because x would hold something like that. Right? A memory address. Now this memory address and the integer 5 would not be equal. But the star operator basically says, go to this address and give me back the value that is stored at that address, which would be 5. And of course, we have to make this variable over here mutable, right? Because we are here mutating y. Partial move. Within the destructuring of a single variable, both by move and by reference pattern binding can be used at the same time. Doing this will result in a partial move of the variable, which means that parts of the variable will be moved while other parts stay. In such a case, the parent variable cannot be used afterwards as a whole. However, the parts that are only referenced and not moved can still be used. So over here we have a lot of stuff we didn't cover yet, and I will try my best to explain it, but if you don't get it 100%, it's no problem, okay? We will go into greater detail on each of these structures and types. So as you can see over here, we have a struct person. Now a struct is basically a custom type. We can create our own types in Rust. And a struct basically is a template. We are saying here, as you can see, the struct holds two members. One name, which is of type string, and one age, which is of type boxed U8. Okay, a heap allocated unsigned 8-bit integer. Then we have to instantiate this person struct, meaning we are using this template and create basically a concrete value of that. So we are providing here for the name member a string like it's defined here, and for the age we provide a boxed value of 20. Now this person variable will then hold a type of person, right? This is now our own custom defined type. Now name is moved out of person, but age is referenced. So over here we are destructuring the person instance over here. And we do that very similar to tuples we have seen. We use the let keyword, the name of the struct, and then we destructure the fields. So the person instance over here will get destructured, meaning person name will get put into the name variable, and the age member here will get put inside this age variable. Now notice something, we are here using the ref keyword, meaning the age variable will only take a reference of this data and not the actual data itself. But name will get moved inside this variable. So the name variable here will be the owner of this string, right? And that means that person is not the owner of this string anymore. It has been when instantiating this struct, but it is not anymore. Then, as you can see, we are printing out these variables, but we then can't use the person instance, right? Because the person instance is not the full owner of all the members inside it. And also we can't access person.name. This is how you would access normally a member in a struct, person dot and then the member, in this case name. But we can access person.h because the person instance over here is still the owner of h, because again we have destructured it and the variable h only took a reference. Again, if you don't understand 100%, it's fine. Okay, we haven't covered a lot of the stuff going on here, and I even think this is not a good example right now, but yeah. So exercise 8. As you can see, we have here a tuple holding two string types. Now we are assigning the first element of the tuple, and by the way, tuples are also zero index like arrays, and we can access the indexes like this: the name of the variable and then dot and the index we want to access, in this case the first one. That means that underscore s will hold a type of string, right? Namely this over here. And that means the ownership of this string data here got transferred to this variable. So underscore s is now the owner of this data. Meaning we can't access t again, because t is not the owner anymore of all the values it contains in the tuple, right? So we can't use it again, but we could still use t at index 1, because this over here is still owned by t, because only the first element has been moved out. And over here again a tuple with two strings. So fill the blanks. As you can see, what we want here is destructuring the tuple, and we want to initialize these two variables, s1 and s2. And remember, when we destructure it, we have a syntax like that. Now over here, as you can see, when we are destructuring this tuple, both of the values it is holding will get transferred to these variables. So s1 will be the owner of this string and s2 will be the owner of this string, meaning t doesn't own any values after this point. But what we can do, because we want to access t again over here, we can call the clone method, as you've seen. Meaning s1 and s2 only hold copies of these strings and not the actual values. And that means that t will still be accessible, and t is still the owner of all the values inside the tuple. Alright, see you in the next topic. So let's look at borrowing. Borrowing is a way of temporarily access data without taking ownership of it. When borrowing, you're taking a reference, a pointer to the data and not the data itself. Its goal is to prevent dangling pointers and data races. Data can be borrowed immutably and mutably, and there are certain rules when borrowing which we have to comply with, otherwise the program won't compile. Let's look at these rules. The first rule states that at any given time you can have either one mutable reference or any number of immutable references. But you cannot have both. You either have one mutable reference or any number of immutable references. And the second is references must always be valid. So let's see an example of a reference. Over here we are initializing s1 with a string. Then we call the calculate length function. And as you can see, we are here passing a reference to s1. And this is indicated by this ampersand symbol over here. So then let's see the calculate length function. As you can see, the argument should be of type reference to a string, which we did provide, right? It's a reference, this ampersand, to s1, which is of type string. And then all this function does, it will call the len method, which will return the length of the string, and it returns it. Now notice that the return type will be of type usize. And then this len variable over here will hold the length of this string, and the type annotation would be usize, right? The return value of this function. And then we just print out s1 and length. And notice something over here. We can use s1 because s1 over here stays the owner of the data. We have just provided here a reference to s1 and not s1 itself. So let's see how that looks. As you can see, we have s1. Now again, it's very important that you understand that the variable s1 over here doesn't hold the actual data, but a pointer to the data which will get allocated to the heap memory. So when we allocate to the heap, we will get back a pointer which s1 is holding alongside with other metadata. Now, because over here we are providing s1 as a reference, that means the variable s from this function will then be another pointer which points to the s1 variable. So s points to s1 and s1 points to the heap allocated data. And that means that s1 over here remains the owner of the string. Let's see mutable references. As you can see, we initialize a string and assign it to s. Now then we call the change function with a mutable reference, and notice that you have to annotate that you want the reference to be mutable. This is important and it has to be explicitly stated so that the rules are set in place, because remember, you can only have one single mutable reference at a time. And then this change function over here, as you can see in the function signature, it takes an argument of type mutable reference to string, which we are providing, right? We are providing a mutable reference to s, which holds a string. And then we can manipulate the string. Now again, very important, s remains the owner of this data. Even though we are manipulating it in this function over here, s remains the owner because we are here dealing with references. So let's look at some examples just to strengthen the knowledge of this concept. As you can see, we here initialize s with a string, and then we have here two mutable references to s, and we assign it to r1 and r2. Now this would fail. This program doesn't compile. Now this would violate the first rule of borrowing, which says that we can only have one mutable reference to the same data at a time. But what we can actually do, let's see this program. As you can see, again, we have a variable s which holds a string. And notice over here we have an inner scope. So in this scope, R1 will hold a mutable reference to s. Now because at the end of the scope, R1 will go out of scope, meaning it will be dropped, we can then again pass a mutable reference to R2. So this program will compile. So over here again initializing s with a string. Here we have two immutable references to s. Now up to this point no problem, because the first rule states that we can have any number of immutable references. The problem is over here, because we are then assigning a mutable reference to s to R3. This is a problem, because this would violate the first rule of borrowing, which says that we can either have any number of immutable references or one single mutable reference. But we can't have both of them, immutable and mutable references, at the same time. Now over here, as you can see, we have the exactly same program, but as you can see, we are here having two immutable references assigned to R1 and R2, and then we just print it out. Now after this point over here, the variables R1 and R2 won't be used in the entire program, and that means that we can assign then a mutable reference to R3. It's important to notice here that again we don't use R1 and R2 after this point. So it's allowed to have a mutable reference over here. While over here, as you can see, we are trying to access all of them at once. This would cause a problem. Now I've showed you some of the reasons why the compiler is so strict, and one of them was dangling references. So let's see what a dangling reference is. As you can see over here, we are calling a function dangle. Now in dangle we are initializing a variable with a string type, and then we are returning over here a reference to this string. As you can see in the return type, it is a reference to a string. Now the problem here is that when the function returns, this variable over here will hold a reference to this string, right? And s over here will get out of scope at the end of this function scope here, and that means this variable over here will point to something that has already been dropped or deleted, so it points to a garbage value, right? And Rust won't allow you to compile a program like that, because this will violate the second rule, which states that references must always be valid. Very important. And to avoid that, we can change this dangle function over here and just returning the string itself, right? So reference to nothing would then be the owner of the string. But returning a reference to something that has been declared inside the function scope is a bad idea. Alright, let's do some exercises. As you can see, we have here a variable holding an i32 value. Then over here fill the blank, and we have to complete this p assignment over here. Now let me see over here, the memory address of x is, and we are providing p. So we want to print out here the memory address. And by the way, this is the notation if we pass here a pointer, that it actually outputs the address of the memory location. that P is holding. So over here what we want to do is we want a reference to X. Now as I've told you, P will then be of type reference to an I32, right? Because X is holding an I32 type. Now a reference to an I32 is basically a pointer to a location in memory that points to this data over here. So P here holds a memory address. We will see that when we execute this program. As you can see, the memory address of X is this. So this memory address is where the value 5 is stored in memory. And we are accessing that using a pointer over here. Again, a pointer is just a normal variable which holds a memory address. In this case, the memory address of X, right? So this is a reference to X. Over here, again, we have variable X holding I32 type and a reference to X, which is a reference to an I32 value. Modify this line. Again, we compare here Y with 5. Now, Y doesn't actually hold the value 5, it holds a memory address. Now, to access the data at which this Y pointer here will point to, we have to dereference, and we do that with the dereference operator, like that. That means go to the location of Y and give me the value, right? So when we go to the location where X is stored, for example at this memory address, we want to get the value that is stored at that address. And we are using here the star operator just to access the value. So over here we initialize a variable holding a string type. Then we are calling the function borrow object. And as you can see, the borrow object function expects an argument of type reference to a string. But what we are here providing is a string, right? We are providing S, which is of type string. Now we want here to pass a reference to S, meaning a reference to string. In this case, we are complying with the function signature. Over here again, variable S holding a string. Then we call pushStir function over here. Now again, we have to always take care of the function signature. What is expected? So as you can see, the argument should be of type mutable reference to a string. So we have to pass here a mutable reference to S, where S is holding a string, right? Number 5, again, here having a string. And as you can see over here, we are mutating P. So that means we want to have a mutable reference to S. As you can see, P will then hold a mutable reference to a string type, right? And then we can mutate the string that P is holding. And again, because we are here having a reference, S will remain the owner of the data, meaning we still can use S even after this assignment over here. Ref can be used to take references to a value similar to ampersand. As you can see, we have here a variable holding a char. And this over here would be a variable which holds a reference to HR, right? A reference to C. Now fill the blank, don't change other code. Now instead of here using the ampersand symbol, we can use the ref keyword, and it's exactly the same. Actually, they are very similar. There are some minor differences in pattern matching, but we will come to that. So when we dereference R1 and R2, then they should hold the same data, right? And over here, check the equality of the two address strings. So we have here a function getAddress which gets called with R1 and R2. Now all this function over here does is it takes a reference to HR as an argument, and it will then put it inside this format macro. Now this format macro over here is the same as the print line macro, with the difference that the print line will print to the standard output while format will return a string, right? So we take this argument and then we will return here the memory address of this reference. Now in this case, R1 and R2 should hold actually the same memory address, right? Because they are pointing to the same data, in this case C. So R1 is pointing to C and R2 is pointing to C. All right, so let's see. And this is compiling. Borrowing rules. Remove something to make it work, don't remove a whole line. Again, here having a mutable variable s, which holds a string. Then we have two mutable references to s, and this actually would fail to compile. Because again, we can only have one mutable reference at a time. So to solve this, as you can see over here, we are just printing out R1 and R2. So these references over here don't need to be mutable, right? Because it's sufficient that we have a read-only reference to S. And again, the rule states that we can have as many immutable references as we want. So this is compiling, and also just to show you, when dealing with references over here, as you can see, S is still valid, right? Error, borrow an immutable object as mutable. Fix the error by modifying this line. As you can see, we have here a string, and we call here borrow object with a mutable reference to S. So the problem over here is that we can't pass a mutable reference to something which is immutable. So we have to make this variable over here mutable, and then we can provide here a mutable reference to this variable. But the other way around, it's no problem. Okay, borrow a mutable object as immutable. So this code has no errors. As you can see, we have here a string, and we are passing to the borrow object an immutable reference, right? Now, this would actually compile because, as you can see, the function signature states it should be an immutable reference. Even though S itself is mutable, we can still pass it as an immutable reference. This would compile without problems. And then over here you can see we are even mutating s because it's mutable. Comment one line to make it work. We have here a string and we have a mutable reference to s, right? So this would be the type annotation, mutable reference to a string type. Now we are then mutating R1, and over here we again have a mutable reference to s. And then we are modifying R2. The problem here is that you know the rule that we can only have one mutable reference at a time. But as you can see, R1 over here gets used again. So this should remain valid, but we can't have two valid mutable references at the same time. So if I comment this out, then this program should compile because we are not using R1 after this point, meaning we can have another mutable reference. And even if I print out here R2, this should also compile, because over here the only valid mutable reference to s would be R2, because we are not using R1 after this point. So over here again we have a string and we have two mutable references to s. Now if we would run that, it would actually compile. As you can see, the program compiles. Even though we have two mutable references to s, but we are not using any one of these in the program. But over here it says add one line below to make a compiler error. Cannot borrow s as mutable more than once at a time. You can't use R1 and R2 at the same time. So let's use both of them over here to force this compiler error. And as you can see, this would be the compiler error we are expecting. Cannot borrow s as mutable more than once at a time. And over here you can see really the Rust compiler is one of the best compilers I've ever seen, because it provides you with really useful compiler messages. Alright, see you in the next topic. So we have now reached the topic of compound types. Now a compound type is a type which is made up of other types. For example, a string is made up of characters, so it's considered a compound type. Now we have in Rust two types of strings. We have string with a capital S, string like that, and we have string slices. Now if I say string, I will always refer to this type. Otherwise I will say string slice. So a string is a heap allocated string type that owns its contents and is mutable. We have seen that a string is allocated in heap memory. A string slice is an immutable sequence of UTF-8 bytes in memory. It does not own the underlying data and is immutable. So think of string slice as a view on a sequence of characters stored as UTF-8 bytes in memory. It's basically just read only. So use string slice if you just want to view a string. And a string slice is more lightweight and efficient than string. And use string if you need to own the data and be able to mutate it. Then we have string literals. A string literal is a sequence of characters enclosed in double quotes. Its fixed size, compile time known sequence of UTF-8 bytes. The type is reference to static string, which indicates the data is stored in static storage, meaning it is valid throughout the entire lifetime of the program. The data is hard-coded into the executable and stored in read-only memory, meaning they are immutable. So let's now see an example of a string slice, and I'm seeing my head is in the way here. Let's do it like that. So let's see. Over here we are initializing s with a string. Now again, I repeat myself, I know, but this is very important. S doesn't hold the actual data. It holds a pointer which points to the data that is allocated in heap memory. So S will have a pointer alongside other metadata that will point to the first character of the string. And let's now consider this world variable here. So we are taking a reference to S, meaning S will remain the owner of the heap allocated string. So we are taking a reference to S and providing here an offset from 6 to 11. Now I hope you remember, in a range this would be excluded, so it would be from 6 to 10. So when we look at the world variable, we see that it has a pointer and a length. Now this length over here is actually false. I'm sorry for that. This should be the length of the string slice. In this case, 1, 2, 3, 4, 5. So this pointer points to the offset of the string we have provided. So it points to index 6 and it goes to 10, because again 11 is excluded. So this world here will hold a string slice of this word, right? So the string slice world points to a sequence of characters stored on the heap. This is basically just a view into a heap allocated string, and that's why it's immutable. Alright, the type of string literal hello world is &stir. For example, let s string slice equals hello world. Now this would be a string literal, right? Because we are hard coding it into the executable. And a string literal is also considered a string slice because it's also immutable. And it's basically just a reference to the static memory this string gets stored in. So stir and string slice. We can't use stir type in normal ways, but we can use reference to stir. Fix error without adding new line. As you can see, this would over here be a string literal. We are hard coding this string into the executable, into the program itself. So again, we can't use stir as a type, but we can use a reference to a stir, right? We can only use stir by boxing it. Ampersand can be used to convert box stir to string slice. Now fix the error with at least two solutions. As you can see over here, we have a string literal, a string hard-coded into the program itself. Then we call the into method. We will cover that later, but basically into will convert a type into the type we are annotating here. So this string literal will be put into a box, meaning it will be heap allocated. Then we are calling this greetings function with an argument s. And as you can see, s, this argument over here, has to be of string slice. So what we can do over here to convert this box into a string slice is passing a reference to this box. As you can see, this is compiling, but we even can just omit all of this, right? This would hold a string slice, and we then just pass s. Notice that we don't have to pass a reference to s because s is already the type we need. String type is defined in standard library and stored as a vector of bytes, vec, but guaranteed to always be a valid UTF-8 sequence. String is heap allocated, growable, and not null terminated. So let's see, we want to initialize here s with a string, right? Then we are mutating this string over here and mutate it again. Now over here we are pushing to it a string literal, and over here we are pushing to it a single char. Now if you push a single char, you just use the push method, not the push stir method. And in the end, s should hold hello world. Now we can initialize here an empty string like that. This is now an empty string type. Now why are we using this type over here and not string slice? Like so, for example. Why aren't we doing it like that? Because remember, a string slice and string literals are immutable. They are just references to some string data in the memory. So we have to use string here. So we are here initiating an empty string, and then we are mutating it and push to it hello world and this exclamation mark. This compiles. Let's output the string. As you can see, the string over here has been mutated, and that's the whole point of using this string type over here. They can be mutated, they can grow and shrink and so on. So let's see exercise 4. Fix all errors without adding new line. As you can see over here, we have initialized a variable with a string. Then we are mutating this string over here, which means we have to make this variable s here mutable. So we are pushing a single character, this comma, and then we are pushing another string like that. And we can even push to the string by using this notation here, even though I don't like it, but it's also possible. But over here we have to pass it a string literal, because this is defined in this standard library. Alright, let's see. And of course over here, sorry, we have to use the push stir method. As you can see, this is compiling. So again, we are pushing a single character. Then we are using here the push stir method, pushing a string literal, and we can also mutate strings like that. Replace can be used to replace substring. Again, we have here a string, and we then can replace some elements inside the string. So we provide as first argument the element we want to replace, in this case dogs, and it should be replaced with cats. So S1 should then hold I like cats. Now again, replace will mutate the string, meaning the S should be mutable. More string methods can be found under string module. So number 6, you can only concat a string with a string slice, and strings ownership can be moved to another variable. So we have here S1 holding a string and S2 also holding a string. Now as you can see, we want to concatenate these two strings, and we can use the plus operator for that. Now in the Rust documentation it says that the first argument should be of type string, while all other arguments must be string slices. So we have to convert S2 over here to a string slice. Now there are two possibilities. The first one is using the stir method like that. So this over here will then be considered as a string slice. So we have converted a string to a string slice, right? But the result of this concatenation will be of type string. It's important to remember that. And S3 should then hold these concatenated strings. Now, because S1 over here has been moved inside S3, we can't use S1 anymore, because S3 has become the owner of this data. So let's instead print out S3. And as you can see, this is compiling. Now there is an easier approach to that. We can convert a string to a string slice by just providing a reference to a string. So a reference to a string can be inferred to a string slice like that. String slice and string. Opposite to the seldom using of stir, string slice and string are used everywhere. String slice can be converted to string in two ways. So we have covered that. Fix error with at least two solutions. So over here we have a string slice, right? Now we call the greetings function over here with an argument of s. Now s should actually be of type string. So we can convert that by calling this toString method like that. So we have converted here a string slice to a string. All right. The second way would be doing it like that, string from and then providing s. As you can see, this is compiling, and there are other ways, for example toOwned, even though I think this is not used that much because it's more general, but it's also possible. Alright, we can use string from or toString to convert a string slice to a string. Use two approaches to fix the error and without adding a new line. As you can see, we have here a string literal that has been put into a string. So this variable over here will hold a type of string. Now to convert this s over here into a string slice, because this is the type annotation of this variable, we can, as I did before, we can pass s as a reference. And again, a reference to a string will be inferred to a string slice. And again, we can use stir, for example. It would be the same. String escapes. You can use escapes to write bytes by their hexadecimal values. Fill the blank below to show I'm writing Rust. So as you can see, we can escape certain values and they will then be converted to ASCII characters. For example, this would be the hexadecimal representation of the ASCII value of S, right? So if we want to write Rust here, then the next character to S would be T. So we would write X74 like that. And you can check this out over here. There are a lot of examples where you can just escape using the backslash. Now using 2 backslashes here will print out these literal characters. So the output will be \x3f, okay? Because we are basically escaping this backslash. Alright, and over here we have raw string, and a raw string is a string in which there are no escapes. So everything is printed literally as it is written. So the output of this, let me run that. So the output of this would be \x3f. It won't be converted to an ASCII character. So let's see, string index. You can't use index to access a char in a string, but you can use slice, reference to a S1 for example, and the offset. So let's see, we have here a string, and now we want to access the first character. Now in most programming languages this would be possible, but in Rust you have to use string slices, meaning you take a reference to S1 and then provide the offset. If we want to only access the first character, we would provide an offset in form of a range from 0 to 1. Now again, in a range this would be excluded, meaning we only access this first element. So the return type will then be a string slice. Notice something here. When we assert age, we would have a string of age and not a character. Even though we are here only accessing a character, we are accessing it using the string slice notation over here. So remember, a string slice is just a view into a heap allocated string, right? So we are just looking what is at this location. In this case, we just want to access the first location over here, right? Modify this line to fix the error. Tips. This would take 3 bytes in UTF-8 format. And that's right, we have said that a character in Rust is of size 4 bytes. Now a character in a string is a little bit different. So if it is an ASCII character, then it will usually take 1 byte. And these Unicode characters can take 3 bytes, or I guess some of them even 4 bytes. Alright, so we want to have in H1 only this character. So again, we are taking a reference to S1 and providing an offset. So H would be at index 0, I would be at index 1, this comma index 2, and then this will be index 3. Now this takes up 3 bytes, so we have to provide here an offset from 3 to 6. Remember, 6 is excluded, so it goes from 3 to 5. 3, 4, 5. 3 bytes. Let me output that. As you can see, this would be the output. And again, this is just a view into a heap allocated string, right? Operate on UTF-8 string. Fill the blank to print each character in this string. So over here there is a method called chars. Now chars will put this sequence of characters into an iterator, meaning we can then iterate over it using a for loop, for example. And that means C will then be in each iteration one of these characters, and we will then just print out C. As you can see, in each iteration we are printing out a single character. Alright, that's it. See you in the next topic. So we'll now cover arrays. Now an array is a fixed size collection of elements of the same data type stored as contiguous block in stack memory. Now it's stored in stack memory because its size is known at compile time. The signature of an array is like that, you can see over here, which indicates that the length is fixed at compile time. Arrays can neither grow nor shrink. They must retain their size. So let's see. The type of array is like this. As you can see, array's length is part of their type signature. So their length must be known at compile time. For example, you can't initialize an array like below. This would not be possible. As you can see, we have an initR function which takes an argument of type i32. And then we try over here to initialize an array with the length that is provided as an argument. Now this would be a compiler error because, as we've seen, the size of an array must be known at compile time. If we do it like that, the size of the array would only be known at runtime. This will cause an error because the compiler has no idea of the exact size of the array at compile time. Let's see, fill the blank with proper array type. As you can see, we have here an array with 5 elements. Now what would be the type of these elements? It would be the default integer type, which is i32. So we annotate arrays like that in square brackets. Then we would have the type of the elements and the amount of elements inside of the array, which is 5. Modify the code below to make it work. So we can call the len method on an array, and it will then provide the length of the array. So in this case, this would be 5, right? Because there are 5 elements inside. Number 2, we can ignore parts of the array type or even the whole type. Let the compiler infer it for us. So we actually don't have to annotate the type, or we can annotate the type but leave, for example, the type annotation here for the compiler to infer. Fill the blank. Arrays are stack allocated. Size of val returns the bytes which an array occupies. A char takes 4 bytes in Rust, Unicode char. So we have seen that before. The size of val will just take an argument and it will output the size in bytes the provided argument occupies in memory. So if we provide the R over here, then we should actually get back 3 times 4 bytes because a character in Rust takes 4 bytes, meaning this array over here would occupy 12 bytes in memory. All elements in an array can be initialized to the same value at once. So as you can see, we have here an array which should hold 100 elements, and each element should hold the number 1, Okay, we are here accessing the first element, and this is the notation for accessing elements in an array. In this case, we access the first element at index 0, and the length would be 100. So instead of typing out 100 times 1, we have a shorthand syntax for that. So we can here first of all provide the element it should hold, in this case 1, and we want it to hold 100 elements of this value over here. Number 4, all elements in an array must be of the same type. So as you can see, because when we annotate an array, we actually have to define the type here. In this case, we want integer types, and we have 3 of them. Now, as you can see, this is a char, and this is not possible. All elements inside an array must be of the same type. Indexing starts at 0. So over here we have an array of characters. Let's annotate that. And there are 3 elements inside it. And now we want to access the first element, right? We want this variable over here to hold the first element. Now again, arrays are 0 indexed, meaning we access it using this notation here and provide it a value of 0. Out of bounds indexing causes panic. So over here we have an array which holds 2 strings, and we want to access the first element, right? Now we can use this notation over here like we did before, or we could use the get method. The difference is that get will return an option type. We will cover that in a later episode, but it's generally safer than using this notation. And this is especially true if you're accessing elements at runtime, okay? So we can use this notation, or we could use this notation. Now over here this would panic because this array has only 2 elements, meaning indexes 0 and 1. So let's access here index 1. And this compiles. So let's see slices. A slice is a reference to a contiguous sequence of elements in a collection. It provides a way to borrow part of a collection without taking ownership of the entire collection. It can be created from arrays, vectors, strings, and other collections implementing the deref trait. So let's see this example of a slice. We have here an array. And then we are over here taking a reference to A and providing an offset. Essentially the same thing we did with string slices, right? A slice is just a view into a collection. And over here we try to access the elements at index 1 to index 2, right? Because 3 would be excluded. So the variable slice will then hold a slice with the elements 2 and 3 in it. Right, let's see. Slices are similar to arrays, but their length is not known at compile time, so you can't use slice directly. Here both this slice over here and stir are slice types, but directly using it will cause errors. you have to use the reference of the slice instead. So because these two slices over here, their sizes are not known at compile time, we have to use a pointer to that, right? And we have seen that in the example of string slices. So we use this syntax over here. Fix the errors, don't add new lines. As you can see, we are holding here an array. Let's annotate the type like that. And this is an array of 3 i32 integers. Now we want here to get a slice with this offset, meaning from 0 to 1, 0, 1. So again, like we did with a string slice, we want a reference to an array with this specific offset. So we are trying to access 0 to 1 because 2 is excluded, meaning we are accessing here index 0 and 1, the elements 1 and 2. So this slice over here will then hold 1 and 2, right? Now the type annotation here would be like that, because we are holding a reference to this array, right? And this would be the type annotation of a slice. Now over here we have a string literal. Now string literals, as we've seen, always are annotated like that. String literal is hard-coded into the program's binary, and that's why we can access it using a reference to this string literal over here, which is in the binary itself. All right. A slice reference is a two-word object. For simplicity reasons, from now on we will use slice instead of slice reference. The first word is a pointer to the data, and the second word is the length of the slice. The word size is the same as usize, determined by the processor architecture. For example, 64 bits on an x86-64. Slices can be used to borrow a section of an array and have the type signature like this, where T over here stands for the type. As you can see, we have here an array with 3 characters. Now we want to have a slice of this array with the first 2 elements, these 2 elements. And this is shorthand notation. Instead of writing it like that, we can just omit the 0. Alright, so we are accessing 0, 1 and 2 is excluded. So the slice variable should hold a slice with these elements. The type annotation over here would be reference to char. Okay. Modify 8 to make it work. Tips slice reference is not an array. If it is an array, then assert will be passed. Each of the 2 characters, this and this, occupies 4 bytes. 2 times 4, 8. Now, because the slice variable over here doesn't actually hold an array but a slice, we are here actually holding a pointer, right? Because this is a reference to this array. And that means we have seen over here a slice reference is a 2-word object, meaning the pointer and the length field will both occupy sizes of type usize. And usize, if you're on a 64-bit computer, it means usize will be of size 8 bytes or 64 bits. And that's why a slice holds 16 bytes. right? If we would pass the array here, we would have, if this slice would have been an array, then 8 would actually pass, because we would have 2 characters. Each character is 4 bytes, meaning 8 bytes. But because we have a slice which holds a pointer and a length, both of type usize, we have 16. So over here we have an array of 5 integers of type i32. Fill the blanks to make the code work. As you can see, we want the slice variable to hold a slice of these elements. So let's first annotate the type actually. So the slice variable over here should hold a slice of i32 elements, right? So we are taking a reference to the array and provide it an offset. We want to go from this to this, meaning index 0, 1. We are starting at 1 and we go up to 0, 1, 2, 3, 4. And I choose 4 here because 4 is excluded. So we will go from 0, 1, 2, 3 to index 3. String slices. And we have covered that already, but let's do some exercises for repetition. Now over here we have a string and we take over here a string slice, meaning we take only the first 2 characters. Like that. Or let me write it like that, right? We take the first 2 characters. Fill the blank to make the code work. Don't use 0 to 2 again. So over here we have a second variable which should hold a string slice, and they should actually hold the same elements. As you can see over here, we are here asserting that slice 1 and slice 2 are the same. So instead of using this syntax over here, as we've seen before, we can use like that. We can omit the 0. Over here we have a string literal. Again, a string literal is hard-coded into the binary, and this would be the type annotation. Modify this line to make the code work. As you can see, we want slice over here to hold a string slice with only this character. So let's annotate the type. This would be a string slice. And because this Unicode character over here takes 3 bytes, we have to provide an offset here of 3, meaning 0, 1, 2, right? 3 bytes. Alright, last one, number 6. A reference to a string can be implicitly converted into a string slice. Now over here we initialize a variable s which holds a string. Here reference to s is reference to string type, but first word needs a string slice, as you can see over here. It works because reference to string can be implicitly converted to string slice. So as you can see over here, we are calling the first word function, which takes as an argument a type of string slice. And this would actually work because we are here providing a reference to s, which means this over here is a reference to a string, right? And a reference to a string can be converted to a string slice implicitly by the compiler. So then this function over here will take a reference of s and provides an offset from 0 to 1, where 1 is excluded, so we just take the first element. And it returns this as a string slice. That means that the return value of this function will be assigned to the word variable. Then over here we are calling the clear method on s, which means the string will then be empty. Clear will just remove every content in the string. The string itself will still remain in memory with the same capacity, and s also is valid, so it's different from drop, but it will empty the string essentially. So we will then have over here an empty string. The problem over here is that clear takes a mutable reference to self. And that's a problem because over here we have a reference which is immutable to s, and we have over here a mutable reference to s. Now the problem arises because we are here using the immutable reference. So if we would delete that and put it over here, then after this point the word variable over here, which holds an immutable reference, is not used anymore, and so we can use this clear method. And this is compiling, and as you can see we just get the first element. Alright, see you in the next topic. Now we will cover tuples. We have seen some tuples before in some exercises, but now we will go into greater detail. So a tuple is a way to store related pieces of information in a single variable. And it's essentially a collection of values of different types grouped together as a single compound value. Again, a compound value is a type composed of other types. It's stored as a fixed size contiguous block of memory on the stack, and the signature is parentheses and the types the tuple is holding. Let's see. Elements in a tuple can have different types. Tuple's type signature is like that, where T1, T2 are the types of tuples members. So as you can see, we can hold different types. We have here an U8 and an I16 together in a tuple. Tuples can be tuples members. So we can even nest tuples. So this tuple over here, as you can see, holds an U8 over here and another tuple inside it, which holds an I16 and a U32 integer. Alright. Fill the blanks to make the code work. So over here we have to annotate the type. Now again, the first element over here would be U8. The second one is U16. The third one is an I64. The fourth one would be a string literal. And the last one is a string. Members can be extracted from the tuple using indexing. So as you can see, we have here a tuple. Let's annotate the type. This is how we would annotate a tuple, and it holds 3 string literals. Then we are accessing here the second element. Tuples, remember, are 0 indexed. But in this case it would be M, but we want it to equal sunface, so we have to access the index 2, right? 0, 1, 2. Long tuples cannot be printed, so if a tuple exceeds a certain amount of elements, it is too long to be printed. As you can see, this would be too long. If I delete that over here, so this would work. So we can have up to 12 elements in a tuple to make it printable. If it exceeds 12 elements, you can still use it, but it's not printable. Destructuring tuple with pattern. So let's first annotate the type of this tuple here. We have an I32, the default integer type, then we have a float, which means F64, the default floating point type, and we have a string literal. Fill the blank to make the code work. So over here we want to destructure this tuple, where X holds 1, Y holds hello, and Z holds 6.4. So let's see. We destructure tuples like this using the let keyword and the parentheses. Then the first element should be X, right? Now the second element, 6.4, should be put into Z. And the last element should be destructured into variable Y. Destructure assignments. Over here we are declaring some variables, and then over here we destructure this tuple and we want to put it inside these variables. So because we have already declared these variables, we don't need to declare it once more, so we can omit the let keyword. And then all we do is we destructure it. So 1 should be put inside variable Y. 2 should be put inside variable Z. And 3 should be put inside variable X. Tuples can be used as function arguments and return values. Fill the blank, need a few computations here. So as you can see, we are calling this function sum multiply, and this function over here expects an argument of type tuple, and the tuple should hold 2 integer values. What we do over here is we perform some operations and return it in a tuple, right? So the first operation will be this one, adding the first element of the provided tuple with the second element of the provided tuple, and then we are multiplying the first element of the provided tuple with the second element of the provided tuple, and we return that in a tuple again. So the result of this operation over here will be the first element, and the result of this operation will be the second element. And as you can see, we can return that in a tuple. Now, after returning this tuple, we destructure it. So the first element will be put in X, and the second element will be destructured to the variable Y, where X will hold 5 and Y will hold 6. So we have now to provide here 2 numbers. When we add them together, they will evaluate to 5. If we multiply the 2 numbers, they will evaluate to 6. So this is a little riddle for you, and try to solve it. And the answer would be 2, 3, right? And don't forget to add here parentheses, because we are passing it here a tuple, right? We are not passing two arguments, we are passing one argument, which is a tuple that holds two elements. Very important. So if we add 2 and 3, we will get 5, and if we multiply 2 times 3, we will get 6. And this will be the return type of this tuple over here. Alright, see you in the next topic. Up until now we have been using types that are defined in this standard library, but we can in fact create our own types. And we can do that by using a struct. Now a struct is a compound type allowing to group together values of different types into a named data structure. It's similar to tuples, but each value has a name, so the values can then be accessed through this name. And a struct has to be instantiated with data. Think of it like the struct itself is the template for the instances you create from it. Now let's see how that works. As you can see over here, we have our template. In this case, a struct named user. And the user struct holds various fields. And we can define a field by giving it a name and a type that this field should hold. So in this case, the active field holds a type of Boolean. Username holds a type of string, email string, and sign-in count U64. And then we can instantiate this struct. And we do that by calling the name of the struct, user in this case, and providing for each field a concrete type. And of course, the types have to match the template. Then we are assigning this instance we have created over here to a variable. So this variable will then hold an instance of the user struct. And we can access and even mutate the fields of an instance. So over here, as you can see, we have created an instance and assigned it to the user1 variable. And then we can use this syntax over here to access a field. So in this case, we are even mutating the email field from the instance user1. As you can see, we do that exactly like we would mutate a variable, just assigning it a new value. Now, to mutate, you have to make it explicitly mutable, meaning you use the mute keyword here like you did with variables. And functions can also create instances and return it. So in this case, we have the build user function, which creates an instance of the user struct. And as you can see, again, it's just providing concrete values for each of its fields. And over here, as you can see, this function takes two arguments, email of type string and username of type string. And then it provides it to the username field and to the email field. Now in this case, we are repeating ourselves, as you can see. And we can avoid this by just using this shorthand syntax. So if the name of a field and the name of a variable or argument matches, then we can write it like that. And this just makes it less verbose. And there is also a concept called struct update syntax. So over here we have an instance of the user struct. Now we want to create another instance, but taking some of the values from the fields from user1. As you can see, for example, in this instance, we want the active field to hold the value of user1's active field. So we are accessing user1 and the active field. And as you can see, we are taking everything from this user1 instance except the email. And as I've said, there is a better way to write this, and this would be instantiating a struct like we did before, but just providing the fields that are different from the instance we want to take from it. So for example, over here we say that the email field should hold this value, and the remaining values should be taken from this user1 instance. So this will then create a user instance with all the same values from user1 except the email field. Then we also have tuple structs, and tuple structs are like normal structs but using tuple-like syntax for defining their fields. It's basically a named tuple, and it's instantiated by parentheses instead of curly braces, and its values are accessed using point notation. And then we have unit-like structs, and these are structs without any fields, meaning they don't hold any values. And it's mainly used when working with traits, and this will be covered soon. And that means they don't store any data. Let's solve some exercises. The types of structs. Exercise 1, we must specify concrete values for each of the fields in the struct. As you can see, we have here a person struct holding various fields. And then over here we have a variable age, which holds a value of 30. Now then we are instantiating this person struct and assign it to the variable p, meaning p will then be an instance of the person struct. Now as you can see, we have here the fields and the concrete values. And this would be the shorthand syntax for this, because we have over here a variable matching the name of the field. So we can write it like that. But as you've noticed, we didn't provide the hobby field a concrete value. So when you are instantiating a struct, you have to provide to each field a concrete value. So let's do that. And the variable p will then hold a type of person. Now age, of course, has to match with the template, so this would be an U8. And of course, we use commas here and not semicolons. Alright. Unit struct doesn't have any field. It can be useful when you need to implement a trait on some type, but don't have any data that you want to store in the type itself. So as you can see, this example is using traits, and we have not yet covered that, so I will skip that because this might just be confusing, and we will cover that soon. Number 3. Tuple struct looks similar to tuples. It has added meaning the struct name provides but has no named fields. It's useful when you want to give the whole tuple a name but don't care about the fields' names. So as you can see over here, we have two tuple structs, one color and one point. And they are exactly like tuples, but they are named. Okay, so over here we have 3 integer values in the color tuple struct, and in the point struct the same thing. Now we want to instantiate the point struct over here, and the variable v will then hold an instance of our custom type point. Then we are calling the check color function and provide an argument of v. Now as you can see, the checkColor function takes an argument of type color. But this is not what we want, right? Because we are here passing a variable of type point. So let's change that. And over here we are then destructuring the instance that was passed. So in this case, as you can see, x should hold 0. So let's provide this value over here. Then the p1 field, and as you can see, we are accessing the fields in the tuple struct like we would access elements in a normal tuple using this syntax. So over here we are accessing the second element, and this should hold 127. So that means the last element should hold 255. And as you can see over here, we are destructuring. So the first element over here gets destructured into a variable x. Now the second one over here, we don't need to destructure, right? Because we are accessing it directly using the p instance. And the last one, let's call this z, okay? And by the way, when destructuring and you don't need a value, like for example this one, you just provide it an underscore. Let's see. And of course, when destructuring, we have to provide the name of the struct, in this case point. And this is compiling. Operating on structs. You can make a whole struct mutable when instantiating it, but Rust doesn't allow us to mark only certain fields as mutable. Fill the blank and fix the error without adding, removing new line. Again, we have the person struct, we have here the age variable. Let's annotate that, and we have the p instance. So as you can see, we want to mutate the age field of the p instance. And this is right, but the problem is the p instance is not mutable. So let's make that mutable. And then we can also mutate the name field like that. Using field init shortened syntax to reduce repetitions. So again, we have the person struct, and in main we are just printing out something. And over here we have the build person function. So as you can see, this function takes two arguments, name of type string and age of type U8. And these arguments exactly match the types defined in the template. So then we can over here instantiate a person struct, meaning we can here for the name field provide this argument. And we have seen we can use field init shortened syntax, meaning if the field name matches the name of a variable or an argument, we can skip it like that. Let's see exercise 6. You can create an instance from another instance with struct update syntax. So as you can see, we have here the user struct, and we have seen an example of that in these slides. Then over here we are creating an instance from the user struct. That means the variable u1 will then hold an instance. That means that the variable u1 will then be an instance of the user type. And again, we are just providing each field over here with a concrete value. Then over here, we call the set email function with an argument of the u1 instance. So let's see over here, as you can see in the function signature, the argument must be of type user. And then we want to create over here a new instance. And what we want to achieve here is that we take every field from the U1 instance except for the email field. We want that to be different. So what we can do is providing a concrete value for the email field and then just saying the rest we want to take from the argument provided. And then we are just returning it. So that means U2 will then hold a newly created instance. Print the structs. We can use derive debug to make a struct printable. Fill the blanks to make the code work. So you actually can't print out a struct using the normal print line syntax. We have to, so to be able to print a struct, we have to derive a trait. Again, we will cover traits, but we have to derive that using an attribute. All right, that means that the struct rectangle here implements this debug trait, and that means we can then use debug notation to print it out. So over here, as you can see, we have a variable scale, and then we are creating here a rectangle instance. So we are providing a concrete value for the field width, and this would be 30 times the scale. And we provide a concrete value for height. Now, as you can see, print debug info to standard error and assign the value of 30 times scale to width. Now, this debug macro over here will just print out debug information to the standard error output. And that means over here rect1 will then hold an instance of the type rectangle. And the type annotation for the scale variable over here would be U32, right? Because we are passing this scale variable over here, meaning it should be of type U32. And then again, we are here using the debug macro and printing out rect1. And instead of doing that, we can also use a normal print line statement like you're used to, except that in the placeholder over here, we have to use this notation, and this is called debug notation, meaning any type that implements the debug trait can then be printed. And the difference between debug macro and printline macro, as you can see, printline will print to the standard output, while debug will print to the standard error. And that's why you don't see it over here. You just see the printline output. Now to see that, I will go to the Rust playground. And we can just run this code. And as you can see over here, this would be the debug output. So this debug macro over here prints out the exact thing we are passing to the width field, in this case 60. And this debug macro over here prints out the instance, right? We then have a rectangle with a width of 60 and a height of 50. Basically the same thing that we print out with the print line statement here. Partial move. Within the destructuring of a single variable, both by move and by reference pattern bindings can be used at the same time. Doing this will result in a partial move of the variable, which means that parts of the variable will be moved while other parts stay. In such a case, the parent variable cannot be used afterwards as a whole. However, the parts that are only referenced and not moved can still be used. And I guess we have seen that before, but let's do another exercise. So as you can see, right, we have seen that. Alright, so let's move to the exercises directly because I've already covered that. And I think the exercises are better for understanding. So as you can see, fix the errors to make it work. Over here we have a file struct holding two fields of type string. Then in main we are creating an instance of the file struct, providing it concrete values for each field, meaning f will then hold an instance of the file struct. And over here we are then assigning the name field of the f instance to the underscore name variable. So what would be the type annotation here? It would be string, right? Because f name holds a string. And that means the name variable here will become the owner of this string data. And that is the reason that we then cannot use f as a whole and also not f.name, because a partial move happened. So if a field gets moved out to another owner, then you can't access this field and also not the data structure that is holding this field. So this would fail over here and this would fail. Now to fix that, we can actually access just the name variable here, right? Because this is now the owner of this string. But what we can't do is accessing the whole instance over here. This is not possible. As you can see, this is working. Now, if you actually want to keep f as the owner of all the fields and to print it out like that, and by the way, notice again, when we are outputting a single field, we use the normal notation. If we output the whole instance, then we have to use debug notation, because these fields over here hold types that are defined in the standard library, while this is a custom type we have created. So to make that work, we can also use here the clone method. And as you can see, this is working and we are here printing out the instance. Alright, see you in the next topic. We can also create custom types using enums. Now an enum is a way of defining a type with only one of a possible set of values. We can only access one variant of an enum at a time, and it can hold additional information using tuples. And it's especially useful when using in match statements. Let's see an example of an enum. So we have here the enum IP address, and this enum holds two variants. So in enums we call it variants and not fields like in structs. And each variant over here holds a type using tuple-like syntax. Alright, so an IP address, by the way, can be in either one of two formats. Either it's v4 or v6. And now we will see the difference between enums and structs. So this is how we would instantiate this enum IP address. We are accessing the name of the enum, double colon, and then the name of the variant, in this case v4. then providing it a concrete value. I hope you noticed the difference. In a struct we would have provided concrete values for each field. In an enum we instantiate the enum only with one single variant. Alright? So this home variable will then hold an instance of the IP address enum. And this loopback variable over here will also hold an instance of IP address, but using the variant v6. And by the way, this is the old format of IP addresses and this is the new one. So let's do some exercises. Enums can be created with an explicit discriminator. So enums are enumerated, right? That's why they are called enum. Now, if you don't provide here a value, it will be implicitly starting from 0, this would be 1, and this would be 2. And we can also enumerate them with an explicit discriminator. Okay, so this will then hold 0, this variant will be 1, and this will be 2. And over here you can see C like enum. Now you can't use as a discriminator a floating point value. This is not allowed. But like in C, if you for example would do it like that, we are here providing the discriminator 5, then 1 and 2 implicitly will be 6 and 7, right? Or we could say this should be 9, for example, right? So you can manipulate the enumeration of an enum. So let's see actually. Let me change that back and let me change that to integers. An enum variant can be converted to an integer by the as keyword. So when we take this enum over here and we create an instance, as we've said, as we've seen, calling the name of the enum and the variant, and then we can convert it to an U8, for example, right? And we can do the same thing here, and over here it should be the same thing. And as you can see, this is compiling. Let me print out. As you can see, when we access from the number enum the variant 1, then a 1 will get outputted. Now let's see if I provided a value of 10 over here. But for that I have to comment that out. As you can see, this would then be the discriminator for the 1 variant. Alright, each enum variant can hold its own data. So as you can see, we have here an enum message. Now this enum has different variants. So this variant quit doesn't hold any additional data, while this variant move here holds fields. It's very struct-like. And this variant write is tuple-like, so it holds a value in a tuple syntax, and the same thing for change color. So we can then instantiate the move variant from the message enum with these values over here, x1 and y2. And as you can see, because this is very struct-like, you instantiate it basically like a struct. And over here, instantiating with hello world. As you can see, this variant over here holds a string type. So like that. And please notice over here that both of these variables here hold the same type, message. Because this is also a custom type, a type we have created. We can get the data which an enum variant is holding by pattern matching. So over here we have the same enum like we saw before, and over here we have an instance of the move variant. Now we can here use if let, and we will cover that in the next section, to get out the data inside this move variant. So we are matching here the message variable holding an instance of the move variant, and then over here we can basically destructure it. So x should then be destructured into a variable a, and y should be destructured into a variable b. And then, as you can see, we can use these two variables. Now we are here asserting a and b, and a stands for this value and b stands for this value. And as you notice, they are not the same, so this would fail actually. So let me change that, and now let's run the program. Fill in the blank and fix the errors. Again, same enum, and over here we have an array of different variants from this enum type, right? We have the quit variant, the move variant, and the change color variant. Now the neat thing here is that all of these instances are of the same type, message, right? Our custom type. Now I hope you remember how we annotate an array. So first thing will be the type and then the number of elements. Let's see, we have over here 3 elements, right? And the type would be, I hope you know it, message, right? All of these variants or instances hold the same type. And then over here we are looping over this array here, meaning message, this variable, will hold in each iteration one of these instances, and then passing it to the show message function. And as you can see, when we want to take an instance of this enum message, we can just use the type message here, because again all of them have the same type, and all we do then is just printing it out. And again, because this is a custom type, we cannot print it out just like that. So we have to use debug notation here and derive over here the debug trait. And as you can see, in each iteration over here, we call the show message function, and it will print out the contents of this array. So let's see exercise 5. Since there is no null in Rust, we have to use enum option to deal with the cases when the value is absent. And I want to show you some slides for that. So the option enum. Option is an enum that represents a value that may or may not be present. It's known in other languages as null, and it's referring to the absence of a value. It's used to handle cases where a function or method might fail to return a value. So this is how the enum option looks like as defined by the standard library. As you can see, it's an enum holding two variants, none and some. Now this over here is a generic, meaning that some can hold any type, and we'll cover generics very soon. But for now, again, think that this can hold any type provided. So let's see an example over here. We are here initializing the variable 5 with the variant sum holding an integer value, right? And then over here we are calling the function +1, providing it 5. So let's see here. As you can see, the argument should be of type option, and the type parameter here would be i32. Now we have to provide a concrete type for this generic type parameter. Now again, we will cover that in much greater detail, but as you can see, this is exactly the type we are passing to the function. Sum is a variant of the option enum, and it is holding an i32 value, and it is holding an i32 type. Now then we are matching this argument over here. If it is holding a none, we will return none. If it is holding a sum, then over here we are destructuring the value wrapped inside the sum variant into the variable I. And then over here we are incrementing I by 1 and wrapping it in a sum, because as you can see, the return type over here is defined as option i32. And that means that this variable over here will then hold sum 6, right? Because we have incremented 5 over here by 1. So this will hold an option type, and the concrete value would be sum 6, the sum variant, and a value of 6. Now over here we are calling the +1 function with none, meaning the argument will get matched and this will then get returned, right? A none. And as you can see, the none is also a variant of the option enum. And this i32 just stands for the sum variant. If we are returning none, then this type over here is still valid, because the none variant here doesn't hold any value of generic type T. But again, generics are a topic on its own. And by the way, this is exactly the same that we have over here. So let's do that, annotating the types. So over here we have an option holding an i32 type. All right. And as I've said, this is not necessary. You can omit that because again, the option type is in the prelude. Then we are calling the +1 function. Again, we are providing it sum 5, which is an option, and then we are matching the argument. So if the argument is none, then we return none. If it is sum, then we destructure the value that was passed over here, and we increment it by 1 and return it wrapped in sum, because the return type has to be of type option. That means over here the type annotation would be option i32. And in this case we are passing a none, so a none will be returned. And by the way, the returned value here would be sum 6, right? Because 5 plus 1 will be 6. And over here we have none, and the type annotation would still be option i32. Now we want actually to unwrap this value inside the sum variant, and we can do that by using if let. So as you can see, we are matching the 6 variable holding sum6, and then we can destructure it basically. So we can then say sum and the variable n, meaning we then can use n over here. And I see right now never let this run, so we have to pack that into an else block. Just to ensure that this doesn't run after we are running this conditional here. And as you can see, it will output the value inside sum. Now again, we'll cover generics, we'll cover if let and match over here. This will actually be the next topic. So don't worry if this seems a little difficult to understand, we will cover that in much greater detail. Implement a linked list via enums. Now over here, this linked list I won't cover because there are a lot of things we haven't seen. So in here we have methods and other things that we didn't really cover. So I think this would be more confusing than it would be helpful. What I suggest you is that you will come back after we have seen some more topics. You come back to this exercise and try to solve it. It's not that difficult, and the solution will be on my GitHub account, but I think this is just overkill right now. So see you in the next topic. The normal flow of execution in a program would be from top to bottom, line by line, but we can actually manipulate the flow of a program. And flow control is a concept that refers to the ability to control the order in which statements or instructions are executed in a program. It allows to specify which instructions should be executed under which conditions and in what order. So we have many ways to do that, and some of them are, for example, using conditionals. So we have the if-else keywords and match, for example, and we can use loops, for loops, while loops. There is a special loop in Rust called loop, we'll cover that. And we can even manipulate the flow inside a loop by keywords such as continue and break. So let's see. So let's start with if-else conditionals. Over here we are initializing n with a value of 5. Then over here we have an if conditional, checking if n is less than 0. In this case, this would evaluate to false, meaning this instruction over here will get ignored and the program will continue executing on the next line. Now in the next line we have another conditional. So we can use here the else if keyword. And over here we are checking is n bigger than 0. In this case, this would evaluate to true, meaning this line will get printed out. Now we can also match anything else using the else keyword, meaning if this evaluates to false and this evaluates to false, then this will get executed. Now in this case, this evaluates to true, so this will get executed, meaning this over here will be ignored. As you can see, this was the line that has been printed out. Number 2, if-else expression can be used in assignments. Again, initializing n. And over here we have a variable assignment. Now we can even use if-else conditionals when assigning a value to a variable. Now remember, a variable assignment is a statement, so So we have to end that with a semicolon like that. So let's see, we have here an if conditional, and this is a Boolean AND operation. Do you remember? We have two inputs, and both of these inputs have to evaluate to true in order the AND operation to return true. So let's see, we have here n should be less than 10, which would evaluate to true, right? Because 5 is less than 10. And 5 is bigger than -10. So this AND operation will return true, meaning the code in this if conditional block will get executed. And over here we are just printing out a line, and then we are multiplying n by 10. And in fact we don't have a semicolon, so this will be returned from this expression, meaning it will then be assigned to the variable big N. So big N will then hold a type of I32. Now in case this would evaluate to false, then this else block would get executed, meaning again we are printing out a line and then dividing n by 2.0. Now as you can see, we should omit this semicolon because this result over here should then be assigned to this variable. Now we actually can't do this operation here because n is of type I32 and we are dividing it by a floating point number. So we can typecast that to an I32. And as you can see, this would be the output, and we are printing out big N, meaning 50 over here. So N has been multiplied by 10. So let's see, we have here a for loop. The for in construct can be used to iterate through an iterator, for example, arrange A to B. Now, as you can see, we have a for loop declaring a variable n, and we provide a range. Now, this range over here reaches from 1 to 100, and 100 here included because we have here the equals sign. Then we are checking if n is equal to 100, this program will panic. That's not what we want. So what we can do over here is just removing this equal sign, because that means 100 is excluded, meaning n will never be equals to 100. The largest it will get will be 99. Let's see. All right. Fix the errors without adding or removing lines. So over here we have an array holding two strings. Now we want then to iterate over this array, meaning this name variable will hold in the first iteration this string and in the second iteration this string. So what we can do over here is printing out name, right? So this will iterate 2 times and it will output this and then this. Now, as you can see, we are trying to access names again over here, and that would then violate the ownership rules, because as you can see in a for loop, the for loop actually will take ownership of the provided value, and we can pass here a reference like we have seen before, and that means we can use names then again. So, and by the way, we don't have to dereference name over here because the print line statement will do that automatically. Now over here we have three i32 integers. The elements in numbers are copies, so there is no move here. So we are iterating over each element in this array, where n will then hold in each iteration one element from this array. So let's see. So, and this would be the output. As you can see, in the first iteration, name will hold this string, and in the second iteration, it will hold this string, and it prints it out in each iteration. Then we print out the whole array, and over here, the same thing, but with the integers. So, again, we have an array. So iterate the indexing and value in A. So there is a useful method called enumerate. And this enumerate method takes a collection, for example an array or a tuple or anything else, and it will then return a tuple. And this tuple will then hold the index and the value. Meaning, for example, in the first iteration, this tuple will hold for I 0 and for v 4, right? Because at index 0 we have a value of 4. And it will then just print out the index, but we increment it by 1 and the actual value. And of course we have to put A into an iterator. So let's see. Like that. So we have to first put A into an iterator, and then we can call this enumerate method on it, because the enumerate method is implemented in the iterator trait. We'll take a look at that later. So as you can see, this will be the output. And that was the reason we have incremented I by 1, because we don't want to start with the 0th element is 4, right? So we say here the first element is 4, second 3, and so on. While. The while keyword can be used to run a loop when a condition is true. Fill in the blanks to make the last println work. So as you can see, we have here a mutable variable n. Loop while the condition is true. So as you can see, this is a while loop, and we provided a conditional, meaning if this evaluates to true, then this loop will keep running until this conditional evaluates to false. So inside the while loop we have other conditionals. As you can see, we here check the condition n modulus 15 is 0. If that would evaluate to true, then we print out that. And by the way, this was a question at coding interviews at Google. So we are here having more conditionals and an else conditional. So meaning if anything of this fails, then this will get printed out. So what we can do over here, checking if n is less than 10, then this loop will keep running. Now when you're using while loops, then you have to ensure that the while loop eventually stops, right? That this conditional over here will evaluate to false eventually, because otherwise you would have an infinite loop. Now to do that, we can increment n over here. So I increment at the end of this while loop n by 1, meaning in each iteration in this while loop, n gets incremented by 1. So n will eventually be bigger or equal to 10, meaning this would evaluate to false, meaning we break out of this loop. Continue and break. Use break to break the loop. So we have here a for loop looping from 0 to 100 and 100 included. So if n is 66, then we want to break out of the loop. And the break keyword will immediately exit out of this for loop. So when this conditional evaluates to true, we immediately exit out, meaning the program will continue execution after the for loop. In this case, this line over here. Let's see. So as you can see, in the end, n will be equal to 66. Because when I is 66, then we stop iterating. Continue will skip over the remaining code in current iteration and go to the next iteration. So as you can see, we are here again iterating from 0 to 100, and we have here an if conditional. If n is not equal to 66, then we increment n by 1. And we want then to continue, meaning that the remaining code in this for loop will get ignored. So this continue keyword, the program will go back to the beginning of the for loop. Now in case this evaluates to false, right? So if n is in fact 66, this would evaluate to false, meaning we ignore this code block and we go over here where we want to break out of the loop, because as you can see, we want n to be 66 at the end. Loop is usually used together with break or continue. So loop is a special loop in Rust where this is basically an infinite loop, and you have to manually manipulate the flow of the loop, and we will see soon. So this is an U32 over here, count. So let's count until infinity. As you can see, we are here using the loop keyword, meaning this would keep looping to infinity, or we provide some keywords that will break out of the loop or continue. So as you can see, in each iteration we are incrementing the count variable by 1. Now if count is equal to 3, then we print out 3, and we want to skip the rest of this iteration. So we can use here the continue keyword, meaning again the rest over here will be ignored. The program will go back to the beginning of the loop. So then over here, if count is not equal to 3, this will get printed out. So we print out the count in every iteration except if count is equal to 3. And then over here, if count is equal to 5, then we print out, okay, that's enough, and we want to break out. Meaning count in the end should hold a value of 5. As you can see, we are iterating 1, 2, and then in the third iteration, this if conditional evaluates to true, meaning we print out 3, and we continue. We are going back to the beginning. So the actual value of count over here is not printed. As you can see, there is no digit 3, but we printed out 3 over here because that was defined in this code block here. And then at iteration 5 we will stop and break out of the loop. So loop is an expression, so we can use it with break to return a value. And again we have here a counter. So over here we have a loop, and we are in each iteration incrementing counter by 1. Then we check if counter is equal to 10, then we want to break out. But as you notice, we want to assign a value to the result variable, right? This variable should then hold an i32, but we don't return anything here. So you can define after the break keyword a return value, meaning, for example, we want to return counter. But in this case, result will hold 10, right? Because counter, when we break out, will be 10. Otherwise, this conditional would not evaluate to true. So if counter is 10, then we break out. But as you can see, we want result to be 20. So we can even pass here an operation, so we can double the counter value. Let's see. And this is compiling. It's possible to break or continue outer loops when dealing with nested loops. In these cases, the loops must be annotated with some label, and the label must be passed to the break continue statement. So, as you can see, we can even nest different loops. So when we do that, we have to actually provide labels. So we provide here outer for the outer loop and inner one for the inner loop. And as you can see, we have even two inner loops. So we have inner one and inner two. Alright, so let's see. In the first inner loop, we are checking if count is bigger than or equal to 20. If this is the case, we break out of this inner loop. Otherwise, we increment the count by 2. Alright. And notice here, this would break only the inner one loop. So when we break out of this loop, this outer loop will still continue looping. Okay? So then over here in the outer loop, we are incrementing count by 5. And in this inner 2 loop, we are then checking if count is bigger than or equal to 30, then we break out of the outer loop. Otherwise, if count is smaller than 30, then the outer loop will continue, meaning the program will go back to the beginning of the outer loop and continue executing from here. So let's go step by step. And as you can see, we have to find out here what the count value will be in the end. Okay, let's go step by step. We start at 0. Then over here we are checking, is count bigger than or equal to 20? No, right? So that means count will get incremented by 2. And this will continue because we are in this loop, remember, and this will continue until this evaluates to true, meaning when count is 20, then we break out of this inner loop, meaning we continue executing here. Then count would be 20 and we increment it by 5. Then we enter this inner 2 loop. So 25 is not bigger or not equal to 30, meaning we don't break off outer, but we will continue outer, meaning we go back over here. Now we enter this loop here, and 25 is bigger than 20. So we break out of this inner loop and continue here. Then we add 5 to count, meaning count is now 30. So we enter this inner to loop, and this will now evaluate to true because count is equal to 30, meaning we break out of the outer loop. So in this case, count will be 30 in the end. And this succeeded, and I will see you in the next topic. Pattern match is a powerful construct that allows you to compare a value against a set of patterns and then execute different code based on which pattern matches. And these patterns can be made up of literal values, variable names, wildcards, and so on. And in a match statement, all possible cases must be handled, and this is enforced by the compiler. And really, this match keyword is something that I really miss when I'm coding in other languages. So once you get used to it, you will love it, and you will see why. So let's see an example. Over here we have a coin Enum, and this Enum holds variants of different denominations of US currency or US coins. And here we have a function value in cents. This takes as an argument a variant of type coin. Then it matches the argument, and as you can see, it matches the variance of this coin Enum. Meaning, if we provide an instance of this coin Enum which holds a penny variant, for example, then it will return 1, right? And this will then be the return value of this function. So for each denomination over here, it will return its proper value. Then let's see if let. So I've said that in a match statement, all possible cases have to be handled. And this could sometimes lead to annoying boilerplate code that is not really that necessary. So for example, we have over here an option type, right? A value wrapped inside sum. And then we match this variable over here that holds this option type. And then we are matching, as you can see, if it is sum, then we destructure the value inside this max variable, and then we just print it out. Now, as you can see, we also have to match any other case, meaning if it is not sum, in that case none, then nothing will get executed, meaning it will return a unit type. Now, this is sometimes too verbose, especially for cases like this. For example, you just want to unwrap something from a sum variant. Now what we can do instead is just using if let. So it's exactly the same as this match statement, but we know that config max holds a sum value, right? So we don't have to consider the case where it holds a non-value. And as you can see, this is how we would destructure this value into the variable max. We use the if let keyword and then the pattern. So if config max holds a sum, then the value will get destructured. Let's do exercises. Fill the blanks. So over here we have a direction enum holding directions over here as variants. Then over here, as you can see, we are instantiating the direction enum with a variant of south. So the type over here would be direction. Then we match this variable here, and if this variable over here holds direction east, then it will print out east. Now we want over here to match south or north. So what we can do over here is pattern matching either south or north, and we can do it like that. So we are here matching. So we are here basically saying if this variable holds either a variant of south or north, then it will print out south or north. Now, in case it's not any of these variants, then it must be west, right? So we can print out here west. Let's see. And as you can see, the variable holds south, so this will get matched, so this will get printed out. Match is an expression, so we can use it in assignments. Over here we have a Boolean value. Fill the blank with a match expression. Boolean true, binary 1, Boolean false, binary 0. So what we want to do is we want to match this variable over here. And then we provided the cases. So if it is true, then we should return 1. Otherwise, we return 0. So that means the return value over here will then be assigned to this binary variable. Let's store that as U8. And that means binary should then hold 1, right? Because we are matching here true. And then the return value should be 1. Using match to get the data and enum variant holds. Again, we have the message enum. We have seen that before. Then over here we have an array of message variants. Over here we are iterating over this array and passing it to this function. As you can see, the argument should be of type message. So we are then matching this provided argument. So we want to match over here message move. Now, as you can see, the message move has struct-like syntax. So we have to match it like that. And as you can see, we want the variables a and b. So let's do that. As you can see, it holds fields x and y. And that means we will then destructure these values into the variables a and b. So a should hold 1 and b should hold 3. Then we match over here the message change color variant. As you can see, this is a tuple-like variant. And this tuple has 3 elements, so we can provide it some variables. And we use here RGB, red, green, blue, and this is for color representation. So in that case, G, the second value, should be 255. And the last value B should be, in this case, 0. And again, because we have to match all the cases, if there is anything else that doesn't match here, we will print out no data in these variants. Like that. Matches. Matches looks like match but can do something different. So the macro matches allows us to test, for example, this array if a pattern matches. So as you can see, we are iterating over the elements of this array. So over here we have the assert macro, and all this does is it asserts that the given argument evaluates to true. So we can over here use the matches macro, and we provide it AB, meaning the character we are iterating over. And then we can give it a pattern it should match. So as we are iterating over each element over here, it should match each of these characters. And we can do that like this. So we want to match characters from A to and including Z, or A to and including Z lowercase, or 0 to 9. And notice these are characters and not integers because we have here an array of characters. Let's see. And this succeeds. As you can see, all we did is we iterated over each element and we checked over here for each element if it matches this pattern. And in this case everything matched because assert didn't panic, right? Because if one of them would evaluate to false, assert will cause the program to panic. Let's see exercise 5. So over here we have an enum with two variants, foo and bar. Then here we have a count variable which is initialized with 0. And over here we have a vector. Now we didn't cover vectors yet, but they are very similar to arrays, but their size can shrink and grow, meaning a vector is dynamic in its size. So as you can see, we are having a vector of my enum variants, two of them foo and one bar. So this is a vector holding types of my enum. Then over here we are iterating over the elements of this vector. Now we want to match my enum foo. And if conditionals don't allow to match for patterns, so we can't use that here, but we can do something else. We can here instead use the matches macro, meaning we take E, the element in the vector we are iterating over, and we match it for this pattern, right? So if the element we are currently iterating over matches my enum foo variant, then we want to increment count by 1, like that. And that means count after this for loop iterating over each element should be 2, right? Because matches matched 2 times, because there are 2 my enum foo variants in this vector. If let, for some cases when matching enums match is too heavy, we can use if let instead. So over here, as you can see, we have an option of type I32. We move the whole match block using if let instead. So as you can see, match is really verbose, so we can use if let instead. And we do that like this. We use the if let keyword and then the pattern we want to match. In this case sum, and the variable should be I. So the inner value here will get destructured into this variable I. And then we are matching on O. And if this matches, then we want to print out these two lines. As you can see, this is much cleaner. And this will get printed out. This is a really long string and 7. As you can see, we here provide I, and I just holds the inner value of this sum variant. Fill in the blank, we have here a foo enum with a bar variant holding a type of U8. Then over here we have an instance of the bar variant holding a value of 1. Now over here again we could do the same thing. We can use if let, and then we match the pattern. So if the pattern is foo bar, then we want to destructure the inner value to a variable I, and we are matching on A. As you can see, this compiles. So we have a foo enum with 3 variants, and only the last one holds a value. So over here we instantiate the foo enum with a variant of Qs and a value of 10. I hope I pronounced that correctly. So remove the codes below using match instead. So if I run this code, then this would actually work because we are using if let here. But we can do it in a match statement. So we match on A, right? And then we can provide the pattern. So in case of foo bar, then we will print out this line. In case of foo bas, we want to output this line. And in case of anything else like that, we print out this line. Now I can delete that. And as you can see, much cleaner. So in this case, match others. Shadowing, fix the arrows in place. Again, we have here an option with an inner value of I32. Then we are here using if let to destructure the inner value to H. And that means we are actually shadowing H, because as you can see, this variable here has the name H, and we are then destructuring into a variable H. So that means H has been shadowed. Create a new variable with the same name as previous H. Now over here, as you can see, H would be sum 30, which is wrong, because we are actually here destructuring it, right? So H doesn't hold sum 30 anymore, but it will hold 30, because we are here destructuring it. The new variable age goes out of scope here, right? So this variable over here goes out of scope. And a match can also shadow a variable. So we can here essentially doing the exactly same thing like in the if-let statement over here. And as you can see, this would be the output from this match here. Alright, see you in the next topic. So let's see patterns. We can use this sign to match several values, and we can use this one to match an inclusive range. So as you can see, we have here a function match number which takes an integer as argument. Then we are matching this integer, and if it is 1, then we'll print out 1. And fill in the blank with this, don't use ranges. Okay, so we have to match here 2 to 5. So we can do it like that. And this pattern is basically saying if n is either 2 or 3 or 4 or 5, then we will print this. Match an inclusive range, so if n is between 6 and 10, where 10 is included, then it will print out that. And for any other case, because again in a match statement we have to match every case, so in this case we will print out that. The add operator lets us create a variable that holds a value. At the same time, we are testing that value to see whether it matches a pattern. So let's see, we have here the point struct that has 2 fields with i32 types. Fill in the blank to let p match the second arm. So we have to complete here something. We have here an instance of the point type. Now let's see the match here. So we match on p, and as you can see, this is how we would match a struct. So we provide the struct name and then the fields. As you can see, we are matching x and y. So if y is equal to 0, that means this arm here matches, and this will get printed out. And we then can use x over here, because this is actually a destructuring assignment. So this would be the same as writing it like that, but this is shorthand syntax. So we are then using x here. Now in the second arm, as you can see, we are matching x and y fields. So x should be between 0 and 5 included, and y should be either 10, 20 or 30. Now as you can see, when we are matching here this pattern, we can't use x. We don't use x here, but we can in fact use y, because we are using here the add operator. So this means we are destructuring the variable y of the field y. So that means the value that y is holding over here will get destructured into the y variable. And at the same time, we are testing y if it is matching this pattern. And the last arm, as you can see, we don't match for any pattern other than this main pattern, and then we can use x and y, because again this would be the same as writing it like that. Alright, now we want to match this second arm. That means we have to provide values that match these patterns. So let's see, x between 0 and 5, so let's do 3. And why 10, 20 or 30? I will do 30. As you can see, this second arm matched. Fix the errors. Over here we have the message enum which is holding one variant with a struct-like syntax. As you can see, this has one field ID of type I32. Then over here we are instantiating this variant, so this will be an instance of the message enum. And then over here we are matching this instance. So if it is hello, then we match the ID field. So is it between 3 and 7? Then we want to output here the ID. Now the problem here is that we did not actually destructure this field here into its distinct variable, right? So we have to provide here a variable. Let's do ID because that's the one defined here. And for that we have to use the add operator. So we are destructuring and matching the pattern at the same time. And over here, this is already done. As you can see, we can also provide a variable with another name, as you can see. So the value of the ID field then will get destructured into this new ID variable, right? It doesn't have to be the same variable name as the field we have. And again, we are destructuring and at the same time pattern matching, and that is the reason we are using the add operator. And as you can see, when we are matching like that, then this ID over here got destructured because this is the shorthand for this. All right. And when we have a pattern here, we have to wrap it inside parentheses. That's also important. And as you can see, in this case, the first arm matched, right? Because ID over here, the value is between 3 and 7. A match guard is an additional if condition specified after the pattern in a match arm that must also match along with the pattern matching for that arm to be chosen. Fill in the blank to make the code work. Split must be used. Alright, as you can see, we have here an option with an I32 value. Then we have here split, and we are here matching the num variable, and we are doing that to basically destructure the inner value. So we are putting the value of 4 into x, right? So we can then use x over here, but we over here also want a match guard to check if x, in this case this value over here, is less than split. We can do that like this. So this basically is just for destructuring this value into x, and over here we have an additional conditional, a match guard, to check for a more specific condition to be true. So if num is a sum, so if num is of some variant, then we destructure x and check it again. And if all of that matches, then we execute this. If it is a sum, but but the value over here is actually bigger than split, then this will get executed, and if num holds a none, then we just return a unit type, ignoring remaining parts of the value with this. So as you can see, we have here a tuple. I won't annotate that. So we are matching on numbers. Now we only care about the first, as you can see, and the last one. So what we can do over here, we are matching on a tuple, right? So this is a tuple, and we want to destructure the first and the last values into the variables first and last. We can do it like that. Right? So we have the first, then anything in between, and then the last. So first should hold 2 and last should hold 2048. Using pattern mutable reference to v to match a mutable reference needs you to be very careful due to v being a value after matching. Let's see, fix the error with least changing, don't remove any code lines. So over here we have a mutable variable holding a string. And this would be a variable that holds a mutable reference to a string. Now we match R, and that means over here we can destructure it directly into a value like that. So this string over here will then be destructured into the value directly. We don't have to match mutable reference like that, right? And that means the value variable will hold a mutable reference to a string. And of course then we can modify the string over here. Alright, that's it. See you in the next one. A method is a function that is associated with a particular type or struct. It takes parameters and returns a value, like a function, but it's defined as a member of a struct or an enum. It's called using dot notation, like accessing members of a struct, and it's implemented through an implementation block. Let's see an example. Over here we have the struct rectangle with 2 fields. And as you can see, we can then implement methods for this rectangle type using the impl keyword and the name of the type we want to implement the methods for. So then over here we can see that rectangle has a method called area. It takes as an argument a reference to self, and self stands for the name of the instance. So inside the method we are multiplying self.width, this field, by self.height, this field, and then we return the result of this operation. Now again, self over here will be replaced by the name of the instance. So when we create an instance of rectangle with concrete values, then as you can see we can call this method on the created instance rect1, meaning when this method is called like that, then self over here will be replaced by rect1. So here rect1.width times rect1.height, meaning 30 by 50 will be returned. Now let's see associated functions. An associated function is a function that is associated with a struct or an enum, but doesn't take an instance as its first parameter. So you can recognize an associated function if it doesn't take self as its first parameter. It's called using the name of the type, not an instance of it. And it's often used as constructors for a struct or an enum. So let's see an associated function. As you can see, we have again the rectangle type. And we implement over here, again in an implementation block, the new associated function for the rectangle type. And notice we don't have self here, and you will see in a minute why that is. Now the new associated function takes two arguments, width and height, both of type U32. And it will then create an instance rectangle and returns it. Meaning, when we want to call this associated function, we don't call it on an instance, right? Because we don't have self here. We call it directly on the type. So in this case, we take rectangle, double colon, and then the function new, and we provide it two values, 5 and 10, right? That means rec1 will then hold an instance of the type rectangle. Okay, let's do the exercises. We will skip this example because I've showed you that before. And we will do the exercises directly. Methods are similar to functions. Declare with fn, have parameters and a return value. Unlike functions, methods are defined within the context of a struct or an enum or a trait object. And the first parameter is always self, which represents the instance of the struct the method is being called upon. So as you can see, we have the rectangle struct again. And over here we have the implementation block. We can implement the methods for this type. Now, as you can see, we instantiate rectangle over here with concrete values and then assign it to rect1. So rect1 holds an instance of type rectangle. Then over here we call the method area on rect1, and we should get back 1500. So let's implement the area method. So the first thing is we always start with self. So every method takes as first argument self, okay? Then the return type will be a U32, right? Because we are here doing operation with these two fields. Now, what we want to do to get the area of the rectangle is multiplying the width by the height. So we use self.width times self.height. And I omit here the semicolon, so this will get returned. Let's see. So when we call the area method on the rect1 instance, then rect1.width times rect1.height will result in 1500, meaning 30 times 50. Self will take the ownership of current struct instance. However, reference to self will only borrow a reference from the instance. Let's see, we have again the struct traffic light with one field. Now over here there is the implementation block. We can implement methods for this struct. Now using self to fill in the blank. So we have been using self like this, right? Meaning we take a reference to the instance. Now this is actually syntactic sugar for this. And as you can see, self with an uppercase S refers to the type we are implementing the method on, right? So in this implementation block, when we use self uppercase, it refers to traffic light. And you can use this syntax, or you can use, like we did before, using just self, right? And here we want to take a mutable reference because we are here mutating the color field. And again, and this and that are exactly the same, but this is not mutable. So if I would do it like that, then as you can see, these are actually exactly the same thing. But I would suggest just stick with that. It's more readable and it's clear what you mean. Associated functions. All functions defined within an impl block are called associated functions because they are associated with the type named after the impl. We can define associated functions that don't have self as their first parameter and thus are not methods, because they don't need an instance of the type to work with. So as you can see, we again use the traffic like struct, and here we have the impl block. So let's see, first implement an associated function new. It will return a traffic light contains color red. Must use self, don't use traffic light in fn signatures or body. Let's first see in main what's going on. So we call here the new associated function. And this associated function is associated with the traffic light type. And again, notice the difference is we call this directly on the type and not on an instance. Otherwise, it would be a method. So we call new, and then we want to have an instance of traffic light back. Right? This new function should return an instance of traffic light, meaning we can then call upon this instance light the getState method and return red. So let's see. Over here we are expecting no argument, right? So let's leave it like that, and remember, associated functions don't take self. Now the return type would be traffic light instance. And because we should use self in here, we can do that. And again, self in an implementation block refers to the type. In this case, traffic light. Then in there, we want to create an instance of traffic light. So again, we can use self instead of this name. And then we, like normally instantiating it, providing it concrete values. So in this case, we want the self.color field to hold a string of red. Like that. And as you can see, then we should get, and as you can see, when we call this associated function, we will get back an instance with this concrete value, a string red. Then we call upon this instance light the getState method. So again, self here refers to light because we are calling the method on this instance. And it takes just a reference to the instance, meaning light is usable even after this method call. And all it does, it will return the value inside the color field of the instance, in this case light. So light.color will hold a string of red. Multiple impl blocks. Each struct is allowed to have multiple impl blocks. Again, rectangle struct, and using multiple implement blocks to rewrite the code below. So we can either put all of the functions and methods in the same impl block, or we can even reorganize it using various different impl blocks. So we can, for example, put that in its own implementation block like that, and it will work exactly the same. This is just for organizing and restructuring. Enums. We can also implement methods for enums. So over here we have the enum traffic light color with 3 variants. Implement traffic light color with a method. So over here in main we are instantiating traffic light color with a variant of yellow. This would be the type annotation. And then when we call a method color on the C instance, it should return yellow. So let's see. So we could implement that using a match statement. Then we match self, and if match self would be this, then we return the string yellow. Okay. And we can over here, instead of writing the whole name of the type, we can again use uppercase self, referring to the type this method is implemented on, in this case traffic light color. And remember, in a match statement we have to handle all the possible cases, meaning we have to create an arm for red and for green too. So let's do that. Let's see. And as you can see, because we have here an instance which holds the variant yellow, we will get back yellow when we call the color method. Alright, that's it. Until next time. Until now, we have only been dealing with concrete types, but we can also deal with generics. And generics are placeholders for concrete types. It enables writing more reusable and flexible code, and it avoids having duplicate code for different types. It's a zero-cost abstraction, meaning the Rust compiler will at compile time fill out the generics with concrete types. And there is also a concept called const generics. I will just briefly touch upon it because this is more of an advanced topic, but I will show you one exercise just so you get the idea from it. So a const generic is a type parameter that represents a compile time constant value. It allows to write generic code that operates on values that are known at compile time, and it's mainly used for array sizes, bit widths and other constants. And you will see what I mean when you see the exercise. Let's start with generics. So as you can see over here, we have a struct A. Now this would be considered a concrete type because we don't deal with generic types in here. Now the struct S takes as an argument an instance of the struct A. This is also considered a concrete type because again there are not generics used here. Now the struct sgen is considered a generic type because we are dealing here with a generic type parameter, and this would be the notation when you declare a type, for example, then after the name of the type, you annotate a generic type parameter like that using these symbols over here, and then providing a name. And by convention, this is usually T, standing for type. And that means this struct can hold any type. Now, as you can see, we have here some functions. This function over here takes S, which is a concrete type. The gen spec T takes as an argument an instance of sgen with a type of A. Now again, A would be a concrete type, meaning the type parameter over here is specified to be a concrete type. So we can only pass to this sgen struct an instance of the struct A. Then over here we have the genSpec i32 function, which takes as an argument the sgen struct over here with a value that is of type i32. And over here we have a generic function, meaning we are declaring after the function name the generic type parameter T, and then we can use it on here, meaning that we can provide as an argument over here an instance of sgen with any type. So let's see, using the non-generic functions. So these over here are all non-generic, as you can see, because we didn't define a generic type parameter, and all the values it is using are concrete, right? Over here we have S, over here we have sgen, and this is taking as a value T over here the concrete type A. And over here it takes as concrete type i32. So all these are non-generic functions. The only generic function over here would be this one. So let's see. So we want to call the recfn function. And as you can see in the function signature, we are taking as an argument a type of S. So let's provide that. Now we have to pass into S the concrete type A, right? Because that is defined in this struct. Then gen spec T. So this function over here takes an sgen struct with a type of A. Now again, A would be a concrete type. So we provide here sgen and A, right? So we are passing to the sgen struct over here a value of type A. And in this case we want it to be sgen and let's say 7, because over here we defined that this function should take as an argument a type sgen which holds an i32 integer. Then explicitly specify type parameter char to generic. So over here we are calling the generic function, meaning we can pass to it an sgen type holding any possible type. Now we can explicitly specify a type parameter for this T over here, and we are here saying T should be a char, meaning we are calling the generic function over here with the type sgen and passing as a value a type of char, let's say A. And implicitly specify type parameter char to generic. So we don't have to annotate the type here. It will be automatically inferred by the compiler. So if I do the same thing over here, let's go with Z this time. As you can see, this is compiling. Now again, because sgen is defined to be generic over its type, pass any value. So let's pass, for example, a floating point. As you can see, this is also compiling because T over here is a placeholder that stands for any type possible. But again, when we annotate the specific type, then we can only pass a character in this example. So if I try 7.7 here, this would be a compiler error. If I define F64, as you can see, then it's working. Alright. A function call with explicitly specified type parameter looks like that. And this is also called the turbofish syntax. So let's see, implement the generic function below. So as you can see, we are calling here the sum function with different types, and that's the whole point of generics. So here we are calling sum with two i8 integers. Over here we call the sum function with two i32 integers. Remember, if nothing is annotated, then the default integer type is i32. And here the same thing, but for floating point F64. So we have to use here generics, otherwise this won't be possible. Over here we are creating our generic type parameter, and again by convention this is called T. Then we take here the arguments. So let's say A should be of type T and B should also be of type T, and then we return a type of T. Meaning, if we pass here two i8 integers, then T will get converted to an i8, right? This is just a placeholder. And because we operate then on two i8s, the return type will also be i8. So what we do is just adding together the two arguments and return it. And over here we have to implement a trait bound, and we'll cover that in the next section. So we have to define here that T should implement the add trait, otherwise we can't use this plus sign over here. And again, we will cover that in the next section when we look at traits. And as you can see, this is compiling. So we can pass to sum two numbers of any type. Let's see, number 3, implement struct point to make it work. As you can see, we are instantiating 2 point structs, but over here we are passing to the fields different types. So in the first instance we would have i32 values, and in the second instance we are dealing with floats. So to make that possible, we have to use generics. So let's implement the point struct, and we are defining here the generic type parameter, and then we can define the fields. And as you can see, the fields hold the type T, meaning if we pass it integers, then X and Y must both be integers. If we are passing it floats, then both of these fields must be of type float. Now, because we are here defining a generic type parameter, this parameter over here becomes part of the type annotation. So over here we are providing to the fields of the point struct values of type i32. So we must annotate that. And over here we are passing f64. And as you can see, this is compiling. Now again, we don't have to do the type annotations actually, I just want to make that clear. As you can see, the compiler is able to infer that for us. Modify the struct to make the code work. Don't modify this code. So as you can see, we are here instantiating a point, but the fields over here hold different types. So this is not working because T over here defines that both of these placeholders will be filled with the same concrete type. So in this case, if we are passing x over here with an i32 type, then the compiler thinks that y should also hold an i32. Now what we can do then is defining another generic type parameter. And by convention, you just go one letter further. So T and U. Meaning we can then use here U, right? And this indicates that the fields over here hold different types or could potentially hold different types. They can also hold the same types. And then when we annotate that, we have said that the generic type parameter becomes part of the type annotation. So we would pass here for x, so we would pass here for t and i32 the value, the type the x field is holding, and over here a string. So this would be the type annotation for this returned instance. Number 5, add generic for val to make the code work. Don't modify the code in main. So here we have the val struct holding one field, and we have an implementation block implementing one method for the val type. Now, how do I know it's a method? Because it has as first parameter the self keyword. And all this value method does is just returning a reference to the val field value. All right. So when we instantiate the val struct over here, we are providing it a type of f64. But over here, we are instantiating the val field with a string. So again, we have different types. So let's annotate here the generic type parameter. Then we can use t here, meaning the field val can hold any type. So let's annotate here. Now over here, as you can see, we are returning the value of the val field, and we define here that it should be of type f64. Now this would cause an error because when we call over here the value method on the instance of y, then self.val would hold a string, right? So it doesn't return an f64. Now we have to use a generic type parameter also in this implementation block, and we can do that like that. So we have over here the generic type parameter for our type, and as we've said, this becomes part of the type annotation. And over here we are also defining a generic type parameter t, so we are then able to use it inside the implementation block. So over here we can define that it should be a reference to t, right? A reference to any type that the val field holds. So in the first call of value it would be an F64, right? That is the type of the returned value that val field is holding. And in the second call over here it would be a string, right? So t then would be string. Number 6, we have here a point struct, and we are here defining that the fields could potentially hold different types, but they could also be the same. And here we have the implementation block for our point struct. Now, as you can see over here, we are instantiating a point with i32 values. Right, so they can be the same. Even if we here have two generic type parameters, it doesn't matter. They can be the same. But over here we are instantiating point with two different types, right? We are instantiating point with a string literal, this here, and a char, that over here. So they are different in its types. Then we call over here the mix-up method on p1 and provided an argument of p2. And then over here, as you can see, we want then p3 to look something like that. So we want the newly created instance here, p3, to hold the value of the first instance, in this case p1. As you can see, we are taking x from p1, and we want the y field to hold the value of the p2 instance, this character, right? So how would we do that with generic type parameters? Now let's first implement here the mixup function. And again, the convention is just the more generic type parameters you are declaring, you just go further in the alphabet. So T, U, V, W, all right? And as you can see, as a first argument, we are taking P1. Now let's take ownership. We don't care because we don't use P1 after this point, meaning we can take ownership and we don't have to use a reference to self here. And as an argument here, we want P2, meaning a point with generic type parameters we are declaring here. And the return type will be a point with a generic type parameter t and a generic type parameter of w, and you will see why that is. So then what we want to do is creating here a new instance, and we provide here x, which should be of self, because self here refers to p1, right? So we want self and we want the x value, and y should take it from the second argument, the P1 over here, and we want the Y field. So let me actually annotate that as other. Right, we take here another point instance, and this would refer to P2 because we are passing P2 over here to this mix-up method. So we take from P2 the Y field, and then we are returning this instance, meaning P3 will then look something like that, right? So let me annotate the type. We would have a point with the X value of P1 and I32 and a character type of P2, the Y field, right? And that is what we will get. Let's first see if this even compiles. And this is compiling. Now, as you can see, we have here a lot of generic type parameters. So when we take a look at the mix-up method, as you can see, we are here declaring new generic type parameters because we want to define over here that the types self, and self again refers to the instance over here, P1, that these types are different from the types provided on the second argument, the instance of P2, right? If we compare it together, then P1 instance holds different types than the P2 instance. So we need new generic type parameters because T and U are for this P1 instance, and the other, the argument we are here providing, P2, will hold different types, right? And as you can see, we are then taking from P1 the X field, and from P2 we take the Y field. And this would be the return type, a point with T, this is from P1 X, and W, this would be the second type from the P2 point. All right. Fix the errors to make the code work. As you can see, we have here a struct point which has two fields which are generic over its type. And we implement over here a method for the point struct over here. Now this method over here is in fact only implemented for a struct point that holds F32 types of fields, right? So if we would pass floats, then this method is not implemented for a point. So this is only implemented for point with a concrete type of F32. Now, then over here we are calling on the fields X, the power integer method. And let's see that in the Rust documentation. So as you can see, the power integer method over here is actually implemented for F64 types, right? So self in this case must be of type F64. As you can see over here, we have X which holds an F64 type, so we can call this method on X, right? Again, this is a method and not a function. So the problem over here is that self in this case would be F32, which is not the right type. So let's change that, F64. And that means self over here would be of type F64, the concrete type we are providing here. And then, of course, the return type would be F64, right? Because we are here performing an operation on two F64 types. Now, over here, of course, we have to provide floating point values, right? Because again, this method is only implemented for a point that holds as fields F64 types, like that. Right. And then we can use this method as defined in the standard library. And of course, over here, we just have to annotate one type, right? Because we only have one generic type parameter. And as you can see, this is compiling, and I will see you next time. So I've told you that we will take a brief look at const generics, and I will just solve one exercise and leave it at that, because const generics is a more advanced topic and you don't need it that much in your everyday programming. So they're useful at some situations, but they are not that much used. So let's see an example over here. We have here a struct array. So we have here the struct array, which defines two generic type parameters, t and n. Now t is a generic type parameter and n over here is a const generic type parameter. And as you can see, each array struct holds a data field with an array of type t and n elements. All right. So when we look over here, we have an array, and I will now annotate this type of type array, right? This struct we have defined over here. We are holding three instances, as you can see, 1, 2, 3, three instances of this array struct, right? Like that. Now, I have told you that when we have generic type parameters, it becomes part of its annotation. So we have to annotate it over here too. In fact, we don't have to do that because it's usually inferred by the compiler, but I will do it right now. So this over here cares about the types in the array the data field holds. So as you can see, we have here integers, we have here floats, and over here we again have integers. And what that means is that in this array over here, these actually should all hold the same type, because we have to provide here a concrete type, right, for t, and that means this data field over here will then hold in its array this type. So in this case we will do I32, and we need to provide it a constant, meaning for the length of the array. In this case we define 3, all right? And what that means is that the arrays inside the data field of these instances must be of I32 type, and they must have a length of 3, right? So we can't use floats here, we have to use I32. And over here we need to add another element. Now they can't be different. For example, let's do it like that. That is possible, but all of them over here must have the same type and the same amount of elements, because we are annotating that here, so it complies with the generic type parameter annotations here. Now let's create another array with floats. Now I want this to hold array instances of type F64, and let's do 2 elements. And I will pass here, let's say also 3. And that means inside here, let's first look at the outside array, at this array over here. So we want 3 elements of type array, this array struct. All right. So let's define that. Like that. As you can see, we have here 3 elements of type array. Now we define here for the generic type parameters that the data field should hold an array right, because this is defined over here in the array struct. So each data field should hold an array of F64, right, the T over here, of 2 elements, right. This is the const generic parameter. So we are passing here a constant and not a type. So in this case, the data field would have concrete types of F64 and 2 elements, right? So let's fill that out. Like that. As you can see, this is compiling because we are here complying with the generic type parameters. We have 3 array instances, right? And each array instance holds a data field with these types, F64, and they have to be 2 elements inside the array. Alright, see you in the next topic. We will now cover traits. So a trait is a set of methods that can be implemented for multiple types in order to provide common functionality and behavior between them. A trait consists only of method signatures, which then have to be implemented by the target type. It's similar to classes in other languages, but not quite the same. And it defines shared behavior in an abstract way. So let's see how that might look like. As you can see over here, we have 2 custom types, sheep and cow. Now we want to indicate that these are somewhat related. So over here we have created a trait Enum, which defines one method. Then over here we are implementing the animal trait for sheep and for cow. Now when we implement a trait for some type, then we have to implement all the methods the trait defines. So in this case, as you can see, in the trait animal, we only provide it with a function signature. And then the concrete types, for example, sheep and cow, will implement the method and its behavior. So as you can see, both sheep and cow then implement the animal trait, meaning they automatically implement the method, right? So both of them take a reference to its instance, for example, a sheep instance, and then just return the string over here. And the same thing for cow. Now there is also derivable traits, and we have seen that before. A trait can be automatically implemented for a struct or an enum by the Rust compiler. These are called derivable because they can be derived automatically. And the most common derivable traits are debug, allowing to output content via this debug notation, we have seen that. Clone, which enables a type to be duplicated with the clone method. Copy enables a type to be copied implicitly without requiring explicit clone method. And partially Q enables comparison. Now we can pass traits as parameters. So the notify function over here takes as an argument any type that implements the summary trait. Meaning we can ensure that the item argument over here implements the summarize method, right? If we provide here a type that didn't implement the summary trait, then it wouldn't have this summarize method. Traits can be used as parameters for functions. The function notify takes as an argument any type that has implemented the summary trait. Now there is also a concept called trait bounds, meaning if we declare over here a generic type parameter, we can define that the type over here must implement the summary trait. So the argument we pass to this notify function must implement the summary trait. And this is similar to the example using the impl summary, but more verbose. So as you can see, this would actually be exactly the same like we did over here. Trait bounds are declared like generics after the name of the function. And use trait bounds if you have lots of parameters to avoid this. So if we would have here an argument which takes a type that implements summary and another argument which again takes a type that implements summary, we can do it like that. So we define here a trait bound, meaning the generic type T must implement the summary trait. So both argument 1 and argument 2 take a reference to a type that implements the summary trait. And if you have big trait bounds, like for example this, we have here generic type parameter T, and we say here that the type T has to implement the display and the clone traits. And the generic type U has to implement the clone and the debug trait, right? And then over here, as you can see, the first argument must be of type T and the second one of type U, and we are taking references. So we can write that in a more concise way using a where clause, meaning after the return type in a function, we can use the where keyword and then over here define our trait bounds. And this over here is exactly the same as this. But instead of defining the trait bounds directly on the generic type parameter, we do it in a separate block. And we can also return from a function a type that implements a specific trait. So as you can see, the return dog function over here returns an instance of the dog struct, and because the animal trait over here has been implemented for dog, we can also define the return type as follows. We return here an instance of dog, meaning we return here a type that implements the animal trait, because as you can see, animal is implemented for the dog struct. Let's see exercise 1. Fill in the two impl blocks to make the code work. Don't modify the code in main. Now we have here a trait hello, defining two methods. Now over here you can see that we didn't only provide the function signature, but we implemented basically the whole method. Why is that? Because this is considered the default implementation, meaning any type that implements the hello trait automatically gets this default implementation of this method. So we don't have then to implement it manually. It will automatically get implemented for the type that implements the hello trait. But as you can see over here, we have a method which is here just a function signature. So we have to implement that manually. Then over here we have two structs, student and teacher, and we implement over here the hello trait for student and for teacher. So let's see, we have here an instance of student, and as you can see, this is just a struct that doesn't hold any values, right? So we instantiate it like that. But because we have here implemented hello for the student struct, that means we can then call upon it this method over here. As you can see, we call the say hi method on the S instance, and then it should return hi. Now we don't have to implement the say hi method over here again, like that. We don't have to do that because it's already implemented by default, right? But what we have to implement is the say something method, because as you can see, we are calling the say something method on the instance of S. And remember, when we implement a trait for a type, in this case student, we have to implement all the methods except the default implementation here. So let's actually take this and copy it over, because the function signature must be exactly the same like defined in the trait. And then over here we want the return to be I'm a good student. So let's return this string here. Like that. So when we call on an instance of student this say something method, then it will return I'm a good student. Now over here we are instantiating the teacher struct. And as you can see, we are calling the method on the T instance, and this should be the returned string. So as you can see, this is different from what is implemented in the default implementation. And that means we have to re-implement this say hi method for the teacher type. And the return string should be hi, I'm your new teacher. So as you can see, if a trait defines a default implementation, we can also overwrite the default implementation and provide another return value. And of course, because we have to implement this over here, I will copy that and I will implement it for the teacher type. So as you can see, when we call the say something method on an instance of teacher, then we should get back this string. So as you can see, we have then implemented the hello trait for our custom types student and teacher. Let's see if that compiles. And this is compiling. Derive. The compiler is capable of providing basic implementations for some traits via the derive attribute. For more info, please visit here. Let's see, over here we have a tuple struct centimeters, which holds a value of type F64. Now, as you can see, this struct here derives two traits, partial EQ and partial order, meaning the compiler will automatically implement these traits for our type centimeters. Now, partial EQ is for comparing equality and partial order is for ordering. So over here we have inches, and inches is a tuple struct that holds an I32 type, and it derives the debug trait, meaning we can print it out using the debug notation. And as you can see over here, we implement a method 2 centimeters for an instance of the inches type. So when we call this method on an instance of inches, then we will convert it to centimeters, right? So we here dereference self, meaning the instance of inches, and then we the structure over here, the inches, basically the value that the tuple struct inches holds. So this variable then will hold the value of the instance provided here. Okay, and then as you can see, we are multiplying inches by 2.54 to convert it to centimeters, and we are wrapping that, and we are returning that as an instance of centimeters, as you can see. So, add some attributes to make the code work. Don't modify other code. So as you can see over here, we are instantiating the seconds struct. So then we are printing it out using debug notation. So we have to derive over here the debug trait. Then we are here comparing for equality. So we have to derive the partial EQ trait. And over here we are checking if 1 second is bigger than 1 second. Meaning we need to implement the partial OR trait like that. And as you can see, we are here instantiating the inches struct, providing it a value of 12, right? This I32 type. And then we print it out, and let's check. Debug is implemented, so we can print it using debug notation. And over here we are instantiating the centimeter struct. As you can see, centimeters takes a value of F64. And over here we are comparing, as you can see over here, this foot instance holding an instance of inches with 12. So in the US, 12 inches equal 1 foot. And then we call the 2 centimeters method on it, meaning this will then return an instance of centimeters, right? So we are taking here inches 12, and that means 12 over here will get destructured, right? Here we have, here self would be inches 12, and we take it as an reference like that. So we destructure it like that, using the let keyword, the reference, because we want to take the value and not a reference, and then 12 will be put inside the inches variable. Then we are multiplying by 2.54 and returning an instance of centimeters. And that means we can then compare this over here with the meter, because the meter holds also the same type, namely the custom type centimeters over here, right? So both types would be here of type centimeters. And if this is smaller than this, then it will assign to this variable a string smaller, otherwise bigger. And these are string literals, by the way. And over here we are outputting the result of this compare. Let's see. And as you can see, this is compiling. So we are outputting here 1 second looks like seconds 1. As you can see, we can output this type over here seconds because we have derived the debug trait, meaning we can use debug notation. Then 1 foot equals inches 12. And over here this 1 foot is smaller than 1 meter. Operator. In Rust, many of the operators can be overloaded via traits. That is, some operators can be used to accomplish different tasks based on their input arguments. This is possible because operators are syntactic sugar for method call. Example, the plus operator in a plus b calls the add method, as in a add b. Over here, this would be a method. This add method is part of the add trait. Hence, the plus operator can be used by any implementer of the add trait. So, implement the function multiply to make the code work. As mentioned above, plus needs t to implement standard ops add trait. That's why we are here importing the ops module from standard library. So let's implement the multiply function. As you can see over here, we are providing 2 U8 integers to the multiply function. Now in the second call over here, we are providing float, means we need a generic type parameter like that. So this function takes 2 arguments, and it will return t, basically the same type of the provided arguments. And then over here, we basically just want to multiply a by b. Now, as you can see over here, we are using the operator for multiplications. And that means we have to ensure that the t over here, the type of the arguments that the multiply function takes, implements the mul trait. Now the mul trait, like the add trait over here, then knows that if both of the types of A and B implement the mul trait, it is possible to multiply these two together. So we can use here a trait bound, meaning the type T over here should implement the standard ops mul trait, because again this is just overloading and syntactic sugar for this call, right? So this actually would translate to this, and we have seen in the add over here that it would be A add B, right? These operators are just overloaded, so it's easier to use. And that's why we have to ensure that A, this argument here of type T, has actually implemented the mul method. And we make sure that this is the case when providing here a trait bound, meaning T must implement the mul trait, meaning then that T has implemented the mul method. Let's see. And we have here to also define that the output will be of type T, because as you can see, the mul trait over here has an associated type of output, so we have to define that. And we will take a look at associated types, but we have here to define that the output should of type T, that the output should be of type T, right? Let's see again. And this is working. Fix the errors, don't modify the code in main. So over here again we are using the ops module from the standard library. Then we have here two structs, foo and bar, and foobar and barfoo. The standard ops add trait is used to specify the functionality of the plus operator. Here we make add bar the trait for addition with a right hand side of type bar. The following block implements the operation foo plus bar should return barfoo. So if we use the plus operator with these two types over here, we should return this type, right? Foo plus bar should return foo bar. Now let's see the add trait. Now the add trait over here takes as default parameter RHS, standing for right hand side. If we don't provide anything to right hand side, then it will be self, meaning the type we implement the add trait on. And as you can see, we have an associated type here for the output. And over here, as you can see, add takes self and basically becomes the owner when called on an instance that implements the add trait. And right hand side is of type right hand side, which means by default it would be self. And this looks confusing, I know, but you will get it when we implement that over here. So as you can see, we are implementing from the ops module the add trait. So we can implement from the standard library traits for our custom types. And let's see. Again, when doing something like that, then the compiler will actually do something like that, right? It will call the add method. Now this over here is the type. Here would be an instance of foo, but just so you get the concept. And as you can see, we have here to define the right hand side, meaning the right hand side over here would be bar. and we are implementing the add trait for foo, right? Because we want the instance to be of type foo, so we implement it for foo. And we want the right hand side to be of type bar. Now if we wanted to add, for example, foo plus foo, then we could omit that, because you have seen that the default is self, right? So the default right hand side would be self, as you can see. So we can omit that, but that means both types must be the same. In this case, foo and foo, right? Because self over here refers to the type we are implement the trait for, right? But in this case it would be bar, right? Because the right hand side is different from the left hand side. And the output should be of type foobar. So and again, associated functions, we will cover that very soon. So over here we have to implement the add method, right? Because the add trait over here defines an add method, so we have to implement it. And that means we take self, and this is taking ownership of an instance of foo, right? And right hand side would be of type bar. Again, as you can see, foo would be the instance, then we call the add method upon the instance, and this argument should be of type bar, and then we return foobar. So in main, when we perform this over here, foo plus bar, we will get back foobar, right? So we have implemented the plus operator on our custom types. Now let's do the same for minus sign, but in this case foo minus bar would be bar foo. So let's see. As you can see, this would be the struct we want to return, bar foo. So minus sign is actually the same, but implementing the sub trait. So we would have foo sub bar, right? This would be the sub method defined in this sub trait. As you can see, we are here implementing the sub trait from the ops module for bar. Now again, we want actually to implement it for foo, because here we call foo sub bar, meaning we would implement it for the foo instance. Because self over here refers to the instance the method is called upon, right? So the sub will be called upon self, meaning we have to implement it for foo. And the right hand side would be bar. Now we want to return bar foo, that's true. And over here, as you can see, the sub method is implemented, but as right hand side the type should be bar, right? This is the right hand side of the operation. And we are returning bar foo. So when we do this foo minus bar, we will get back bar foo. So we have overloaded this operator. And of course, to do assert EQ here, because this is a custom type, we have to implement the partial EQ trait. So let's do that. And we also have to implement the debug trait. As you can see, this is compiling, meaning when we use our custom types with these operators, they will return a custom type. And we can do that by implementing from the ops module, from the standard library, the appropriate traits for our custom types. Use trait as function parameters. Instead of a concrete type for the item parameter, we specify the impl keyword and the trait name. This parameter accepts any type that implements the specified trait. As you can see, we have here a trait summary. Implement function summary to make the code work. Fix the errors without removing any code line. So over here we have a struct post with 3 fields of type string. And we implement over here the summary trait for the post struct. Meaning we have to implement the defined method in the trait. So we implement it for post like this. As you can see, we are accessing from the instance. Remember, this is a method, so it refers to an instance it is called upon, right? So we access the fields self.title and self.author, right? Then over here we have a struct Weibo with 2 fields of type string. Then we implement the summary trait for Weibo, and we then have to implement the method from the trait. Alright, because again, when we implement a trait for a type, we have to implement its methods. So this over here accesses the username and contact field and prints it out. Now here we have an instance of post, and here we have an instance of Weibo. So as you can see, we are here calling the summary function with an argument of post and Weibo. So we have to implement this summary function below. Let's do that. Now, as an argument, it takes in the first call post and in the second call Weibo, right? 2 different types. But now think about it. What do they share in common? Right, they implement the summary trait, right? We have implemented it for post and for Weibo. So we can define over here that the argument provided must be a type that implements the summary trait. And we do it like that. And then inside the function body, we want to take this argument. And again, A is an instance of a type that implements the summary trait. So we are taking A and we call upon it the summarize method. Meaning, in the first one, it will be post.summarize. Now post over here is of type post, meaning we go to post, and as you can see, this would be the summarize method. As you can see, self would refer to the instance, in this case post, this instance over here. So then the summarize method will return a string. So let's actually assign this to a variable. This would then hold this string and we can then output it. Like that. Let's see. And of course, when we are calling the summary method with an instance, then we can't use the instance again. So let's define here that it should take a reference, right? And as you can see, this is compiling. Now what we can do over here, and this would be exactly the same, we can define here a generic type parameter t, and here define that it should implement summary, right? So we define here the type t, and it should be a type that must implement summary, and then we can write it like that. So A should then be a reference of type T, which implements summary trait. Let's see. As you can see, exactly the same thing. Returning types that implement traits. We can also use the impl trait syntax in the return position to return a value of some type that implements a trait. However, you can only use impl trait if you are returning a single type. Use trait objects instead when you really need to return several types. So over here we have two custom types, sheep and cow. And we have one trait animal, which has one method. So over here we are then implementing the animal trait for both of these custom types. And as you can see, when we implement a trait for a concrete type, then we have to implement the given method. So over here we have a function random animal. It takes a random number and then looks if the random number is less than 0.5, it will return a sheep instance. Otherwise it will return a cow instance. Now over here the return type of the function would be a type that implements the animal trait, which both of them do. And as you can see in main we have here our random number, and we call this random number on the random animal function. So let's for now assume that this really is random, okay? So that means that when this is passed over here, it could either be a sheep or a cow to be returned here. But the problem here is that the return type in a function must be of known fixed size at compile time, which in this case sheep might be bigger than cow, or cow might be bigger than sheep. So the exact size is not known at compile time. So when we do that, this doesn't work. And to make that work, we have to know about trait objects. So let's see. So trait objects. Using impl trait doesn't work when returning multiple types. Different implementations of a trait probably use different amounts of memory, but sizes of types must be known at compile time. In this case, a trait object can be used. A trait object is essentially a pointer to any type that implements the given trait, where the precise type can only be known at runtime. So over here, for example, we have a trait animal and two custom types, dog and cat. Then we implement the trait animal for both of these types. And as you can see, we have a function return animal. It takes a string, and if this string is dog, then it returns a dog instance. Now if it returns cat, then it returns a cat instance. But as you can see, we are here providing a reference to the instance and not the instance itself. Because when we return a reference to a type that implements the animal trait, it means that the size of this type is known at compile time. because remember, a reference is a pointer, and the size of a pointer is known at compile time, meaning it's of type usize, and usize is 8 bytes on a 64-bit computer. So the size of the return type is known. It's just a pointer sized type. So the size of the return type is known at compile time. It's of size usize, right? Because we are here returning a pointer, meaning it doesn't matter if dog is bigger than cat or otherwise, it's always the same size, because pointers have a fixed size at compile time. And that is how we would solve this problem. So again, here we have a function which returns a type that implements the animal trait. This could be dog or cat. As the trait object is behind a pointer, the size is known at compile time, which is usize, the size of a pointer. This allows for more flexible code, as the exact return type doesn't have to be known at compile time as long as the size is fixed. So we don't care anymore about the size of dog and cat because they're behind a pointer. And to understand what's going on, you have to know about static and dynamic dispatch. So let's first look at static dispatch. Static dispatch resolves method calls at compile time. The compiler will generate function code for each concrete type that implements the trait. It calls the appropriate function based on concrete types. It's faster and more efficient than dynamic dispatch, but it doesn't provide great flexibility. So we have here the trait animal holding one method, say hi. Then we have dog and cat, and we implement the animal trait for dog and for cat. Now, as you can see, when we create an instance from dog and from cat and call the say hi method on it, because as you can see, every type that implements the animal trait must have this method. And when we then run this program, then the compiler will actually generate methods for each concrete type, in this case dog or cat, because then the say hi method we are calling here on the dog and cat instance is known at compile time. So the compiler then knows when we call the method on the dog or cat instance which method has to be resolved for which type. So let's see dynamic dispatch. In dynamic dispatch, the specific methods to be called is determined at runtime and not at compile time like static dispatch. It works by creating a reference or smart pointer to a trait object using reference_din or box_din. When trait object is created, the compiler will build a vtable for that trait. A vtable is a table that contains a pointer to the implementation of each method in the trait for the specific type of the object that the reference points to. The compiler will do a lookup in a vtable to determine which method should be called for which type that implements the given trait. And this lookup will cause overhead but allows for more flexible code. So exactly because of this lookup, static dispatch is faster than dynamic dispatch. But on the other hand, dynamic dispatch allows for more flexibility. So let's see how that might look like. As you remember, with box we are able to allocate a type to heap memory, meaning the type will then get allocated, for example, a i32 integer, like 7, will get allocated to the heap, and we will then get back a pointer. This is what box is for, and we have seen examples of that. Now, when we use box with a trait object, it means that the type that implements the specific trait will get allocated in heap memory. Get back a pointer to the location where the type that implements the specific trait was allocated, and we will get back a v pointer, right? This is happening when dynamically dispatching. So the v pointer points to the v table, and in the v table there are certain fields. Now, there is also a field called methods, and this is where all the methods for the concrete type over here are located. Meaning, at runtime, the compiler will check this vtable and see in the methods over here which methods are implemented for the concrete type that was allocated in heap memory. So let's see an example. So we have over here a trait animal, and we have two custom types, cat and dog, and we implement this method defined in the trait for both of our types, right? Because when we implement a trait for a custom type, we have to implement all of its defined methods. So over here we have seen we have a random animal function which takes a random number, and based on this conditional it will either output a cat instance or a dog instance. So then when we call this random animal function with the random number, and for now just assume that this is really a random number, that means the compiler first of all cannot determine the size of the type which gets returned, and this is of type that implements the animal trait, right? Cat and dog both implement the trait, but we can't know the exact size at compile time, meaning we put it behind a pointer, in this case a box, but a reference would also be possible, and that means the size is now known, right? It's the size of a pointer, basically U size, 8 bytes in a 64-bit computer. But we have another problem. Over here, the return value will be a type that implements the animal trait. But at compile time, when we call the noise method over here, the compiler doesn't know which of these types get returned. So the compiler can't know which method he has to call. Is it for the implementation on cat or dog, right? So this is why we use dynamic dispatch, because that means this over here will get decided at runtime. So again, the compiler will then look up in this v table over here using the v pointer, which points to the v table stored in heap memory. And then it will check for the concrete type that got allocated on heap memory the specific methods. So for example, again, this is happening at runtime. We return a cat, then the compiler will see that the type over here, which is concrete, is cat. So it will see in the v table the methods implemented for the concrete type of cat. I hope this makes sense. So this is why we need dynamic dispatch here. Static dispatch doesn't work, because again, the output of this function is random. So let's see box. Box is a smart pointer that allows to store data on the heap rather than the stack. And you can use box when you have a type whose size can't be known at compile time. It returns a pointer to the data stored on the heap. So what's the difference between a reference and a box? In terms of memory, a box allocates the data on the heap and owns it. It's also responsible for deallocating when the value goes out of scope, and the reference only points to a value that is already in memory, meaning the reference points to something that is already there, while a box allocates, and the reference also doesn't own anything, it just points to something. In terms of lifetimes, a box can be passed across scopes, while a reference has limited lifetime, and we will cover lifetimes very soon. A box can be cloned and a reference cannot, and a box can also be used in pattern matching. So we have left off over here, and I hope by now you know that this over here is not possible. We cannot return a type which implements the animal trait because these could vary in size. And again, over here we return a type that implements the animal trait. Now if this over here would be really a random number, then we don't know exactly at compile time which type gets returned, meaning we can't use here the noise method, because the compiler can impossibly know at compile time, of course, which method he has to call. Is it this one or is it this one, right? And for that we will use dynamic dispatch. So again, we can put this in a box and using here the din keyword, meaning we want to go with dynamic dispatch here. And that means we have to box these instances. So now the return type over here is known at compile time, meaning we can annotate it. It would be a box which holds a type that implements the animal trait, and this is using dynamic dispatch, meaning we then can call this noise method on this instance here, because the compiler can check for this noise method at runtime and not at compile time, meaning it is determined which of these will get called at runtime when the program is running. Let's see. And this is working. Trait bound. The impl trait syntax works for straightforward cases, but is actually syntax sugar for a longer form, which is called a trait bound. When working with generics, the type parameters often must use traits as bounds to stipulate what functionality a type implements. So over here we are calling the sum function with two arguments. In this case, two i32 arguments. And as you can see, we could also call this with floats because we have here defined the t generic type parameter. So as you notice, x and y must be of the same type t, and the type will be t which gets returned. And all we do over here is adding x plus y. Now again, to use this plus operator here, we must define that t over here is a type that implements the add trait. Because remember, this would actually translate to this. So it's critical that x implements the add trait, right? And we also have to define over here the associated type output to be of type t. Let's see. this is compiling. Let's actually call the function and print out the result. So as you can see, the output would be 10. And we can call it with floats, right? So let's see exercise 8, fix the errors. As you can see, we have a pair struct which has two fields holding values of type T, meaning they are generic. And then we have an implementation block for pair, and we define here an associated function. And this is not a method because it doesn't have self as parameter. Now over here we are instantiating a new pair. And remember, self over here, uppercase S, refers to the type of the implementation block, meaning pair. And then we return this instance. So if I write pair here, it would be the same thing. Then over here we have another implementation block for the type pair. And as you can see, we define here that T over here should implement the debug and partial OR. So the type T over here, the type of the two fields, must implement debug and partial OR. Then over here we are defining a method compare display, which takes a reference to an instance of pair. And then checking over here, is the value of the X field bigger than or equal to the value of the Y field? If that is the case, then self.x will get printed out using debug notation. That is why we need T to implement the debug trait. Otherwise, we print out the value of the Y field. So as you can see over here, we have a custom type unit that holds an i32 integer. Now over here we are instantiating a pair struct. And as you can see, we are passing here as concrete values for X and Y fields the unit type, our custom type. And over here it holds 1 and here 3, right? An i32. The type annotation for that would be, we would have a pair instance, and T over here would be unit, right? Because X and Y hold a type of unit. So T over here will be unit. Now remember, we have over here an associated function. So let's actually use that to instantiate a pair. As you can see, this is exactly the same thing as this, but here we are using the new associated function that got implemented on the pair type. So I can delete that. And again, when we call on this instance the compare display method, then we would have an error, because as for now, doesn't implement the debug and partial order traits. So we have to derive them. And by the way, we also need the partial EQ trait. And that's because we are here checking for equality. Alright, so we need partial equality. And because we have now derived these traits for this type, it means unit implements debug, partial ord and partial EQ, meaning we can over here compare for equality and ordering, and we can print the field out using debug notation. Let's see. And this is running. So the largest member is Y unit 2. So we have here a pair with an X field of unit 1 and a Y field of unit 2. And then the compare display method will give us back unit 2, right? Because the Y field holds a value that is bigger than the X field. Compare these two, because this is a custom type, is only possible because we have derived these traits. Alright, see you in the next topic. So before doing more exercises on trait objects, I want to cover associated types. Now an associated type allows to specify a type that is associated with the trait. When implementing the trait for a specific type, we have to specify the concrete type. It's basically a type placeholder that the trait methods can use in their signature. And it's similar to generic types, but they are more flexible because they allow a trait to have different associated types for different implementing types. Let's see an example. We have here the myTrait, and this has an associated type called myType. And as you can see, we can then use this associated type over here in the methods we are defining in the trait. So we here, for example, define that the return type should be of type myType. Meaning when we implement this trait over here for a concrete type, like for example myStruct, then we have to define the concrete type. As you can see, when we implement the myTrait for myStruct, we define here that myType should be I32. And as you can see, this method over here will then return an I32 type. And this is defined over here. And we can access the associated type using self, uppercase, double colon, and the name of the associated type. Now again, self here stands for the type we are implementing this trait for. So in this case, myStruct. Alright, let's do some more exercises practicing trait objects. As you can see, we have here a trait bird that has one method. Then we have here two custom types, duck and swan. So let's see, for duck we have an implementation block, and here we define a method, and this method takes a reference to the instance and prints out something. And for swan we also implement a method. Now notice, this has nothing to do with the trait. These are methods that are defined directly on the struct, right? So here we define a method fly, which again takes a reference to the instance and prints out something. Now over here we are implementing the bird trait for duck and swan, meaning we have to implement the method defined by the trait. So as you can see, this quack method we have to implement for both types. Then over here we want to instantiate a duck. So we then can call on this duck instance the swim method. So this will then get executed. Then over here we call the hatch a bird function with an argument of 2. And over here we call the hatch a bird function again with an argument of 1. So as you can see, when we provide 2, we want over here a duck. When we provide 1, we want over here a swan. And I see that because of the output when calling the quack method. So let's implement this function. We have seen that the function takes as an argument an integer. So let's call the argument species and let's define it as U8. Now I will keep the return type open. We will see that then. So let's see, when we get 1, let's actually match the species argument. When we get back 1, we want to return a swan. Right? If we get here for the argument a2, we want to return a duck instance. And because we have to handle all the cases, I will just panic in case anything else has been passed. So over here, what would be the return type? Now think about it. When calling this function over here, we have to provide the return type. Now again, the return type has to be of known fixed size at compile time. Now over here, we don't know what will get actually returned at compile time, right? Especially if this argument over here would be something that is generated at runtime, meaning we don't know the exact size, because the swan struct could be larger in size than the duck struct or otherwise. So we have actually seen the solution. We need to box the return type, and we over here define that it should be dynamically dispatched, and that means we have to box these concrete values here. And now we are good to go, because also another problem would be that in a match every return type has to be of the same type. Now again, over here the function could sometimes return a swan or sometimes a duck, right, depending on the argument. And when we do it like that, we actually return a type of box, right? So they have all the same return type. Now again, because we are here using dynamic dispatch, we have to put it behind a kind of pointer. And that means over here we will get a box holding a trait object. And the trait object in this case is bird. So that means, and we have seen that the compiler will then allocate the concrete type, for example over here duck, in the heap memory, and will create a v table with all the methods. Because when we call over here the quack method on bird, then at this exact point dynamic dispatch happens, because it is not known at compile time which concrete type got returned here. This will be determined at runtime. So at runtime the compiler will check the v table and see the right, and will execute the right method call, right? In this case it would be for duck. So the compiler will look this method up in the v table for the duck type, which has been allocated in heap memory, and we got. And notice something over here. When we return a trait object, the trait object actually only implements the methods from the trait, in this case bird, right? So we then can't call, because we have here a trait object, we can't call a method directly defined on the type. So for example, this swim method is not in the vtable that the compiler creates. I hope you see that, because again we are returning a trait object, meaning in the vtable are only the methods from the trait. So over here, because we have created an instance on the concrete type, we can call the swim method. But over here, because we have a trait object, we can only call methods from the trait. Let's see. And as you can see, this is compiling. Array with trait objects. Again, we have the bird trait with the same method. Then we have duck and swan. And as you can see, these are methods that are implemented directly on the concrete type. Then over here, again, implementing the bird trait for duck and swan. We have seen that. Fill in the blank to make the code work. So over here, we want to have an array, because we are here iterating over this bird's variable, meaning we want to iterate over an array. Now let's first annotate. We want over here an array of birds, right? So we want a type that implements the bird trait, meaning in this case duck and swan. And this time I will use a reference instead of a box. So we define over here that we want an array holding a type that implements the bird trait and is dynamically dispatched. Alright, and again, because using dynamic dispatch requires that we put it behind some kind of pointer, either box or a reference. Now in this array, let's say we want to have two elements, one duck and one swan. So let's provide here the instances. And again, we have to put that behind a pointer, so the size is known. So the size is known at compile time, because remember, the size of the elements in an array must be known at compile time. In this case, it would be uSize, the size of a pointer. Now then, we want over here to iterate over these elements here. And then, as you can see, for each element, we are calling on it the quack method. Now again, because this over here is happening at runtime, the quack method will be determined at runtime which one to run here, for duck or for swan. Alright, let's see. And this is compiling. Now over, and here we have the same thing. Bird.fly, the method we have directly implemented on the type, isn't available, because in a trait object over here, only the methods from the actual trait bird are in the vtable. Other methods won't get into the vtable, and so the compiler cannot look it up at runtime. Referenced in and boxed in. So we have here a trait draw, which has one method, and we implement the draw trait for U8 and F64. As you can see, we can implement our own custom traits for types in the standard library. And all this does over here is it will take a reference of the instance and it will output the value. Now in the newer version of Rust, we don't have to dereference self here. This is happening automatically. Like that. And for F64, the same thing. Now as you can see, we have here an F64 and an U8. Basically the types that implement this draw trait. Then over here we are calling the function draw with box. And as you can see, this function over here expects a trait object of the draw trait. And this trait object should be boxed. Alright, and then it is calling the draw method. Again, the compiler will then look in the vtable and will execute the appropriate method at runtime. So let's pass the argument for the draw with box function, and in this case we want to draw x, so let's pass it x. And of course this has to be boxed, right? Like this. Now over here we want to draw y, and this time we are passing a reference, meaning we over here expect a reference to a trait object that implements the draw trait. Alright, and then we are calling the draw method again, this time on y. Let's see. And this is compiling. Let's see exercise 4. We have a trait foo which has one method. Then we implement foo for U8 and string types. And as you can see, we can implement our own traits on types that are defined in the standard library. So in this case U8 and string. Then over here in main we have a variable x holding a U8 and y holding a string. Basically the types we are implementing foo for, right? And let's see now the function call static dispatch. So we pass here x, the U8 type, and this should be statically dispatched. So let's implement this function. Implement below with generics. So we need here a generic type parameter, and we define here a trait bound, meaning we want t to implement the foo trait, right? Because we want the argument to be of type t. So it's important that we define here the trait bound, because we call this function only with arguments that implement the foo trait. And we are defining that in order to be able to call the method on it. Basically this method defined here, right? Because then we can pass types of U8 and string to this function, and it can call the method because the foo trait is implemented for this type. Any other type that doesn't implement the foo trait won't be allowed to be passed to this function. So this is static dispatch, because the compiler at compile time will actually expand this code and create a function for the concrete types. So in this case we are passing U8 to this function. So the compiler will create a function like this, right? And then we'll call it. And this is happening at compile time, meaning the compiler will fill in the concrete types over here. And then of course the compiler will know when we do a method call, which method over here it should call, right? And static dispatch is usually a lot faster than dynamic dispatch because you don't have to do a lookup. It's everything in the binary itself. But when you have to do a lookup, you have to follow a pointer to heap memory and then get the data from this memory location, which is more expensive. So let's see dynamic dispatch in this case. And we use dynamic dispatch because sometimes it's just not possible to use static dispatch, right? When the size of the returned type cannot be known at compile time, then we use dynamic dispatch. And let's see how that looks like. So over here, we are passing a reference to y. So we are passing here a reference to a string. Now, as an argument over here, we want a reference, right? That's what we are passing to a trait object, implementing the foo trait, all right? And again, because this is dynamic dispatch, so this happens at runtime, it must be behind a pointer, so the size is known at compile time, because a pointer is always of size usize. We have covered that. And then we call the method on the argument, right? The difference is that over here, this will then be determined at runtime, which method over here to be called, right? Because the compiler will then do a lookup in the v table at runtime and then determine for which type the method should be called. Let's see. This is compiling. Object save. You can only make object save traits into trait objects. A trait is object save if all the methods defined in the trait have the following properties. The return type isn't self and there are no generic type parameters. So let's see exercise 5. Use at least 2 approaches to make it work. Don't add, remove any code line. So I think we will go first with static dispatch because it's easier. So I will remove this box here. And let's see, we have a trait here defining one method. Now this defines that it takes a reference to a self, meaning a reference to an instance of my trait, and it returns self, where self over here refers to the type for which the my trait is implemented. So in this case, for example, over here, my trait is implemented for u32, meaning we implement this method over here, and self over here would refer to u32, right? We can write it either way. And u32 and string implement my trait. Alright, so they both implement the f method. Then over here we have a function that takes a trait object. Now in this case we want to use static dispatch, so we define here a generic type, right? Because we are calling it with u32 and a string. Now we want to ensure that t, this type, implements my trait, so we can be sure that it implements this f method. So this is called trait bound, and this makes sure that t implements my trait. So we then can call the f method on the provided argument here, which is of type t. And that's basically it. We have implemented the static dispatch for this function over here. And what then will happen is when we call this function, the Rust compiler will take this generic function here and it will provide it with concrete types. And it will provide it with concrete types. So in this case, U32, right? We are passing it U32. And we forgot to define the return type. So the return type over here would be the return type of the f method. Now in this case, it would be the type, right? So if we are calling it, if we are calling the f method on an U32, then the return type will be U32. If we call it on a string, then the return type will be string. So again, we pass here t, right? Because the type we are passing, for example, U32, will be the return type of this function, U32. And that in case means that the return type of this function over here will be U32, right? And then the same thing happens for a string. So the compiler will actually put into these generic type parameters concrete types. And that means when we are using static dispatch, these method calls here are known at compile time. So the compiler knows if you're passing a U32 type, then it will call the f method from the U32 implementation of my trait, right? And in case of string, then the compiler will know that the f method can be found in the my trait implementation of string, right? So everything here is known at compile time, and also the size is fixed. And this is working. Now we want here to now use dynamic dispatch. So we solve it in two approaches. So before we can even use this trait object over here, we have to make the trait itself object safe. And we do that when the return type isn't self and there are no generic type parameters. So we cannot define here self. We have to provide it concrete types. Now in this case, we want the f method to return a trait object, meaning we return a pointer that points to the type that implements my trait. All right. And over here, because we are taking here this function signature and implement it for each type we implement the my trait for. So as you can see, the return type must implement the my trait and it has to be boxed. So we have to box this over here. Turn over here a U32, right? Which implements the my trait, and over here a string. Which also implements my trait. So as you can see, we got rid of self because again, at compile time, the return type size has to be known. That's why we are putting it behind a box. Now, again, the return type of this function would be the return type of the method calls. In this case, it would be a boxed trait object, right? Let's see if this is compiling. And this is also compiling. Now I hope you see the difference here. When we pass here a trait object, basically a type, in this case U32, that implements the myTrade trait, then this method call will be determined at runtime. And that's why we have to put these behind pointers, so the size remains fixed and known at compile time. And again, use whenever possible static dispatch because it's faster and I guess easier to write, but dynamic dispatch has its advantages and you can use it for more flexibility in your code. Alright, see you in the next topic. So we have reached the topic of collection types, and string is also a collection type, meaning we are just repeating because we have covered strings, but I think these exercises are good for some repetitions. So string is a UTF-8 encoded growable string. It is the most common string type we used in daily development. It also has ownership over the string contents. So let's see, fill in the blanks and fix errors. Don't use toString, don't add, remove any code line. So as you can see over here, we want a string type because we are here modifying the string, meaning it has to be growable. So let's allocate this data over here on the heap. So we have now a string type. Now let's see the pushStir method. As you can see, this pushStir method is implemented on the string type, and it takes as a type for its argument a string literal. As you can see, we are calling it on a string and providing it an argument of a string literal. So we have to delete that because this would actually be a string, right? We want here a string literal, like that. And push is for pushing single characters. So we want to push here an exclamation mark. So S will then here match with this string literal. And as you can see, we are calling the move ownership function here, meaning this function will then take ownership of S, and that's not what we want because we are using here S again. So what we can do is just clone it. So the data passed to move ownership over here is actually cloned, right? It is copied on the heap memory, and that means we can still use S because S remains the owner of this data. Alright. Then a string is stored as a vector of bytes but guaranteed to always be a valid UTF-8 sequence. String is heap allocated, growable, and not null terminated. A string slice is a slice, basically a slice to U8 integers, because as you can see, this string type is a vector of U8 integers. That always points to a valid UTF-8 sequence and can be used to view into a string, just like a slice to T is a view into vector T. And we'll cover vectors after this topic. So fill in the blanks. We have here a string and we want to take a string slice from this string. Now the easiest method would be just to take a reference to S, which means we take a reference to a string type. And this can then be inferred by the compiler to a string slice. And the second way would be to call the sStir method on it. This will essentially do exactly the same thing. It will take this string S and we'll convert it to a string slice. Now over here we also want a string slice, but we want to provide a specific offset. We just want this data over here, and that means we take a reference to S and provide it here an offset from 0. We can omit the 0 on here until index 0, 1, 2, 3, 4 until index 4. Now we would provide here 5 because 5 is excluded, meaning we go from index 0 to 4. And over here, as you can see, we want to modify the string, holding then hello world, because we are pushing to it this exclamation mark. As you can see, we want it hello world and with an exclamation mark. So what we can do is taking S over here as mutable reference. So this would then hold a mutable reference to a string. Let's see. And this is compiling. Now notice over here we could also take ownership of S, meaning slice3 will hold a string, because we are not using S after this point. So slice3 can be the owner of S, but in this case we have to make the variable mutable. And this is also working. Question: how many heap allocations are happening here? So we have here a string, and when we create a string type, then the data that is provided is allocated in heap memory. So this would be the first allocation. Then over here we are taking from this string over here a reference, meaning a string slice. And remember, a string slice is just a view into some data. So we are just going to this location and checking what's in there. So no allocation is happening. And over here we are taking this string slice and convert it to a string, meaning a heap allocation is happening over here, right? Because we are taking this string slice holding this, and then we allocate this into the heap once more, because we are calling this toString method. Let's see, indexing. So we have a string here, and we want to index into the first element. So slice1 should then hold H. So we want a string slice. So we take a reference to S and provide it the offset from 0 to 1, where 1 is excluded, meaning we just take the first character. And that is because H only takes 1 byte in UTF-8 format. So ASCII characters in strings usually take 1 byte, while these Unicode characters over here take 3 bytes. So when we take a string slice here, we want to access this character. Now for that we have to provide the right offset. So we go from 0, 1, 2, 3, 4, 5, 6, 7, starting at index 7, and as you can see, these Unicode characters hold 3 bytes, meaning we must provide here an offset of 10. 10 is excluded, meaning we go from 7, 8, 9, 3 bytes. Iterate through all chars in S. So to iterate over characters in a string type, we use the chars method. But that will actually just return the char we are iterating over. But as you can see, we want here as return type a tuple which holds the index and the actual character. So we can use here the enumerate method. And enumerate will return a tuple with the index and the specific character. So in the first iteration we would have 0 and age, right? The index and the character. So here we are checking if the index over here is 7, then the variable c should hold this character, right? Let's see. And this is compiling. Now there is a crate called UTF-8 slice. You can import it into your project, and this then allows you to slice into a string, not using bytes as offsets, but just indexing into the individual characters. So over here we provide an offset from 4 to 5, meaning we want the character at index 4. So we don't have to worry about the byte size of this symbol. Then fill in the blanks. We have here a string. Now we have seen that a string is actually a vector holding U8 integers. And as you can see, we have here some bytes in a vector. So this vector holds U8 integers, right? And that means these are bytes that can be converted to ASCII characters. So in this case, these over here would translate to hello. Alright? If you look up this code over here in the ASCII table, then we will find that this is represented for the character age, and this ELLO. So we want to turn a bytes vector like this into a string. So we want a string here. So let's see this method here. So in the documentation you can see that the string type implements a method from UTF-8. And this just takes a vector of bytes, and then we can call this associated function on the string type and provide it as an argument a vector of bytes. And this will then convert it to a string. So we can try it out. So first of all, we want to actually mutate the string here to hold the same data as this vector holds, namely hello. So we can do that by using push stir. And we push hello, meaning this string then holds hello. And then we can take this string type and call from UTF-8 method, providing it this vector. And this should then convert this vector of bytes into an actual string, meaning S and S1 will then hold the same value, namely a string hello. And of course this actually returns a result, so we have to unwrap it. And as you can see, this is compiling. So in fact, a string is just a vector of bytes, right? And we'll cover vectors very soon, and you will then see how this is actually stored in memory. So a string is made up of three components: a pointer to some bytes, a length, and a capacity. The pointer points to an internal buffer string uses to store its data. The length is the number of bytes currently stored in the buffer, always stored on the heap. And the capacity is the size of the buffer in bytes. As such, the length will always be less than or equal to the capacity. We have seen that the string type is a 3-word object holding a pointer to the actual data stored in heap memory, the length, which shows the length of the string, in this case 5, and the capacity. And the capacity, as you can see here, is the total amount of memory received from the allocator. So when we allocate a new string type on the heap, the allocator will find an empty spot and then will return a pointer to that location. Number 6, if a string has enough capacity, adding elements to it will not reallocate. So when we run this program over here, then we see the capacity of string S. Now over here we are initializing an empty string, meaning we have an empty string, so nothing gets allocated to heap memory. We still have a string object, but with a length of 0 and a capacity of 0. Then we print it out, as you can see, 0. Over here we are iterating 2 times, modifying this string. So in the first iteration, S will then hold hello. So it would have a length of 5, but when we print out the capacity, it will show 8. So we have a string object that points to this data with a length of 5 and a capacity of 8. Now this is the default behavior when we don't specify a capacity ourselves. So when the length exceeds the capacity, then Rust has to reallocate the data, meaning it has to find a new spot in heap memory that is big enough to hold the data, and then will return a pointer to the new location. So in this case, because we have modified the string, the length 5 exceeds the capacity 0. So it has to reallocate. Because remember, in heap memory, the data is allocated as contiguous block of bytes. Alright? And the default behavior is that the capacity will always double. So it starts from 1, then 2, 4, 8, 16, and so on. And that's the reason we have here a capacity of 8, even though we only need 5, right? This is a string of length 5. But because of the default behavior of the allocator, we will get back a capacity of 8. And then in the second iteration, we again push hello. Right? So we would have a length of 10. But as you can see, the capacity doubles. So 10 exceeds the length of 8, meaning the allocator will then find a new spot in heap memory to allocate this string over here of length 10, and it will then reserve 16 bytes of memory in heap memory. And so on. If we then exceed 16 bytes, then it will allocate to a location which holds 32, right? It always doubles. And this is when you let Rust allocate. So this is the default behavior. But as you can see, this might be expensive. So if you start with a capacity of 0 and then you modify the string multiple times, it means Rust has to reallocate your data. And that means it could potentially be expensive when you mutate this over here multiple times and a lot of reallocations are happening. So there is a function called withCapacity. And then we can define over here that we want an empty string, meaning the string length is 0, but we want a capacity of 25, meaning S is allocated in heap memory and there is enough space reserved for this data to hold 25 elements, right? So when we do that again, then as you can see, no reallocation has happened. We have only allocated the string one time in heap memory with a capacity of 25. Now, because the length doesn't exceed the capacity in any of these modifications of the string, it means that there is no need to reallocate the data, right? So when we print out the string s over here in the end, then as you can see, this is the string that s holds in the end, hello, hello. So we have here 10 elements, meaning there is no need for reallocation because a capacity of 25 can hold the string of this size, and this can make your program a lot faster. So let's see vectors. A vector is like an array but dynamically sized, meaning they can grow and shrink. It's allocated on the heap as contiguous block of memory. All elements in a vector have to have the same type. And there is a special macro vec which you can use to initialize a new vector. So all this time we've been dealing with an imposter. So in actuality, this string type is just a vector of UTF-8 bytes that gets allocated in heap memory. So as you can see, when we have the S1 variable over here, then again S1 won't hold the actual data, but a pointer to the data allocated in heap memory alongside a length and a capacity, meaning S1 is a 3-word object of size 24 bytes. Now, as you can see, this would be a vector allocated in heap memory that holds the UTF-8 bytes over here. Of course, in memory, this would be in binary, but as you can see, this then holds the character code for this character inside the string. So let's do some exercises. Vectors are resizable arrays. Like slices, their size is not known at compile time, but they can grow or shrink at any time. So over here we have a normal array holding 3 U8 elements. Now we can convert this array to a vector using the from associated function and then passing it the array, meaning V will then hold a vector of U8 elements. And here you can see the difference between an array and a vector. We don't provide here the length of the vector because the vector can actually grow or shrink, meaning it's dynamic in its size. Now the isVec function basically just checks if the provided argument is a vector. Then, as you can see, we are shadowing V and we are here initializing it with a vector of these elements. So as you can see, you can use the vec macro to quickly create a new vector like that. So this will then hold a vector of U8 elements. And by the way, you can either use square brackets or you can use parentheses. It's both exactly the same. Now, as you can see, here we are initializing V, or basically shadowing it, and then we are passing it to isVec, meaning ownership would be transferred. But we are using V here again, so let's clone this. And over here, as you can see, we are initializing v1 with the vec macro. Now we are passing to the vec macro the array. Now the vec macro over here won't convert it directly to a vector like this from associated function did. Instead, we would here have a vector holding this array. All right. I hope you can see the difference. Here we have a vector of U8 elements. Over here we have a vector holding an array of 3 U8 elements. So when we compare over here V and V1, they won't actually be the same, right? And again, let's do clone here, just so we can then reuse v1. Now what we can do over here to fix that is using the vec new, like that. And vec new basically will then create a new empty vector, meaning it would be an object with length of 0 and capacity of 0. Now over here we want to iterate over the elements in V. Let's take a reference here because we are using V again and we don't want this for loop to take ownership. Now all we want to do is pushing all the elements from V into V1. And because we are here iterating over references of elements, we have to dereference it. And by the way, we will take a look at that in much greater detail. So what we also have to do is making this v1 variable mutable, because when pushing to it, it has to be mutable. All right, let's see. And this is compiling. So in the end, v1 will hold a vector of u8 elements, meaning v and v1 are exactly the same. But remember, when you have an array, use the from associated function and not the vec macro, because it won't convert it directly to a vector. Instead, it will create a vector holding an array. A vec can be extended with extend method. So over here we have a vector. Let's say these are i32 values. And as you can see, we can pop, meaning removing the last element. So over here, the vector will then hold 1 and 2 because the last element got popped. Then we are pushing to it 3. Meaning we have a vector holding 1, 2, 3. Now over here again we are initializing an empty vector. Now as you can see, we want v1 and v2 to be exactly the same. So what we can do is using the extend method and providing it the v1 vector, meaning the elements and we have to pass here a reference, meaning the elements then from v1 will be put into v2. So again, v2 will then be a vector of i32 elements and they hold exactly the same data, right? It's basically copying the contents of a vector into another vector. Turn x into vec, fill in the blanks. So over here we have an array, and this array holds i32 types, and the size of the array would be 3. Then, as we've seen, we can use the from associated function. So we create a vector from this array, meaning v1 will then hold a vector of I32 types. Or what we also could do is calling the Enum method. And if a type implements from, then it will implement into, and we will take a look at that. So we then take this array over here and convert it into a vector of I32 values, right? So that means v1 and v2 will be exactly the same. Now converting a string into a vector. So the from trait over here is actually implemented for the vector type. So over here we have a string, and remember, basically a string is a vector of U8 elements. And then again we can call here into, right? Converting S into a vector of U8 elements. And then over here we have again a string, and we call the method into bytes, meaning v2 holds a vector of UTF-8 bytes, represented as U8. And this is actually exactly the same, so meaning v1 and v2 will be identical. Then over here we have a string literal, and we want to create a vector from this variable, meaning we again use the from associated function and provide it as an argument over here, meaning v3 will then hold a vector of U8 types, right? So v2 over here and v3 are identical. Iterators can be collected into vectors. So when we have here an array of 10 elements of value 0 and we put it into an iterator, we can then collect it into a vector. Alright, and we will see these methods over here, intuiter and collect, in much greater detail. Meaning v4 will then hold a vector of 10 times 0. Like that. Alright, let's see. And this is compiling. Fix the error and implement the code. So let's see, over here we have an array and we convert this array into a vector using the from associated function we have seen. So this will then hold a vector of I32 types. Alright. Now then we are iterating here 5 times and just print out each element at the specific index. Here we have to implement some code, and actually v in the end should hold a vector with these elements. So as you can see, we are starting with a vector holding 1, 2, 3, and we end with a vector 2, 3, 4, 5, 6. Now what we want to achieve here is we are adding 1 to each element, then we would have 2, 3 and 4. Now if we exceed the boundary over here, then we want actually to add the new element over here. Now let's see first in the for loop here, this would actually panic because we are trying to access indexes that are out of bounds. So over here we are iterating from 0 to 4, right? 5 excluded, but we have only 3 elements, meaning indexes 0 to 2. Now we can here use the get method. And we have seen this get method before. And this is generally safer because it will return an option. In this case, option I32, because we are dealing with I32 types here. And what we then can do over here, we want to actually manipulate this vector. So let's first access the elements. And as you can see, again, I use the get method because we want to actually see if the index is out of bounds or not. So in case it's not out of bounds, we would return a sum, right? The get method will return a sum and the actual value at that specific index. So if we found an element at the specific index over here, then we want to access the element and just add to it 1, right? So we are then taking the element over here. Let's see, for example, in the first iteration, I will be 0. Then we pass 0 to this get method, meaning we will get back some 1, right? So we'll get back some 1, meaning E over here will then hold a value of 1. Then we access this array at index 0, right? And what we want then to do is taking 1, E over here, and add to it 1, meaning then the first element in this vector has been modified to then hold 2. Now in the second iteration, it would be exactly the same thing. So I would be 1. We get over here the element at index 1 and E will then hold 2. And then over here, V at index 1 should then hold 2 plus 1, right? And we assign it, meaning in the modified vector, the second element will then hold 3. Now we do that again, and after we are out of boundaries, meaning we return a none here, and then we want to push to the vector the index plus 2, right? So for example, in the third iteration, I would be 3, right? This would be out of bounds. There is no index 3 here. So we get back a none. And then over here we push to V the index, in this case 3 plus 2, meaning we then get back 5, right? And let's see if this is actually working. Alright, and let's remove this type annotation because this would be of type usize because of the get method. Now, as you can see, when we print out here the output of the get method, we would get some 1, some 2, and some 3, and then 2 times none, because at iteration 3 and 4, we would get back none because there is no element in this index. And we are succeeding here because again we have 3 times sum here, and when we have a sum we just add 1 to the value, meaning we then have 2, 3 and 4, and then we will get back 2 times none, meaning we take the index and increment it by 2, pushing it to the vector, so we get 5 and 6. Slicing. A vec can be mutable. On the other hand, slices are read-only objects. To get a slice, use reference. In Rust, it's more common to pass slices as arguments rather than vectors when you just want to provide read access. The same goes for string and string slices. So over here we have a vector let's say I32. Then we are taking a slice from V over here, meaning this would then be a slice of I32 elements, right? And this would be the offset, meaning we would take from the first element to the last element. Out of bounds will cause a panic. You must use V length here. So as you can see, again, we are taking a string slice, but we are here out of bounds, right? Because this would iterate from 0 to 3 for excluded, and we have here only 0, 1, 2 indexes. So what we can do is using v.length, meaning we just iterate, meaning we provide an offset from 0, the first element, to v length, where the length here is excluded, meaning v length minus 1. Alright? Slices are read-only. Node slice and reference to vec are different. So as you can see, we take here a mutable reference to a vector, and then we can push to this vector over here the value 4. Now we have seen that slices are immutable. They are just a view into some data. So we can't use a slice to mutate the vector, right? So over here we want to have a slice of I32 elements, right? Like that. And we can remove the mute keyword over here because again we can't modify slices. So we have pushed to it 4, meaning when we take the slice we want to take also this last pushed element, right? And this is compiling. Capacity. The capacity of a vector is the amount of space allocated for any future elements that will be added onto the vector. This is not to be confused with the length of a vector, which specifies the number of actual elements within the vector. If a vector's length exceeds its capacity will automatically be increased, but its elements will have to be reallocated. For example, a vector with capacity 10 and length 0 would be an empty vector with space for 10 more elements. Pushing 10 or fewer elements onto the vector will not change its capacity or cause reallocation to occur. However, if the vector's length is increased to 11, it will have to reallocate, which can be slow. For this reason, it is recommended to use the withCapacity function whenever possible to specify how big the vector is expected to get. And this we have already covered with strings, but now let's see with vectors. So over here, as you can see, we are initializing an empty vector, but with a capacity of 10. So this object here would hold length of 0 and capacity of 10, meaning the actual elements inside vector are 0. There are no elements, but in heap memory there were 10 locations allocated for this data, right? The vector contains no items even though it has a capacity for more. So when we call the length method over here, we would get back 0, right? Because vec doesn't hold any values. But it has a capacity of 10 because we have defined that over here. These are all done without reallocating. So we are then pushing 10 times to the vector, right? Now this means vec here holds enough space that this is happening without reallocating the vector, right? So after pushing to the vector would be of length 10 and capacity 10, right? So the length must never exceed the capacity, otherwise a reallocation is happening, as you can see here, but this may make the vector reallocate. So we are pushing another element to the vector, meaning the length will be 11. This would exceed the capacity, meaning then this whole vector will be reallocated in heap memory. So when we have a length of 11, then the capacity will be at least 11, but it can be more, because we have seen that the default behavior when reallocating is that the capacity doubles. Fill in an appropriate value to make the 4 done without reallocating. So as you can see, we have here a vector we want to initialize with a certain capacity. Then we are pushing 100 times to this vector, meaning the length here will be 100. So what we want to do is we want here to initialize a vector with a capacity of 100, meaning we can push 100 times without this vector to be reallocated in heap memory. Store distinct types in vector. The elements in a vector must be the same type. For example, the code below will cause an error. So we have here integers and a float. This would cause an error because again, all of them have to be of the same type. But we can use enums or trait objects to store distinct types. So over here we again see the IP address enum we have seen before in the examples. Now fill in the blank. We want over here a vector that holds IP addresses, meaning at index 0 we want this variant here, and at index 1 we want this variant. Now we can use the vec macro for that. And then over here I just copy this variant and this over here, right? We would then have over here a vector holding types of IP address. And because this is a custom type, we have to actually implement partial EQ here. So I hope you get the concept. We have here a vector holding types of IP address, right? Then over here we have a trait IP address that defines one method display. And then we have two tuple structs, v4 and v6. We implement the IP address trait for v2 struct and v6 struct, meaning we have to implement the specific method. And all it does, it then basically prints out the value that is stored inside the struct. So fill in the blank. As you can see, we want here a vector holding trait objects. Remember, a trait object is boxed or put behind a reference. So over here we have a vector holding boxes, right? And the box holds a trait object, meaning again this is using dynamic dispatch, and we want here a type that implements the IP address trait, right? In this case v4 and v6 both are types that implement IP address. And as you can see, even though we are holding here different types, we can use it using here trait objects to store it in the same vector. typo. So, and then we are iterating over the vector, and for each element in here we just call the display method that has to be implemented, because we only have types in here that implement the IP address trait. And this is exactly where dynamic dispatch happens, and we have covered that. Let's take a look at HashMaps. So a HashMap is a data structure to store key value pairs. It's allocated on the heap as it is dynamically sized, meaning it can grow and shrink. It allows for efficient lookup, insertion and deletion of data. So when talking about time complexity, this means accessing and modifying elements, or entries as they are called in HashMaps, would be in the best case at constant time, meaning big O of 1. While in the worst case, if you have a lot of collisions, then it would be still linear time, which is still pretty fast, which means big O of n. Each key is hashed to a unique index in the underlying array. So, where vectors stores values by an integer index, HashMaps store values by key. It is a HashMap implemented with quadratic probing and SIMD lookup. By default, a HashMap uses a hashing algorithm selected to provide resistance against HashDOS attacks. So over here we find some information about the used algorithm for the HashMaps, but let's dive into the exercises. So the first thing is we actually have to use here a namespace. So we are basically importing from the collections module from the standard library the HashMap type. And when using vectors or strings, these are all in the prelude, meaning we don't have to import it, but a HashMap you have to basically import. So over here we are initializing an empty HashMap. Then we insert some entries, and again a HashMap holds entries of keys and values. Now important here is that all the keys must be of the same type and all of the values must be of the same type. So this over here would cause an error. And let's go with integers like that, and we annotate the HashMap like this, where key stands for key and v stands for value. So over here we use string literals as keys and I32 integers as values. Then, as you can see, we can access the entries in a HashMap by using again the get method, which returns an option. We have seen that before when dealing with vectors. So we provide the get method the name of the key, all right? And then we will get back the appropriate value, in this case 98, because we are accessing the entry sun phase, right? So we would get back here a sum, an option I32, right? This would be the return value, sum 98, and this would be the type, option I32. So we can check if the HashMap contains a certain key. So for example, if the HashMap contains the key Daniel, this would evaluate to true, meaning the code block here will be executed. And we can also index into a HashMap using bracket notation like that. So again, this would then hold the value of the entry Daniel, it would be 95, right? And this would be an I32. Again, notice the difference between indexing like that or indexing using the get method. We will get back the value here directly, while here we get back an option. So get is generally safer. And then over here we are removing Daniel from the hash map, right? So we can use the remove method and provide it the key of the entry we want to delete. Meaning after deleting Daniel over here, the length of the hash map would be 3, right? And we can also iterate over a hash map. So we provide it here, the variable holding the hash map, and then the return would be a tuple holding the key and the value. And then we just print out the key and the value. Let's see. Alright, and we would get back here an option holding a reference to I32. Alright. And over here too, we would get back a reference. This is what the get method will actually return. So as you can see, we are printing out the hash map. And this would be the key, for example, Ashley, and this would be the value, as you can see. Now notice that the order here is different from what is over there. And that's because a hash map is unordered. So the order won't be retained, all right? And of course we have only 3 elements here because we have removed the entry of Daniel. Then over here we have an array holding tuples, which holds a string literal and an integer, right? So we have an array of 3 elements, and each element is of type tuple, and inside the tuple is a string literal and an I32. Then over here we are initializing a new empty hash map. Then we iterate over here through the elements of this teams array. So for each element here, we insert into this empty hash map here the name over here, the string, and the value. All right. Implement team map2 in 2 ways. Tips: one of the approaches is to use collect method. So we can also implement a hash map from an array holding tuples of keys and values by using the hash map from function. So we provided here teams, and this will then directly convert this array holding tuples of keys and value pairs to a hash map. Meaning we then have a hash map holding string slice keys and I32 values. All right. And over here we would have the same thing. And then when we compare teams map 1 and teams map 2, they should be equal. Let's see. This is compiling. Now the second approach would be taking this teams array here, and we want to put it into an iterator, and again we will cover that, and then we call collect. Now when we call the collect method, it will basically collect the elements in this iterator into the type we have annotated here. Again, this would compile because we have in Teams map 2 the same keys and values as we have in Teams map 1. And as you can see, we don't need to write a full-blown for loop, we can just use some simple methods. Let's see, number 3, fill in the blanks. So type inference lets us omit an explicit type signature, which would be HashMap, string slice, and U8 in this example. So again, we don't have to annotate the types. I do it just to make things more clear, but we can leave it at that. Insert a key only if it doesn't already exist. So here we are accessing player stats, this empty hash map, and we call the entry. Now the entry checks if an entry exists with this specific key. And then we can call over here the OR_insert method, meaning if this entry doesn't exist, then we insert this key with this value. Meaning when we then access player stats with a key of health, we should get back 100, right? Because this has been inserted over here. Insert a key using a function that provides a new value only if it doesn't already exist. So again, we are trying to access player stats and look for an entry health. Now in this case, this exists, right? Because we have inserted it at that point. Now we can also use here the method OR_insert_with. The difference to OR_insert is that we don't provide a concrete value, but a function pointer. Meaning this function will then get executed. So this function only returns 42. So that means if the entry health doesn't exist, we insert this key with the value of 42. Now again, health exists, meaning when we access health, we will still get 100, right? Because this only executes if entry isn't found. Ensures a value is in the entry by inserting the default if empty, and returns a mutable reference to the value in the entry. So we are here checking for the entry health, and if it doesn't exist, we insert 50, right? So in this case, health already exists, meaning we would get back a mutable reference to the existing value 100, right? So this would be a mutable reference to 100. And because it is mutable, we can then modify the entry manually. So we can here decrement from health, which holds 100, we decrement 50, meaning the health will then hold 50, right? This health variable holds 50. Let's see. And this would be U8 in this case. And this is compiling. So as you can see, when we call entry, it will give us back a mutable reference to the value. If it already exists, to the existing value. If it doesn't exist, it will here create an entry, because this is what the OR_insert method does, and will return a mutable reference to the created value. And then we can modify this mutable reference, right? Requirements of HashMap key. Any type that implements the EQ and hash traits can be a key in HashMap. This includes bool, int, uint, string, and string slices. Note that F32 and F64 do not implement hash, likely because floating point precision errors would make using them as HashMap keys horribly error prone. All collection classes implement EQ and hash if their contained type also respectively implements EQ and hash. For example, a vec holding a type t will implement hash if t implements hash. So if the elements in a collection, for example a vector or a tuple or an array, implement the hash trait, then the collection itself will implement hash. Let's see, fix the errors tips derive is usually a good way to implement some common use traits. As you can see, we have here a struct Viking with two fields of type string. And here we have an associate function for Viking, just creating a new Viking instance from the arguments we provide. And as you can see, use a HashMap to store the Viking's health points. So we are creating here a HashMap from an array holding tuples of keys and values. Now notice we have here a HashMap, and the type of the keys would be the custom type Viking, alright? And the value would be I32. Use derived implementation to print the status of the Vikings. So here we are taking this created HashMap as a reference, and we would get back a tuple holding the key and the value, and then we just print out the key and the value here. So we have seen that in order a type can be used as a key in a HashMap, it has to implement EQ and hash. So let's implement that. Let's also use the partially Q over here and debug, so we can print out the key over here in debug notation. Let's see. And of course we have to implement the hash trait. And as you can see, it will print out each element in the hash map we have created. So we have now a hash map using as key our custom type Viking. As you can see, this would be the key and this would be the value of the hash map. Capacity. Like vectors, hash maps are growable, but hash maps can also shrink themselves when they have excess space. You can create a hash map with a certain capacity using hash map with capacity, or use hash map new to get a hash map with a default initial capacity. This is recommended. So like we did with strings and vectors, we can define when initializing an empty hash map the capacity, right? Ensuring that when we know we will push a lot of entries, that there are no reallocations, because remember, reallocations are slower. So then we are here inserting two entries, and as you can see, this would be an entry of key I32 and value I32. So the key and the value can be of the same type. And over here we insert again another entry. Indeed, the capacity of HashMap is not 100, so we can't compare the equality here. So even though we have here defined that the capacity should be 100, it could actually be more than 100, and this is just in case there are collisions, there are some internal stuff going on, so the Rust compiler will actually allocate more capacity than 100 we defined here. Shrinks the capacity of the map with a lower limit. So when we call map over here, our hash map holding 2 entries, and then we can shrink the capacity to 50, right? So again, the capacity won't probably be exactly 50 then, but around 50. So we can shrink the hash map, and shrinks the capacity of the map as much as possible. So because over here we have only a hash map of 2 entries, 50 spaces in heap memory would actually be more than we need. So we can use the shrink to fit method so that the capacity will shrink around the amount of elements it actually holds. Again, it won't probably be 2 exactly, but around this number. Ownership for types that implement the copy trait like I32, the values are copied into hash map. For owned values like string, the values will be moved and hash map will be the owner of those values. Fix the errors with least changes, don't remove any code line. So over here we have initialized a variable with a type of I32 and an empty hash map, right? Then we insert here an entry into M1 and using the same exact value for the key and the value, meaning we have here a hash map with keys of type I32 and values of type I32. Over here we have a string and we initialize here an empty hash map. Then over here we are inserting a new entry using v2, the string here, as the key and v1 over here as value. So we would have here a hash map using of keys of type string and value of type I32. And because this is an owned type, meaning it doesn't implement copy, this will then actually be moved into the hash map, so we can't use v2 here. But what we could do to fix that is we could use a string slice of this string, right? We just provide a reference, meaning then the hash map will have type for the keys of string slices, right? And that means we can then again use v2. And again, because v1 is of type I32, it means it implements the copy trait, meaning even if we pass it as a key in the hash map or as a value, it is still usable. But when you're dealing with types that don't implement copy, the ownership will get moved, meaning hash map will then be the owner of the type. Alright, and there are some third-party hash libs, but I won't cover that in this beginner's course. So, see you in the next topic. Let's now look at type coercion, and we have already seen the as keyword, and this is mostly used for converting integers. So type conversion, also called typecasting, is coercing a primitive type that can be performed by as keyword. As conversions can be chained, and when casting to an unsigned type t, for example, then t max plus 1 is added or subtracted until the value fits into the new type. and using unsafe methods can lead to undefined behavior. So let's see an example. As you can see, we have here the largest unsigned 8-bit integer, 255, and this would be the binary representation. This means that U8, right, this data type for unsigned 8-bit integers, max, meaning 255, plus 1 will be 256. So for example, if we typecast 1000 as U8, then let's see what the compiler will do. It will subtract 256, this value over here, from 1000. And then it will check 744 is still bigger than the largest value it can represent, meaning it will do the same thing. Subtracting 256 will leave us with 488, still bigger than this value. So again, the same thing, it will subtract 256, and this will leave us with 232, meaning this will then be the returned value when we cast 1000 as U8. Because remember, an 8-bit unsigned integer can't represent 1000, it's out of bounds. Now, when we typecast -1 as U8, then remember, an unsigned integer cannot represent negative numbers, meaning what it will then do, it will basically rotate. So 0 would be the smallest possible number an 8-bit unsigned integer can represent, and then -1 will just basically rotate. It will go back to the biggest one, meaning this typecasting over here will result in 255. So convert by as. Rust provides no implicit type conversion coercion between primitive types, but explicit type conversions can be performed using the as keyword. Fix the errors and fill in the blank. Don't remove any code. So over here we have an F32 float, right? Then we typecast this float into an U8, meaning over here the fractional part will get removed. So the value would be 97. And of course this will then hold a U8. Now we want to typecast this decimal into a char. Now this is not possible directly, but we have seen that we can chain as statements. So we can convert this first to an U8, meaning we will get 97 like we did here, and then typecast it to a character. So C1 will then hold a character. And by the way, 97 would be the ASCII code for A. And over here, as you can see, we can typecast this integer holding an U8 type as char directly. So C2 would also hold a char. Now, as you can see, we are here comparing the integer holding 97 with this typecasting. Now, this typecasting over here converts the B character to its U8 representation. Now B would be represented as 98. So what we can do over here is adding 1 to 97, because remember 97 would be A. Meaning when we add 1 to it, we will get back B, right? So both of them will hold 98. By default, overflow will cause compile errors, but we can add a global annotation to suppress these errors. So, as you can see, the largest possible number U8 can represent would be 255, meaning this would cause an error. Because again, 1000 is larger than the largest possible number a U8 can represent, meaning we have here an overflow error. Now we can actually allow overflowing by using this attribute. So this then won't complain, right? And then when we print out v, as you can see, we would get back 232, because we have seen over here that this would be the result when the compiler performs this operation. So we allow here overflowing literals, right? If we comment this out, then the compiler will complain, because this is actually not possible. When casting any value to an unsigned type t, tmax plus 1 is added or subtracted until the value fits into the new type. That's what we have seen. So in this case, 1000 as U16 would return 1000, right? Because a U16 can represent a number of 1000. But over here we would have an overflow, meaning this would return 232, like we have seen over here. For positive numbers, this is the same as the modulus. So this would actually be the same as doing 1000 modulus 256. Remember, U8 max plus 1. Meaning 256. Now we have also seen in the example, when we have -1 and casting that to an unsigned integer, it will then basically just rotate. So this will return 255. Since Rust 1.45, the as keyword performs a saturating cast when casting from float to int. If the floating point value exceeds the upper bound or is less than the lower bound, the returned value will be equal to the bound crossed. So in this case, we have a float here, casting it to U8, meaning a saturating cast will be performed. So it will just return the largest possible number U8 can represent, which would be 255. Now, in case we have here a -100 as floating point and convert it to U8, this just would return 0, the smallest possible number U8 can represent. This behavior incurs a small runtime cost and can be avoided with unsafe methods. However, the results might be overflow and return unsound values. Use these methods wisely. We can use here in an unsafe block the method toInt unchecked. So the compiler here won't actually check what's going on. So as you can see, we are casting 300 floating point to an uint to a U8. So as you can see, we are here casting 300.0 floating point to an U8 integer, and this won't be checked by the compiler. That's because it's in an unsafe block. Now this would return 44, right? Because 300 minus U8 max plus 1 would be 300 minus 256, meaning we would be left with 44. And minus 100 as U8, as you can see, we are typecasting this floating point to an U8 integer, and again this is unchecked. So again, what the compiler will do here, it will take U8 max plus 1, meaning 256, and it subtracts 100, meaning we would get 156. And not a number would be converted to 0. Okay. And of course, here we have to use again the attribute allow overflowing literals, just so this will actually compile, because usually this won't compile. And as you can see, this would be the output. Now over here we are dealing with raw pointers, and we won't cover that in this beginner's course because this is more of an advanced topic. So see you in the next topic. So we have seen type conversions for integers and types from the standard library, but what if we want to convert types that we defined, basically custom types? And Rust has for this the from and the into trait. So let's see, from and into traits are used for type conversions between different types without requiring explicit casts. It's part of the standard library and can be implemented for custom types. Implementing the from trait for a type will give us the into implementation for the given type for free. Meaning when we implement from, we implement it into automatically. So always implement the from trait and not the into trait. Let's see here an example. We have a custom type number. And then over here we are implementing the from trait, right? So we want to convert from an I32 to our custom type number, right? And the from trait implements a method from. So we take here as an argument an I32, and we will then create a new instance of the number type with the provided value and then return it. And that means when we use here the from associated function on our custom type number and provide it an I32, then this can directly be converted to our custom type, right? And we can do it in two ways, from, as we've seen, because we have implemented it, and I've told you that when you implement the from trait, the into trait is automatically implemented, meaning we can also call the into method on the type we want to convert to. But when you use into, a type annotation is needed, so the compiler knows into what type you want to convert this type, right? So we convert here a type of I32 into a number, and this would be the implementation. So the from trait allows for a type to define how to create itself from another type, hence providing a very simple mechanism for converting between several types. The from and into traits are inherently linked, and this is actually part of its implementation. It means if we write something like this, so we implement here the from trait for the custom type u, then we can use u from t, right? We can then create a U type from the type T. We have implemented the from trait on. Or we could also use into. So we convert T into U. The into trait is simply the reciprocal of the from trait. That is, if you have implemented the from trait for your type, then the into trait will be automatically implemented for the same type. Using the into trait will typically require the type annotations, as the compiler is unable to determine this most of the time. So for example, we can easily convert a string slice into a string. As you can see, we have over here a string slice, and then we can call string and the from associated function, providing it this string literal, meaning this will then be converted to a string. And we could also use the toString method. Again, this and this is exactly the same. And we could also then use the into, because remember, when we implement from, we get into for free. So we convert this my string literal into a string. And again, type annotations are needed. Because the standard library has already implemented this for us, impl from string slice for string. So we can easily convert a string to a string slice and vice versa. Some implementations of from can be found here. So as you can see, we have here impl from bool for i32, meaning we can convert a boolean into an i32. So when we have here a boolean value and call into, it will convert this boolean value into an i32 integer. In this case, this would be 0 for false and 1 for true. And again, when we can use the into method, we can use the from associated function. So we call the associated function on the type i32 and provide it here the boolean value, right? So this will then actually be exactly the same. Fix the error in two ways. First, implement from char for. Maybe you should check the docs mentioned above to find the answer. Second, a keyword from the last chapter. So let's see the docs. So we want here to convert a character. So let's see over here. As you can see all the types that implement the from trait. So we want to go from character, and as you can see, we can convert a character to either U32, U64 or U128, as well as string. So I32 is not supported. And as you notice, these are only unsigned types, because it's logical. A character can't be negative, right? It can't hold a negative number. So we only have unsigned integers here. So we can then in fact convert a char into a U32, let's say. So in this case, char implements. So in this case, we use here U32, right? We can convert from a char to a U32, meaning when we change this over here, this should actually work. So we provide here a character called the into method, and then we should have an U32. Fix the error in two ways. So we can't use the as keyword here. This is not implemented, but what we can do is, let's first use the from method. So we can create a string, or basically converting a character into a string, because we have seen in the documentation this is actually implemented. And the second way would be to call a and then into, right, like we did over here. Implement from for custom types. From is now included in standard prelude, so there is no need to introduce it into the current scope. So we don't have to import the from trait. It's actually in the prelude, meaning we can use it without importing anything. So over here we have a custom type number with one field. Now we want to implement the from trait for our custom number, meaning we should be able to convert from an i32 into a number. So when we call over here number from, right, then we should get over here number. This would then create an instance of the number struct, and the value field here will hold a value of 30, right? So, and the same thing is when we would call 30 like that and call into, right? This should then convert the i32 integer into the number type automatically. And remember, we only have to implement the from trait, because then we can use from and into both of them. So let's see. So this over here is the from trait, and let's take this function signature over here and copy it like that. Now in this case, self refers to number, right? And what we want to do is create here a new instance, and we just take the value, in this case the i32, right, and we provide it as a value for the value field. And again, because the name of this argument matches the name of the field, we can use it like that, and this is sufficient. So let's see. And this is compiling. So as you can see, then it's really easy to convert one type to a custom type we have created. When performing error handling, it is often useful to implement from trait for our own error type. Then we can use question mark to automatically convert the underlying error type to our own type. Now we didn't cover that, this will be the next topic, but let's see the exercise. We have here an enum CLI error. Now the two variants here, IO error and parse error, hold error types from the standard library, okay? And these are actually the error types that get returned in case of an error when using these specific methods that are implemented in this standard library. So as you can see, we want here to implement the from trait for different error kinds from this standard library, and we want to convert that to our custom error type, CLI error. So let's see, over here we have the function open and parse file. It takes a file name as argument and it returns a result, and we will cover results. So a result basically says, in case of success, it will return a result with i32 and otherwise CLI error. So then we call the read-to-string function, and as you can see, this is defined in the fs module. Fs is used for file manipulation, and we provide to this function over here the file name. Now we pass a reference because this is defined in the documentation of this function. We are here using the question mark operator, meaning in case of success, the result type that will get returned will be unwrapped and contents will hold a string. In case of an error, it will return the CLI error, meaning the rest of this code won't get executed and we just get a CLI error instead. Now, the error type returned from this function would be IO error. So in order this error to be converted to a CLI error, we have to implement for this error type the from trait, right? But let's see what's happening here. We then take the contents, meaning this string over here that gets returned in case this function call is successful. And we then hold over here the contents of the provided file. Then we trim and then we parse. Now parse could potentially fail. And parsing is basically converting a string to an integer value, right? So in case of success, we will get out an I32. In case of error, we'll get back a num parse int error. This is defined in the num module. Again, we will cover error handling and all of that, don't worry. This is now just about the type conversion. And then we return an OK with the num value here. We have to wrap it in OK because we return a result type. Now let's see how we would implement that. So again, I will just go to the documentation and copy the function signature like that. So we have the function signature, and then we can over here see what we want to do. So in case we get an IO error, we want to convert that to our custom CLI error. Now how would we do that? Let's change here the argument to E for error, and the type would be IO error, right? We are implementing it from this type. Now what we want to do is we just want basically to pass the IO error into the IO error variant in our custom type. So we can access the variant. So we can create an instance. Remember, this is the syntax to access the enum. So we access CLI error and then the IO error variant. And all we do then is just passing this IO error type, meaning we then have an instance of this variant holding our IO error. And that means we have then implemented the from trait for our custom type. So any IO error type can be implicitly converted to CLI error, meaning in case this function over here returns an IO error, it will implicitly be converted to a CLI error. Let's do the same thing over here for parse int error. This would be the error type from the parse method. So again, let's change here the argument name, and the type would be over here. And then we again just access this enum. We want to access the parse int error variant, and we pass it the actual error that gets returned. And this would mean we then create another instance of the parse error variant. Let's see if this works. And as you can see, this is compiling, meaning in case of an error over here, both these error types from the standard library, IO error and parse int error, will be implicitly converted to CLI error, right? Try from, try into, similar to from and into, try from and try into are generic traits for converting between types. Unlike from into, try from and try into are used for fallible conversions and return a result instead of a plain value. Now again, we use the result type, we will cover that, when there is a possibility of an error, of something going wrong. So as you can see, we have here an I16 holding 256. Into trait has a method into, hence try into has a method try into, right? This is the method defined on the try into trait. So we take this value here and call the try into method on it, meaning this will return a result. So we match this result. In case of an OK, then we unwrap the value from the result, and if it is an error, then we just print out the error over here and return 0, right? So in case this succeeds, then n will hold a u8 and the value. In case this fails, n will hold a value of 0. Now we have seen that when we want to convert an u8, then this would actually fail because this is out of boundaries. But because we are here basically error handling, that means that the program here won't actually panic. So in case this fails here, which it does, then we will just assign to n the value 0 and print out the error. So in this case, n would be 0. And again, error handling will be our next topic. So don't worry if this seems a little bit strange. Then over here we have a tuple struct Enum, and it takes an I32 type. We implement here the try from trait for the custom Enum type. Now here we have an associated type, and we define that it should be of type unit type, okay? And then we implement here the try from function. So all this function basically does, it takes a value and it checks if it is divisible by 0, and then we will return the result, in this case OK, Enum, and inside it the value provided. Otherwise, if it is not divisible by 2, then we return an error holding our unit type we have defined here. As you can see, the type in case of an error would be this associated type error, meaning a unit type. So we have provided that over here. So then we can use the try from function. So when we call Enum and try from 8, then this would return OK, right? Because 8 is divisible by 2. So we would get back a result, in this case OK, Enum, and the value we have passed, right? That's what we defined here. Now in case we try from a value of 5, this would return an error with a unit type inside, because again 5 is not divisible by 2. Now with try from and try into, it's exactly the same like with from and into. When we implement try from, then try into is automatically implemented. So we can use this try into method here directly. So we try here to convert 8 into this result, right? And the result in case of success will hold the type of even num and otherwise a unit type, like defined over here. And in this case, result will then hold okay, even num, and the value we have passed, 8. Now when we call try into on 5, then this will actually return error and a unit type inside, like we have defined over here. Let's see. And this is compiling. See you in the next topic. Let's now see 2 more exercises, and this time we are converting a custom type into a string. So to convert any type to string, you can simply use the toString trait for that type. Rather than doing that directly, you should implement the fmt display trait, which will automatically provide toString and also allows you to print the type with print line. So again, same thing like with from and into. If you implement from, then into is for free. So you usually don't implement this trait directly for a type. You implement display and you will get toString implementation for free. So let's see. We import here fmt and we have here our custom type point. Now here we are instantiating a point. So what we want to achieve here is that when we take the point instance here we have instantiated and converted to a string, this should then be the output. And we can also use the format macro here. Basically just providing origin, because the format macro will automatically convert that to a string in order to print it out, and the output will be the same. So let's implement the display trait here. So as you can see, this is the display trait and it provides one method. Now let's take it from over here. They provide here an example. And we can just copy this over here. Now I remove the lifetime, it's not needed. And let's implement the fmt method here. So as you can see, the fmt method provides here a formatter, meaning we want to write, we can use the write macro here, and the write macro works like println or format, but the difference is it will write to a buffer, in this case f. This is the formatter from the fmt module. And then we here provide what we want to print out. So in this case we want to print out the point is and the values. So let's do that. And then, like in a println macro, we provided the values. So in this case we want self.x and self.y. We want to print out the x and the y field. And that's basically it. We have implemented the display trait for point, meaning our customly created type point can be converted directly to a string. So let's see. And this is compiling. So if we pass origin here, let's see the output. As you can see, this would be the output. So we can even manipulate how the output should look like. So instead of just printing out the two fields, we have even provided the output with a whole sentence, right? This will be the last one we will be doing. We can use parse method to convert a string into an I32 number. This is because from string is implemented for I32 type in standard library. To use from string method, you need to introduce this trait into the current scope. So we have to import this trait from the stir module. So over here we want to parse, and parsing again means converting a string into an integer. So we would here have an I32 type of this value, and over here the same thing. Now we can either annotate the type over here, or we could use the turbofish syntax, meaning we can directly annotate the type on the method, like that. And then, because the from string trait is actually implemented for the I32 type, we can also call the associated function from stir. Let's do 20 here. So this will convert from this string literal into an I32, meaning this will then hold an I32. Now, because all of them hold I32 integers, we can then do a mathematical operation, meaning we just add together all of these values, 5, 10 and 20. So the variable will hold an I32 and it should be equal to 35. And this is compiling. See you in the next topic. Now we will cover error handling, and the simplest form of error handling is to use the panic macro. Panic will print out an error message, unwind the stack and finally exit the program. Now, unwinding the stack means that when you actually execute the program, then we have seen that the local variables and the function calls will be pushed to the stack. Now, when panicking, that means that the compiler will actually delete everything step by step from the stack memory and then exit the program. And in multi-threaded programs, it will exit the thread in which the panic occurs, not the whole program. So we don't deal here with multi-threaded programs. This will be another course, but I just want to mention it. So let's see exercises. As you can see, we have here a function drink, which takes a string literal. If the string literal is lemonade, then we print out success. Otherwise, we actually want to panic, right? Because we want to ensure that this line never gets reached, meaning never gets printed out. So when we pass over here lemonade, then this will print out success and then will panic. And this would be the output if a program panics. Thread main panicked at explicit panic, and it will provide you the line number at which the panic occurred. In this case, an explicit panic, because we have here called the panic macro. Common panic cases. Make the code work by fixing all panics. So when we call here the asBytes method on a string, then it will give us back the array holding the UTF-8 bytes of this string. Now we have seen that actually the UTF-8 representation of A would be 97, B would be 98, and C would be 99. So again, if assert EQ doesn't match, if this does evaluate to another value than this, then assert EQ will cause a panic. Over here we have a vector, and we try here to access the third index. Now we only can go to index 2, right? It's the outmost index we can provide. So let's change that. And this will then hold an I32, right? Because we are accessing a specific element. Unwrap may panic when get return a none. So the get method over here will return an option, meaning it either returns a sum with a value or a none. Now in this case, this would return a none because we don't have any value at index 3. So when we try to unwrap a non value, then we will panic. Now let's here access index 1, for example. Then it will return a sum 2, right? The first element, right? The element at index 1, and unwrap will basically just unwrap the inner value. So LA will then hold a value of 2 of type I32. Sometimes the compiler is unable to find the overflow errors for you in compile time, so a panic will occur. So when we call here the production rate per hour function with a value of 2, then let's see. We have here speed, the provided argument of type U8. And here we have CPH of type U8. Now, as you can see, we are inside here multiplying the speed, in this case 2, by CPH 222. Now this would actually result in an overflow because 2 times 221 would be 442, right? Now remember, an U8 can only represent up to the number 255. So this would actually cause a panic. But what we can do is just actually taking here a U16 and converting that to U16, meaning when we multiply these together, then the result of U16 will still be able to represent the resultant number. And over here we can do the same thing. And then let's see, because of the same reason as above, we have to wrap it in a function to make the panic occur. So here we are calling the divide function with two arguments, 15 and 0. So the divide function takes two arguments of type U8 and just divides it. Now this would also panic because we can't divide by 0. This is a mathematical rule and this will always lead to a panic. So let's here divide by 1, for example. Let's see if this is compiling. Alright, and again, when we use the get method, we will get back a reference to the value and not the actual value. So let's change that. And this is compiling. Detailed call stack. By default, the stack unwinding will only give something like this. So this would be the output if your program panicked. Though there is the reason of panic and the line of code is showing where the panic has occurred, sometimes we want to get more info about the call stack. Fill in the blank to display the whole call stack. Tips: you can find the clue in the default panic info. So when we run cargo run, this is basically how you execute a program you have written, and we'll cover that. Then you just provide over here this Rust backtrace equals 1 environment variable, and it will then give you detailed information about the panic that occurred. So over here, unwinding and abort. By default, when a panic occurs, the program starts unwinding, which means Rust walks back up the stack and cleans up the data from each function it encounters. But this walk back and cleanup is a lot of work. The alternative is to immediately abort the program without cleaning up. If in your project you need to make the resulting binary as small as possible, you can switch from unwinding to aborting by adding below content to cargo.toml. So we can here define in this cargo.toml file, and I will show you an example of that, how panic actually behaves. So we have two options here, either unwinding or aborting. When choosing abort here, then the stack won't get unwinded, meaning this will then be the responsibility of the operating system and not of the Rust compiler. Alright, see you in the next episode. So we have seen the option type. And the option type stands for a value that could potentially be absent. So let's now look at the result type. Result is an enum type that represents the outcome of an operation that could potentially fail. It has two possible variants, OK, a value t was found, and error, an error was found with a value e. And as you can see, the variants hold the specific information. The expected outcome is OK, the unexpected outcome is error. Since result is an enum, the possible variants can be matched using a match pattern, and that is what we call error handling. So let's see an example. Let's again consider the divide function we have seen before. So again, we can't divide by 0. Meaning, if the second argument here is a 0, then we should return an error. Otherwise, the program will panic. Now we can do here error handling, meaning we check if y is 0, right? Or in this case 0.0, because the arguments are floating point numbers. Now in case y holds a value of 0, then we return the error variant of the result enum, and we provided an error message. Alright, so in this case we use an explicit return keyword, meaning when this returns, it won't execute any further. It will directly return the error type and stop execution. Now in case y is not 0, then we will just divide x by y and wrap it inside OK, because remember, result is an enum, meaning we have to wrap the resultant value inside the variant. So that means when this function succeeds, then we will get back an F32, right? The result of this operation. And this is wrapped inside OK, because as you can see, we are returning a result type. Now in case of an error, we would return this string over here, wrapped in the error variant. And this allows us then, when we call the function divide with two arguments, that we can then match the result we get back here. As you can see, we would get back a result type, meaning the result type has two variants, either OK or error. And we can here use pattern matching to destructure the inner value, for example, this F32, into the variable val, which we then can print out. And in case of an error, we will get back this string over here, the error message. And we destructure it into this variable here and then print it out. Unwrap. The unwrap method takes as input a value of type result and takes out the value which is wrapped inside OK in case of success, or panics in case of an error. In case it returns an OK variant, we just take the value that is wrapped inside. Otherwise, the program will panic. So you should use unwrap only if you're 100% sure that the return variant will be OK. Otherwise, you should use match. And let's see the question mark operator. The question mark operator is a shorthand way to propagate errors or unwrap OK results. Basically, it's the same as unwrap, but instead of panic, it returns an error. It replaces an entire match statement and it can even be used in the main function. So, as you can see over here in the main function, we can define here that main should return a result type. And as you can see, we have here a string holding a number. Then we try to parse this string over here into an I32 type. Now we have seen that the parse method could potentially fail, right? If we have here a string holding T, for example, the compiler can't convert it to an I32 because it's not a valid number. So in case we get back the OK variant, remember parse will return a result. If we get back OK, then we just take the inner value and return it, meaning the inner value will then be assigned to the number variable. In case of an error, we want to return, meaning this over here won't get executed, it will return before. And we just provide the error message over here. And in this case, because we are using a function from the standard library, this error message is actually provided, right? So we just take the provided error message and return it. And if this didn't fail, it means this will get executed, and we just print out the unwrapped number. Now, because we return here a result type, we have to also return an OK in case everything succeeded. Now, because at the end of main, basically the end of the program has been reached, so it doesn't make sense to return any meaningful value. So we just return a unit type like that. So I've told you that the question mark operator actually replaces an entire match statement, meaning this over here would be exactly the same. So let's see. Again, we are in main and we return a result. Now, as you can see, we have again a string holding a number. Then we try to parse over here, and again parse returns a result. So we have to handle the error case. Now we can do that appending to it the question mark operator, meaning in case this succeeds and it returns an OK with the value, in this case 10, but parsed as an integer, then it will just assign it to this variable, meaning number will then hold 10 as an I32. In case this fails, then it will return a parse int error as defined in the parse method. Okay, so this over here is exactly the same like we did over here. And when this returns an error, the following lines won't be executed. In case this succeeds, then we have number which holds 10 of type I32. Then we'll just print out the parsed number, and then we return a unit type, because remember, we are here returning a result, meaning we have to also return OK variant in case of success. But again, because we are in main and this would be the end of the program, we don't return any meaningful value, we return a unit type. And there is also a concept called type alias. So it's basically just a way giving a name to an existing type. So if you like to write use64 like this, then you can create a type alias, meaning we can use the type keyword and provide a new name for a specific type. And as you can see over here, we are then using the new type we have created here. And this would at compile time then be replaced with the real type. And please don't confuse that with associated types in traits. They are different, okay? Let's see. Result is an enum to describe possible errors. It has two variants, OK and error. In short words, the expected outcome is OK, while the unexpected outcome is error. So let's see, fill in the blanks and fix the errors. First of all, we are importing the parseInt error from the Enum module, because we are using here the parse method, meaning it will, in case of an error, return the parseInt error. Now we have here the function multiply that takes two arguments of type string literals. Okay. Now, as you can see, we are here returning OK, meaning the return type will be of type result. And in case of success, or let's actually wait with annotating that, let's first see what's happening here. So we are taking this string literal and try to parse it to an I32, right? So again, this parse method over here will return a result. In case of success, we would have OK and the value that was parsed. So for example, when we call here multiply with an argument of 10 for the first parameter, then we would have a parsed number 10, right? So we would have, in case of success, an I32 here. In case of an error, we would have the parseInt error, like that. And parseInt error is the error type that is defined for this method. Again, this is implemented in the standard library, so this has to comply with what is defined there. And N2 is exactly the same, but for the second argument. Then over here, we unwrap, and remember, unwrap will take a result and just unwraps the inner value. So in case we have OK, let's take the first argument 10. Then unwrap will just unwrap the inner value, meaning it returns the integer I32, right? That is wrapped inside the result enum. And then over here we are multiplying by N2. Again, we have to unwrap because this is a result type. And if this succeeds actually, then we will return an OK, meaning OK will then hold in this case 10 times 2 will be 20, right? Like that. So we return an I32 in case of success. In case of error, we will return a parseInt error, because that is the error that is defined from the parse method. So let's see, when we call multiply with these two string literals 10 and 2, then this should actually work, right? Because the compiler is able to parse these into integers. So it will parse here, and this will then be OK 10, and over here we would have OK 2. Then we unwrap both of these over here, meaning we unwrap the value from the variant, and here 2, meaning we multiply 10 by 2. And then this would be 20, and we wrap it inside OK, because we have to return a variant of the result enum, which means that the return type over here would be this, right? So result in case of success will hold OK and 20, right? Now in this case, this would actually fail because the compiler can't convert t to an integer. Now we want this to actually assert to 8, so let's do here 4, and this means this will get parsed to 4, and this will get parsed to 2, right? And then again, we just multiply these together and return it wrapped inside the OK variant. Meaning over here, we get back a result, and result will then hold OK and 8. Right? Now, if we unwrap the result over here, then it would unwrap the inner value, as you can see. So unwrap method allows us to unwrap the inner value. So OK 8 would be unwrapped to 8. Question mark operator is almost exactly equivalent to unwrap, but question mark operator returns instead of panic on error. So let's see, we have again the %" error. Implement multiply with question mark. Don't use unwrap here. So let's see. Again, we are taking two arguments of type string literal, right? 3 and 4 in this case. And let's start to implement. So we declare here n1, and we take n1 string and try to parse it into an i32, right? Now again, we should here use the question mark operator. So we append it after the method call here, and then we can only use the question mark operator when the return type of the function is a result, right? Because the question mark operator, in case of an error, will return the error variant and inside it the error value. So we return here a result. In case of success, it should be i32. And in case of failure, it should be this %" error, because again, this is defined as the error return value of the parse method. Now for n2, we do exactly the same. And that means if any of these fail, then it will immediately return, meaning the rest of the function won't get executed and a %" error will be returned. Now the question mark operator, in case of success, it won't return a result, it will unwrap. So for example, when we pass here 3 and this will get parsed, it will return OK and 3, right? and then the question mark operator, like unwrap, will unwrap the inner value. So n1 will then hold 3, meaning an i32 integer, and n2 the same thing. And then all we want to do is just returning an OK in case of success, because the return type is result. And we want to multiply n1 by n2. Notice over here that I didn't have to unwrap, because we have here i32 types, right? While over here we had to unwrap, because these held result types. You have to remember that. Let's see. And of course I have to change that over here. Typo. And this is compiling. So what we had over here when we provide 4 as a string, we would have OK 4. Right, and then the question mark operator unwraps the value, and then over here we are multiplying 3 by 4, which would be 12, and then we wrap it inside OK to comply with the function signature. So this will then be the returned value, right? And then over here, as you can see, we are calling the function and unwrap it, because we have here a result type. So we unwrap the inner value, because this would return OK12, and we unwrap it, meaning the inner value gets unwrapped. Let's see over here, we have the file type from the FS module, and over here we are importing some stuff from the IO module. So over here we are opening a file, providing here to the open associated function the name of the file in form of a string literal, meaning this will then return a result, and in case of success it will hold a file, right? And in case of error, it would be IO error. All right. And then we are matching F. Now, F holds a result, meaning we must over here handle both cases in case of success and in case of failure. So if it is OK, then we unwrap the inner value, meaning the file, and we just assign it to F. In case of an error, we return the error wrapped inside the error variant of the result type, right? Because this function over here returns a result. All right, and then over here we are creating a new empty string. We then take F over here and read to string, meaning the contents of this file over here will be copied to this string, meaning S will then hold basically the contents of the file we have opened. And we have to provide here a mutable reference because this is defined in the standard library. And then again, because this read to string method returns a result, we have to match it. So in case of OK, then we will return over here a string, right? This string S over here. In case of error, we will return the error. And both of them, file open and read to string, return an IO error. All right. Now over here, fill in the blanks with one code line. Don't change any code lines. As you can see, we have here the function read file to, which returns a result. In case of success, it's a string. In case of error, it will be the IO error from the standard library. We here declare a new string, and we here initialize a new empty string. And I told you that the question mark operator replaces a whole match statement. So we can write all of this in one single line. So first of all, we are opening the file. So let's take this. And as we've seen, open will return a result. So we can use the question mark operator here to replace this whole match statement. So in case of error, it will immediately return, and it returns this error type. In case of success, then we will get OK and a string, and this will then unwrap it to the string, right? And in case of success, we will have a value of type file, like we saw over here. And again, file is a type defined in FS module. So we have seen that the question mark operator will then unwrap. We will basically get something like that, and it will unwrap the file inside the OK variant. What we then can do is call the read to string method on it, right? So we are calling read to string, and then again we have to append this question mark operator, because read to string also returns a result type, right? So in case of success, we will then over here mutate s, meaning the contents of this file will get read to this string, all right, or written to this string. And then we just return s, right, the string. And that means in case of success, we will have as return type a result that is holding a string. In case this or this fails, then it will return an IO error. Meaning if this fails, then over here a IO error gets returned, and this will never be executed. And if this fails, again, we return this error, and this will never get executed. Let's see. This is compiling. Map and then. Map and then are two common combinators for result TE, also for option T. So we have over here the parse int error, fill in the blank in two ways, map and then. So we have here the function add2, taking a string literal and returning a result. In case of success, holding an I32. In case of error, parse int error. All right, because this is the default error type of the parse method. Then we are taking this string literal and try to parse it to an I32. And then, as you can see, when we provide here add2 with a string holding 4, then we want to get back 6. So as you can see, when we provide 4, we will get back 6 over here. And that means we want to parse this string and then add 2 to the parsed number. And for that we can use map, which is really convenient, because we not only want to handle this result case, but also then modify the value, right? So n here takes a closure, and we will cover closures very soon. So we provide here an argument n, and n would then hold the parsed number, and all we do is adding 2 to n, right? And that's all. So let's actually see the map method in the documentation. As you can see, maps a result TE to result UE by applying a function to a contained OK value, leaving an error value untouched. So when we call the map over here, it will it will apply a function if this method returns an OK value. If it returns an error, then it will leave it untouched. Alright, so in this case, this would actually succeed, right? So parse over here will parse this 4 into an I32 integer, meaning it will then take the OK value and unwrap it, so n will then hold a 4, and then we just add n, and then we just add 2 to 4, right? Let's see. And this compiles. Now the second approach would be using and then. Now and then is very similar to map. The difference is here in the closure that the and then method takes. So let's go back to map here. So over here you can see this is the argument for the closure, right? And the closure over here returns directly the value, all right? And over here the closure itself will return a result. Now both of these methods return results over here, but the difference is in the closure, and you will see what I mean when we are looking at this. So this is very similar. It will take this parsed integer and then put the unwrapped value into n, and then over here we add 2 to n. Now we have seen that map would work like that, and then method will actually return in the closure itself a result. So we have to wrap that into OK, like that. But otherwise they are exactly the same. And this succeeds. Number 5, with the return type rewritten, we can use pattern matching without unwrap, but it's so verbose. So here again we have the multiply function taking 2 string literals. In case of success, it returns an I32, otherwise parse int error. So over here we are using the match keyword. Now we want to parse the first string literal, the first argument. In case of OK, then we destructure it into the variable n1. So n1 will then hold the parsed number. In case of an error, we just return the error type. Then we match inside this match arm over here again. So we match the second argument, parsing it, and if this is okay, then we get out n2, all right? And then we can multiply n1 by n2 and return the result wrapped in the OK variant. Because as you can see, the function returns a result type. And in case of an error, it just returns an error. So this would be very verbose. So rewriting multiply to make it succinct. You should use both and then and map here. So let's see. We take first of all the n1 stir over here, the first string literal. All right. Then we want to parse it to an I32 integer, right? And let's then use and then. So if this succeeds, then we will have here n, which holds the parsed integer, right? And let's actually write it more beautiful like that. So we take then n, or let's call it n1, just to make a distinction. And then over here we want to parse the second one. Right, we want here the second one. And then if this also succeeds, we want to multiply n1 and the parsed n2 together. So let's use map here. And we would here have n2, right? Because map over here is called upon the parse method. So we would then get back n2. And then we just return n1 times n2. And notice, because we are using map here, we don't have to wrap it inside OK, right? So this will then return, for example, when we call it by 10 and 2, it will return 20. All right? And then we have seen that it will return the result type. So in case of success, it will return OK with an i32 value inside. Otherwise, it will return a parse int error. Let's see. And this is compiling. So as you can see, when we are calling the multiply function with 10 and 2 as string literals, it will parse the first argument, meaning we then have over here OK 10, right? And then over here we call the and then method. All right, so we take this n1 value here, basically unwrapping it, and inside and then we parse the second number. So in this case 2, right? So this will then get parsed into an i32, and we then can map, meaning we have n2 over here, and 2 in this case would be OK 2, right? And map will take and unwrap the value inside OK, meaning we then have n2, which holds 2 over here, and then we multiply n1 by n2 and return it. All right. And all we then do is here the returned value would be of this type, right? And in this case, this would return OK 20, right? Because it could parse these two numbers and it multiplied it and returned it. So we get OK 20. Then we pass that to the print function. As you can see, it takes as an argument a result type. Then we match it. If it is OK, then we print out the value wrapped inside OK, in this case 20. Otherwise, we will print out the error. And when we call multiply with an argument that can't be parsed, then we would get a parse int error, right? So this would then hold a parse int error. We are providing that to the print function, and then we match the argument, this tt, and this will then match the error, meaning the error will get printed. So in the first print call, n is 20, so we have successfully parsed these two numbers and unwrapped the value, printing it. And in the second one, because we provide here an argument that can't be parsed, we get an parse int error, and this would be the error message that is provided in this standard library. So type alias, using this type over here everywhere is verbose and tedious. We can use alias for this purpose. So at a module level, creating aliases can be particularly helpful. Errors found in a specific module often has the same error type. So a single alias can succinctly define all associated results. This is so useful, even the standard library even supplies one IO result. So as you can see, we have here again the parseInt error, and we want here to create a type alias. Now we have here the same multiply function we have seen above, so I won't cover that anymore, but the return type is defined as res i32. And the print function over here takes as an argument a type of res i32. Now, as you can see, exactly the same functions as we had over here, but we don't write out the whole type. We use here a type alias, so we can define that here. We use res i32, and we want to define that as a result. In case of success, holding an i32. In case of an error, as you can see, the parse method would return a parseInt error. And then instead of writing that all the time in our functions, we can use this simple type alias. And of course, at compile time, these type aliases will then get replaced with this concrete type here. Let's see. And as you can see, the same output as before. Using result in fn main, typically the main function will look like this. However, main is also able to have a return type of result. If an error occurs within the main function, it will return an error code and print a debug representation of the error, debug trait. The following example shows such a scenario. So as you can see, we have here again the parseInt error, and we define here in the main function that the return type should be of type result. In success, returning a unit type. In case of error, it will return a parseInt error. So over here we have a string literal, and we are then trying to parse this string literal to an i32. Now again, parse returns a result, so we have to handle both cases. In case of OK, we just take the wrapped value and assign it to a number, right? In this case, this would hold an i32. In case of an error, it will just return the error, and it will stop execution from this point. And then all we do is we will print out the number. So let's see if this is compiling. As you can see, this is compiling. We are printing out the number. And don't forget, because we return a result type here, we have to return the result variant OK with a unit type in case of success. We provide here a unit type to the OK variant because the end of main means the end of the program. Because the end of main means the end of the program, so we don't have to actually return anything here, right? Because if the program ends, this returned value won't be beneficial. But we can just provide the unit type so we comply with the function signature. And by the way, as we've seen, we can here just use the question mark operator. So we can replace this match statement by this. And this is actually the reason most people use here in main the result type, because then it allows us that we use the question mark operator. Otherwise, if we didn't have result here, we can't use this operator. Let's see. Of course, I have to remove the match keyword here. And as you can see, this would be the same thing. Alright, see you in the next topic. Let's take a look at Cargo. Now, Cargo is the official package manager and building tool in Rust. It helps automate tasks such as creating new projects, building, running, testing code, and managing dependencies. A crate is a compilation unit of Rust source code. So basically a crate is the smallest amount of code the Rust compilers considers at a time. And crates.io is the repository for Rust packages. So, as you can see, this is the website of crates.io, and here you find some libraries. For example, we have here the rand library, and this allows for creating random numbers. And as you can see, you can add this very quickly into your own project, and we'll see how this will work. What is a crate? A crate can be of two types. Either it's a binary crate, and that means the program is compiled into an executable binary. It's basically a program you can run. And binary crates always have the main function in it. And a library crate. A library crate is compiled into a library, and it doesn't contain a main function, but it's considered a collection of reusable code that can be shared across multiple projects. And the crate root is the source file that is the root module of the crate. In binaries it would be source main.rs, and in libraries it would be the file lib.rs. Then we have modules. And a module is a way of organizing code by grouping together related items. Modules can be imported using namespaces, avoiding naming collisions. It also controls the privacy of its items like functions, structs, enums, and so on. When compiling, the compiler starts from the crate root. We have seen in a binary crate this would be in main.rs. And in a library it would be lib.rs. Then it checks if the modules are declared and looks for submodules. Submodules could be directly written in line with curly braces. It could be written in a separate file which has the module name ending in .rs. Or it could be in a separate directory which has the same name of the module and a mod.rs file inside it. And we'll do exercises and you will see how that works. So in case you want to follow these exercises, you actually have to install Rust on your system. So you can go to rustlang.org and then you can click install. And over here it will give you a command you can copy. Then running a terminal, and you can just copy this into your terminal. Now I'm on a Unix-like operating system, meaning I will use the Linux command, but the website will recognize your operating system and provide the appropriate command. So if you're on Windows, it will give you a command that you can paste into PowerShell, for example. So proceed with installation default. You can then press 1 and enter. Now I have already downloaded that, so I won't run it again. And then to check if everything is installed correctly, you can use these commands. First of all, we check is the Rust compiler installed. If you get back a version, it means everything is installed. Then we check for cargo. This is fine. And rust up. And rust up is used for updating the version of Rust on your local system. Alright, so let's now see the exercises. A package is a project which you create with cargo in most cases, so it contains a cargo.toml file in it. So create a package with below layout. Now I will do that directly in the home directory, but you can do it at any location you want. So to create a new package, we can use cargo new and then provide the name of the package. So we want the name here to be hello package. And as you can see, the package has been created. So let's see cd hello package, and we are now inside our created package, right? So we have here cargo toml and a source directory. Let's see source. And if I print out the contents in main, as you can see, it contains a simple program that prints out hello world. So let me actually do it like that. So over here, if I now do a tree command, as you can see, we have exactly the same file structure here. We have a cargo toml and then a source directory with main.rs inside. Let's print out the cargo toml. And as you can see, this matches the file in the exercise. Create a package with below layout. So over here we want to create a library. So I'm back in my home directory and we can create the library create right now. Let's do cargo new, then the package name here. And then we have to provide the lib flag, right? So this will then create a library. And then let's cd into that. And as you can see, we have cargo toml and a source directory. Now let me print out the cargo toml file. And as you can see, again, this matches. And if we go to the source directory, as you can see over here, we have a lib.rs file. And this just has a basic add function over here together with some tests. All right. Fill in the blank with your answer. What's the difference between package number 1 and package number 2? Now the difference would be package number 1 is a binary crate. And package number 2 is a library crate. All right. Crate. A crate is a binary or library. The crate root is a source file that the Rust compiler starts from and makes up the root module of the crate. In package hello package, there is a binary crate with the same name as the package, hello package, and source main.rs is the crate root of this binary crate. Similar to Hello Package 1 also has a crate in it. However, this package doesn't contain a binary crate, but a library crate. And source lib.rs is the crate root. So what's the name of the library crate in package Hello Package 1? The answer would be, Hello Package 1. Right, because as we've seen over here, in the package Hello Package, there is a binary crate called Hello Package. And that means in a package Hello Package 1, the name of the library crate would be Hello Package 1. And by the way, a package is what we have seen over here. Basically, when we create a new project, right? When we create a new project, we create a new package. And a package consists of a cargo.toml file and a source directory together with other stuff. Add a library crate for Hello Package and describe its files tree below. Alright, so we want to add in the Hello Package a library crate. So let me remove this over here, and we will go inside Hello Package. Now over here in the source directory, we want to create a new library crate. As you can see, we have until now a binary crate, so let's create lib.rs. Touch is a Linux command that allows to create a new file. So then we would have librs and main.rs. So when we look at the tree, as you can see, we then have the cargo.toml, the source directory, and two crates, one library crate and one binary crate. So this would then hold lib.rs and main.rs. After this step, there should be two crates in package Hello Package, a binary crate and a library crate, both with the same name as the package. A package can contain at most one library crate, but it can contain as many binary crates as you would like by placing files in source bin directory. Each file will be a separate binary crate with the same name as the file. So create a package which contains three binary crates: Hello Package, main1, main2. One library crate. So what we want over here is to have in the source folder the lib.rs and main.rs. Then inside the source folder we want to have a bin directory which holds main1 and main2. Right? So as we've seen, we can have as many binary crates as we want in a package, but only one library crate. And over here we have some other directories. So we have tests for integrated tests, benches for benchmark, and examples. So let's create these over here. So as you can see, inside source we already have a library crate and a binary crate. Now we want to create a new directory called bin. Then we cd into bin and we create main1.rs and main2.rs. So again, when we go to the root of the package, as you can see, we have cargo.toml, the source directory. We have inside the source directory a bin directory holding two binary crates, main1, main2, and we have in the source directory lib.rs and main.rs. Yep, as you can see, the above package structure is very standard and is widely used in many Rust projects. So let's see modules. Modules let us organize the code within a crate into groups for readability and ease of reuse. Module also controls the privacy of items, which is whether an item can be seen by outside code, public, or is just an internal implementation and not available for outside code, private. We have created a package named hello package in previous chapter and it looks like this. Now we actually created over here a bin directory, so let's delete that. I go into source and then remove the bin directory. So as you can see, the tree looks exactly the same. Now it's time to create some modules in the library crate and use them in the binary crate. Let's start. So as you can see, we can define some code in the library crate and then use it in the binary crate. So implement module front of house based on the module tree below. So in the library crate, we want to create a module front of house, and this should then hold two submodules, hosting and serving. Now hosting holds 2 functions and serving holds 4 functions. So as you can see, we would do that in the library crate. All right. And again, modules allow us to structure our code. So let's open lib.rs and I will copy this over here. So we have to implement front of house. Now we have seen that front of house module should contain 2 submodules, namely hosting and serving. Like that. So we have a front of house module that contains 2 submodules, hosting and serving. Now we want to add these functions over here, add to waitlist and seat at table in the hosting module. Add to waitlist, add to waitlist and seat at table. So as you can see, front of house containing 1 submodule, hosting, holding 2 functions over here. Now let's see serving. I will just copy that. Like that, and doing it like that. As you can see, the serving module holds 3 functions. And when we run the code, actually we can use the cargo run command. And as you can see, this is compiling, but it gives us warning that we didn't use these functions over here, which is okay. And of course, hello world will get printed from the binary crate, right? Because main just prints out hello world. Let's call add to waitlist from a function eat at restaurant, which is within the library create root. So inside lib.rs, we are below the module front of house, we are creating a new function. Like that. Call add to waitlist with absolute path. So it's like in a file system, you can have absolute paths and you can have relative paths. So in this case, we want to use the absolute path to the add to waitlist function over here. So we would use for the absolute path the create root. Then we want the front of house module. And we want the submodule hosting, right? And then over here, we can call the function like that, add to waitlist. Now this would be considered the absolute path. Now over here, we are using the relative path. So we are actually already in the create root, right? So that means we don't need to use create here. We can directly access front of house. Hosting. And then call the add to waitlist function. Now, as you can see, it gives me here an error. Module hosting is private. So we can make this public using the pub keyword. All right. Now the same thing with the functions. Let's make them public. Like that. You can use super to import items within the parent module. So again, in lib.rs, we want to create another module. So let's copy that. I will put it below the front of house. And as you can see over here, we have the back of house module with two functions declared inside it. So we have fix incorrect order, and inside this function we call the cook order function over here. Fill in the blank in three ways: using keyword super, using absolute path. So in order to access the function over here, serve order, let's first use the super keyword. So super means we go one level up, right? So we are here inside the module back of house. So we go one level up, which would be the create root, right? lib.rs. So we use super. And then we can access front of house. And I guess hosting, no, serving, and serve order. Like that. And again, serving is private. Let's do that. Let's make it a public function. And again, serving here is private. So let's make that public. And also the function here, like that. And the second way would be using absolute path. So again, we can use here create, right? Create would refer to lib.rs because it is the create root of this package. Separating modules into different files. So as you can see, we want to put these modules into their own distinct files. Please separate the modules and codes above into files resident in below dir tree. So as you can see, we have here main and librs crates, and here we have the modules we want to split up. So we have the module front of house holding hosting and serving. These are submodules and mod.rs, and we have over here back of house.rs. Now we have said that there are three ways to declare modules, right? The first way would be in the crate root, for example lib.rs. We define a module and put it right inside the curly braces, right? All the code is inside these curly braces, right? The second way would be to, in lib.rs, declaring the back of house module, but without curly braces, right? Only declaring like this, for example. Only declaring the module. And that means the compiler will then check, is there in source directory a file named as the same name as we gave it to the module, right? So we declared a module in lib.rs, and then we have to create a file ending in .rs with the same name as the module we have declared. And the third way would be, if we want the module to be a subdirectory of source, then we have to again declare front of house inside lib.rs, the same way we did before, but we create a directory instead of a file with the same name as the module. And then, very important, the code of the module will then be in mod.rs. Now in our case, we are declaring in mod.rs two submodules, hosting and serving. All right. So we want to have this code separated in different files, and this is how it should look like. So let's start with back of house. All right. I will copy that. And first of all, I will delete anything in here, and let's declare the module back of house, right? Now we have here declared a module. As you can see, the file is not found, so we can here declare and back of house .rs, and then we can put the code of the back of house module directly into this back of house file. Removing this over here because we have already declared the module, and as you can see, back of house file now contains only the code related to this module. Again, we have in lib.rs declared the back of house module, then we have over here created a file that has the same name as the module, right? And in here we are providing the code like that. And because we have already declared the back of house module, we don't have to redeclare it inside here, right? Now, as you can see, we also want front of house. Now the difference is front of house should be a directory holding two submodules. So let's first of all, in lib, we want to declare front of house module. like that. Then we create the directory with the same name as the module. Like that. Then the first thing is we create a file mod.rs. This is now the crate root of this. This will be considered the root of this module, mod.rs. And as you can see, we want here inside front of house two submodules, hosting and serving. Let's declare them. Like that. And then we can create both of these files. Let's start with hosting. And we just take all the code from the hosting module here. Like that. And let's create serving. And we just take the code here from the serving module. Like that. Let me remove the comment. So, and now if we go back to the source directory, as you can see, we have back of house. This is a module. We have front of house, hosting, and serving. These are two submodules. And we have here mod.rs, exactly like we wanted here. Now over here, by the way, this function eat at restaurant will be directly in the lib.rs. So as you can see, instead of defining the module and putting all the code in curly braces, meaning inline, we can use different files to restructure and reorganize our code. And this makes the lib.rs file much more clean and readable. Accessing code in library crate from binary crate. Please ensure you have completed the fourth exercise before making further progress. You should have below structures and the corresponding codes in them when reaching here. So we have done that. Now we will call a few library functions. Now we will call a few library functions from the binary crate. So let's copy that into the binary crate. Like that. Now we want to call a function. So the output should be sit down please, and then a second function which returns yummy yummy. Now, as you can see over here, we have to call the eat at restaurant function to get back yummy yummy, and sit down please would be in the front of house module, in hosting, and seat at table function. So let's see. First of all, I want here the module front of house, right? Because the binary crate and the library crate are separate from each other. So the binary crate over here can't know what is defined in the library crate. And then over here, we can, as the crate module, and then here we can use an absolute path providing the crate root. Now we have to actually provide here the name of the crate, meaning hello package. All right, and then we can call front of house, and let's see, front of house hosting seat at table. Seat at table, like that. And then over here we call hello package and then eat at restaurant. This is defined in our lib.rs. So again, instead of writing here crate, we write the name of the package because we are here in the binary crate. So we can use the crate keyword in lib.rs, but in main.rs we have to provide the name of the package. Let's run that. And as you can see, we have some errors. Module serving is private and module hosting is private. So to actually access that from the binary crate, we have to make them public. So let's see. First of all, we go to lib.rs and we want these two modules to be public. So let's make them pub like this, which means that these two modules are now accessible for our binary crate, the main.rs file. Then let's go to front of house. And let's here make these two modules or these two submodules also public. Like that. And if the module itself is public, that doesn't mean that the inner functions, for example, or structs or anything that is inside the module is also public. So we have to declare here, as you can see, this is already done, that these functions are also public if we want to access it. And as you can see, serving also has the public functions. Now let's check again in lib.rs because we are calling here a function. Alright, this is also public. Let's run it again. And as you can see, this is actually compiling. It just over here complains that we didn't use some of the functions, which is okay at the moment. Now, instead of just asserting, let's actually print that out. Yeah, let's do it like that. As you can see, the output will be sit down, please. Let's call the second one. So we want to get this. Like that. Let's see. All right. I copied here the whole assert. We don't need this actually. Let's see. And as you can see, the output will be sit down please and yummy yummy. So we have successfully restructured and reorganized our whole code into different files and folders, meaning it is much more organized and much more readable. Alright, see you in the next topic. We will now take a look at the debug and display traits. So types which want to be printable must implement either debug or the display traits. And automatic implementations are only provided for types in the standard library. So this doesn't apply to our customly created types. A debug trait can be implemented by simply using derivable trait. And a display trait must be manually implemented. Let's see. We have here println and format. Printing is handled by a series of macros defined in standard format, some of which include format, write formatted text to string, print, same as format, but the text is printed to the console. Println is the same as print, but a new line is appended. ePrint is the same as format, but the text is printed to the standard error. And ePrintln, same as ePrint, but a new line is appended. All parse text in the same fashion. All parse text in the same fashion as a plus Rust checks format correctness at compile time. So let's see, we have here a string literal and we use here the format macro, meaning the return type will be string. And we want here s to hold a string of hello world. So again, we use the format macro like we would use the println macro we have been using. So in this case, we want to take s1 over here and then just append the rest. So we take hello, this will be placed here, and then the rest. And this is compiling. Let's actually print that out. As you can see, this would be the output when printing out s. Print println, fill in the blanks to make it print hello world, I am, and then on the new line sun face. So over here we want to use print, because as you can see, I am should be on the same line. So as we've seen, print macro doesn't append a new line character. Now a new line is defined in C like that, alright? And this is a symbol that the compiler knows that it should treat it as a new line. But in this case, print doesn't append it, so the next line will be on the same line as this print statement. So let's use here println, because as you can see, after I am, we want to have a new line. And then over here we can again use println. And this would be the output. Debug and display. So all types which want to be printable must implement the standard format formatting trait, debug or display. Automatic implementations are only provided for types such as in the standard library. All others have to be manually implemented. Let's first look at debug. The implementation of debug is very straightforward. All types can derive the debug implementation. This is not true for display, which must be manually implemented. and we have used that before. This is the debug notation, must be used to print out the type which has implemented the debug trait. So as you can see over here, we have a custom type. This structure cannot be printed either with display or debug. To make this struct printable with debug, we can derive the automatic implementations provided by Rust. So again, we can use a derivable trait, meaning this struct over here implements the debug trait, meaning we can print it out using debug notation. So fill in the blanks and fix the errors. As you can see, we have here a custom type structure holding an i32 value. Types in Standard and Rust have implemented the debug trait. So as you can see, this is of type i32. Now all of the types in the standard library have implemented debug or even display. So we can use here the display notation, and this will print out fine. Now over here we must use debug notation because this is a type that we have created. And again, to use the debug notation, we have to derive the debug trait. Like that. And that means structure implements the debug trait and we can then print it out. So this i32 type will be printed automatically because it's a type defined in the standard library. And over here we just had to derive the debug trait and then use debug notation here. So format debug definitely makes one type printable but sacrifices some elegance. Maybe we can get more elegant by replacing this notation with something else, but not this. Alright, let's see. We have here a custom type that derives the debug trait. Then we are here instantiating it. And when we now execute the program, as you can see, the output will be like this. Now we want the output to look something like that, and we can for that use the pretty notation, just adding this hashtag symbol between the colon and the question mark. And then the output should look much more pretty. As you can see, the output will then be like this. And notice we first had to derive the debug trait in order to print it out using debug notation. We can also manually implement debug trait for our types. So as you can see, we have here two custom types, structure and deep. Now structure holds a type of i32 and deep holds a type of structure, meaning these are basically nested. So we have deep, which holds a structure, which holds an i32, right? The problem with derive is there is no control over how the results look. What if I want this to just show a 7? So as you can see, we are here instantiating it with a value of 7. Now when we print it like that, then as you can see, the whole structure will get printed out, but we only want the value over here. So what we can do is we implement the debug trait manually, meaning we can manipulate the output. So let's see the debug trait in the documentation. And as you can see, this is the debug trait as defined in the standard library. So let's copy this function signature. So we can then over here implement the debug trait. And this is found in a module and this is inside the module FMT from the standard library. And we want to implement it for the deep over here. Now we remove that, and we also remove that because we are implementing debug trait manually, right? We don't need the derived implementation. So let's see, deep, then I will copy the function signature. So here we can use a custom type fmt result. And you know what, we can use a namespace here. So then we don't have to write here standard all the time. Like that, I can delete this lifetime. And now we can implement the debug trait, namely this fmt method. So again, we want to write to a buffer. So we use the write macro, and it should write to this formatter, which is provided by the debug trait. And then over here, all we want to actually print out is, in this case, self, right? The instance over here. And then we access the first element. So when we access the first element in a tuple, we use the dot notation like that. And inside here, we have now accessed structure, and we want to access this value, this structure struct holds, right? So we again use 0. And that's basically it. Now it should print out. And of course over here, fmt formatter, this is also from the fmt module. And as you can see, now 7 will print. So all we did over here is manipulating how the output of the debug trait looks like when we use debug notation. And as you can see, we have defined for the deep custom type over here how the output should look like. So the output will just be the inner element of deep and structure, right? This I32. And we just access that and write it to this buffer. All right. Display. Yeah, debug is simple and easy to use, but sometimes we want to customize the output appearance of our type. This is where display really shines. Unlike debug, there is no way to derive the implementation of the display trait. We have to manually implement it. Another thing to note, the placeholder for display is this and not that. So this would be for debug trait. For display, we are using that, and you know that already. So make it work. As you can see, again, we are using the fmt module, and we have a custom type point2d holding two fields of type f64. Now we want to implement the display and the debug trait for this custom type, meaning when we instantiate this point2d, then we can pass the instance over here and it will give us this output, right? So we are using here the display notation and debug notation. And as you can see, we can here define different outputs. So when we pass an instance of point, then the display trait actually will output something like that. If we use debug notation, then we want the output to look something like that. And that's what I mean when I say we can manipulate how the output of a custom type will look like. So I will take over here this method and I will just copy it over here. Now let's first implement the display trait. As you can see, we want the output to look something like that. So we define here display, the X field, the value of X field, and then plus the value of the Y field, and we have here an I, okay, like that. And we can access these fields using normal notation self.x and self.y, right? And for debug notation, we want the output to look something like that. So let's copy this, put it inside here. And as you can see, we want here the value of the X field and here the value of the Y field. And as you can see, we are here using curly braces, and this is usually for the placeholder. So what we have to do here is using two of them, meaning this curly braces over here will basically be escaped. All right. And then over here we have to provide the arguments self.x and self.y. Let's see. And this is compiling. Now let's see the actual output. As you can see, I'm using display notation and debug notation and just provided an instance of the point to the type. And as you can see, this will then be the output. So question mark operator implementing FMT display for a structure whose elements must be handled separately is tricky. The problem is each write generates a FMT result which must be handled in the same place. Fortunately, Rust provides the question mark operator to help us eliminate some unnecessary codes for dealing with FMT result. So, let's see. Again, we are using the FMT module and we have here a custom type, a struct list, a tuple struct list holding a vector of I32 elements, right? Over here we are instantiating this list with a vector holding 1, 2, 3. Now as you can see, when we put this list over here into the format macro, then we want the output to look something like that. So we want to print these square brackets, the index, colon, and then the actual value. Now let's see how this would be implemented. Notice over here we are implementing the display trait, so we can then use it to display the type directly. So as you can see, this is the function signature from the FMT module. And as you can see over here, we return a type of FMT result. Now this is a type. Now this would be a type alias, and we have covered that. Now over here, we want to extract the value using tuple indexing and creating a reference to vec. So the first thing we do is we want to access the vector in the list struct, and we do that using tuple indexing, right? We want the first element because there is actually only one element on here. So we access that, meaning we will get back a reference to a vector holding I32 types, right? Here we are taking a reference. Now, then we have basically unwrapped this vector into this variable. Now, as you can see, we use the write macro to write to this buffer this square bracket, because as you can see, this is what we want to output. So the first thing added to the buffer will be this square bracket. Then iterate over v in vec while enumerating the iteration count in count. So we take this vector and we iterate over it and enumerate, meaning we will get back a tuple holding the index and the actual value. Then for every element except the first, add a comma. Use the question mark operator to return on arrows. So as you can see, if count is not equal to 0, meaning if it is in fact the first element, then we don't add this comma, all right? Because we don't want to look something like that. So this is only after the second iteration that this comma will be added. And then we write the actual value over here. And this iterates 3 times, right, for each element, and then in the end it will put into the buffer this square bracket. So when we run that, as you can see, the output would be something like that. But this is the output that we want. So what's missing over here is we didn't include the indexes, right? So what we can do over here, we want here to be the index and then a colon like here and a space and then the value. So we have the index in this count variable, so let's use that. And again, we can then run the program, and this succeeded. So let's actually print that out. As you can see, this would be the output. So we can really manipulate the output of our custom types using the debug and the display traits. And by the way, as you can see, we are here using the question mark operator because this over here could potentially fail, right? That's why we are using this here, and we use here the result type from the FMT module, just in case any of these operations here fail. Alright, see you in the next topic.